Hey everyone, and welcome back to PrepFusion. So today we will start with the control system. So I'm not starting with the first chapter of control system, basics of control system. I'm directly starting with frequency response. Okay, like just I thought of it because frequency response is pretty important. So like videos will come, the basics of control system, those videos also will come, right? There will be, I will divide control system into 4 parts. Part 1 will include basics of control system, signal flow graph, block diagram reduction technique, and time response. That video will come after this video. Okay, so because for some reason I recorded this earlier, so this was recorded, so that's why I had to upload this early. So who can watch this video? The students who are comfortable in control system before frequency response. Basically your root locus, Routh-Hurwitz criterion, basis of control system, signal flow graph, block diagram reduction techniques, and also your time response analysis. So students who are comfortable with this, they can continue. If you're not comfortable, for now you can drop this video. I will bring, of course, the complete control system as well, like part 1, part 2, part 3. This is the part 4 basically, the frequency response part, or sorry, part 3 basically. Okay, the frequency response. So those who just want to revise the frequency response, they can watch this, but there is some prerequisite. So you have to watch the part 1 and part 2. Okay, that is a prerequisite. But you will say, sir, currently part 1 and part 2 have not been uploaded, right? For like later it will be uploaded. Currently it is not uploaded. So then you can wait. Then you don't need to watch this video. Just if you want this series to continue, hit the like button and then you can drop off, go away and do your thing and watch the part 1, part 2, then come back to this video. But you hit the like button, comment down below. This will help us to reach to more audience and hype the video, right? There is a new feature, hype. Also hype the video, like that will help us out, right? If you want this series to be continued, then do all these things, right? Now watch these 2 parts. After that you can come. If you're not comfortable with control system at all, if you're somewhat comfortable with control systems, the topics mentioned, then you can continue. So first of all, we'll start with polar plot, R-PYQ, the frequency response, second order frequency response of second order systems, and polar plot. Okay, and then we will continue Nyquist and then Bode plots. So let's start with the polar plot. So let's start with the first topic of frequency domain analysis, that is polar plots. Before starting that, I want to discuss exactly what is frequency response. Why do we study frequency domain analysis, and why are there 3 different types of analysis like Bode plots, Nyquist plots, and polar plots? Both, like all the 3 plots have their own importance. Okay, so first let's understand what is frequency response of a system. Frequency response basically deals with the response of a system when a sinusoidal input is given. That is what we mean by frequency. What is frequency? What do we mean by frequency? Frequency of what? Frequency of a sinusoidal signal. Do a DC signal has a frequency? No, DC signal doesn't have any frequency. We only discuss about frequency when I have a sinusoidal signal, right? When it is like periodic, when it is periodic, right? So first thing that you should get into your head is we are discussing frequency response. That means we are discussing when a sinusoidal input is given to the control system, what type of response I will get. That is what is meant by frequency response. The magnitude and phase relationship between the sinusoidal input and the steady state output. Steady state output is also very important point. I will explain why am I giving so much emphasis to steady state output. Okay, in 5 minutes we'll understand. Of a system is termed as frequency response. Okay, so this is just a definition, but mathematically what do I mean? So if I have a input here, okay, and this is a simple negative feedback system, and like I have a feedback that is not non-unity negative feedback system. G of s is the OLTF, H of s is the feedback gain. Okay, and this is my transfer function. I hope you know all these things. Okay, now so in my full course I have derived it from scratch. Here obviously we don't have time and this is not that important, but you should know that, like this is the thing, the concept you should know. The derivation I'm not doing because I don't want to waste the time here. Okay, so if I have given a input that is sinusoidal, whose amplitude is R and whose frequency is omega naught, then the output, the steady state output will be what? Steady state output, that from this point, right, from this point the steady state output will be something like this. If I write here, steady state output will be C of t will be equals to some C constant into sine of omega naught t plus phi. Phi, like if you know a bit of signals and systems, that means if you give a sinusoidal input,
then you will get a sinusoidal output of same frequency if it is a LTI system. And obviously in control systems, whatever we discuss, it is a LTI system. If you understand this thing, great. If you don't understand, skip this. Okay, no need to worry about that LTI system thing. Okay, so this is the phase output and this is the gain. So by varying, what we'll do, we'll just vary our omega naught. Okay, omega naught will be variable. We'll vary our omega naught and see the response, of this amplitude and see the response of this phase. Okay, phase and amplitude, and that is what we plot in Bode plots, in Nyquist plot, in polar plot. That is exactly what we plot. I think many students who are watching this might be a bit new, because what do we plot, what do we exactly plot, that you don't know. Okay, I think you have understood something, that what do you exactly plot, and there might be some chances gate can ask some conceptual question from this particular topic. Okay, so I will just show you a bit of like proof why is this the case, like why am I emphasizing on steady state error, so steady state output. So here I am giving it some input a naught sine omega naught t, and the transfer function is g of s upon 1 plus g of s. It is some, like it will be some numerator upon denominator, right? It will be some function of n of s by d of s, correct? So my r of s is this in Laplace domain, and if I just do all the things, right, if I multiply this and then finally in my full course I have done this. I will not do this here because like this is not the purpose of this lecture. Purpose of this lecture is to crack the examination. So like after solving all this, right, the final outcome, final result, what you will get is this one, okay, like in time domain, doing the Laplace transform, multiplying it in Laplace domain, then again taking the Laplace inverse, ultimately whatever you will get is this. So ultimately you will get a sinusoid whose amplitude will be a naught, the initial sinusoid amplitude, multiplied by the magnitude of the transfer function at frequency omega naught, j omega naught, okay, plus some expression, okay, some expression that is a function of t, also that is a exponential function. Okay, so what is this? This is the AC transient that we get. You remember whenever we used to give a sinusoidal input to a RC circuit or something like that, we used to get a AC transient. It is that exact thing. Okay, so as I am discussing about steady state error, what happens generally, this m, right, m is negative, like this m comes out to be negative. Okay, so if this m comes out to be negative, like this should be minus of m something like that. This if this m comes out to be negative, then what happens is this whole term goes to 0. Okay, because t increases and very high value raised to power negative will be 0, right? So that's why this goes to 0. That's why system is stable. If the system is stable, that is, if the system is stable, then only this term will go to 0. Why? Then my m, all the poles will lie on the left hand side. If all the poles lie on the left hand side, then m will be negative. If m is negative, that means as t increases, the value will reduce. I hope you understand this basic maths. That's why. So this goes to 0 only when the system is stable. That's why stability is also important in sinusoidal analysis. That's why we would always discuss whether the system is stable or not. If the system is not stable, then this term will be dominating because m will be positive. Then 2 raised to power something positive, right, will increase in value. So this term, this AC transient term will also be there with sinusoidal. But actually, if I have given some sinusoidal input, I will want some pure sinusoidal output. Okay, that is my desired output. Obviously, I am not getting it. That's why we want our system to be stable. How we make it stable? By making all the poles on the left hand side. I hope you understood in frequency response as well why poles lying on the left hand side is very, very important. Okay, this is the reason, because this is the extra term that we will get and we don't want this term. Okay, so as opposed to unit step response, which we study in time domain analysis, the steady state sinusoidal response will be oscillatory in nature, of course, because I'm giving it a input that is oscillatory also, but also I will get a transient response as well, but it will go to 0 as t increases. As the time increases, it will go to 0. Okay, the response will settle down to a sinusoid of same frequency as it is a LTI system, but it will be scaled in magnitude by t of j omega and shifted by phase phi. Okay, that's why we are interested in this, because how much am I scaling, how much is my phase at particular frequencies, I'm interested. Okay, that's why we plot those things. Okay, by that also we will understand the stability as well. This is the property of LTI system. So we have to, as mentioned, we have to visualize the variation of a steady state output with respect to omega. We have to visualize this. So that's why we made few plots. Okay, first one is the polar plot, second is the Nyquist plot, third will be the Bode plot. Okay, so in polar plot we plot the real of the OLTF after replacing s with j omega. So you, in the question, you will be given the function g of s into h of s. You will replace s with j omega. Why? I hope now you understand why we replace s with j omega. We replace s with j omega because I'm giving a sinusoidal input and I'm varying my frequency. That's why we replace s with j omega, where omega is variable. So in polar plot, we plot the real and the imaginary part of the OLTF with respect to omega. Omega varies. Okay. So in x-axis, I will have the real, and y-axis, I will have the imaginary. And like this is just like a plotting of complex numbers, right? Similar to that, but instead of z, I have real of g of j omega and imaginary of g of j omega. Now, omega in this case varies from 0 to infinity. Okay, very important point to note here. For polar plot, omega will be positive because we are only discussing about positive frequency, and this happens for real signals, right? Real signals generally have positive frequency. Obviously, we don't discuss about negative frequency. How can frequency be negative? Like then time period has to be negative, right? That is other discussion. That is mathematically correct. But in real signals, obviously we will only get positive signals. That's why polar plot is only used for positive frequencies. Nyquist plot. Nyquist plot is also like a bit different. Why? Because it can comment about absolute stability, which we'll discuss, which will come to. Don't worry about that. So Nyquist plot is the same only, like polar plot only. Difference is the omega varies from minus infinity to plus infinity. So I have more range of omega. And why is that important? That is mathematically important to find the absolute stability. That of course I will discuss later on. Okay, once we'll come to this Nyquist plot. And Bode plot also we only discuss about positive frequencies, omega greater than 0. Okay, Bode plot also only discusses about positive frequencies. It has two plots. One is the Bode magnitude plot, another one is the Bode phase plot. So this also we'll discuss. This also can be used to find stability and also other variation, other parameters. Okay, now so this is like just a standard second order system that you have seen, and this you already know, right? Like there is another topic known as frequency response of a standard second order system. That also we'll study at the end. That is also important. Just two formulas are there, so at the end just remember those two formulas. Okay, and that should be enough. That should be more than enough. Okay, for the frequency like for the frequency response. So the difference in time domain and frequency domain, I hope you have understood the exact difference. All signals functions are depending on time, but in frequency domain, all signals and functions are depending on frequency, because my omega is varying, right? I'm giving it some sinusoid. Initially I was giving it some 50 hertz sinusoid, then I'm giving it some 100 hertz sinusoid. That is what we're interested in frequency domain. So that's why frequency domain is independent. So here t is an independent variable in time domain, and in frequency domain omega is an independent variable. So how, like the relation between frequency domain and time domain, which particular thing relates the frequency domain and time domain? Fourier transform. This is for signal system. I'm not discussing about this, just giving you a idea. I hope you like this also helps you revising the signals and system as well. Okay, so okay, so this is the transfer function of a second order system. This like how do I find out the transfer function of a standard second order system? That is what is written over here. So this, right, I will come to later on, because this is for the standard second order system. This I will come to later on. Okay, not now. So now let's start with the basics of polar plot. So polar plot, as I have already mentioned, is a combination of absolute values of magnitude and phase angle. Okay, so like it is a combination. Like you might say, sir, you said that we have to visualize the gain and the phase. How am I visualizing the gain and the phase with real and imaginary part of the g of j omega? Yes, the real and imaginary part together combined can comment about the gain and the phase as well. Okay, because if you have a complex number, let's say 1 plus j2, can you comment about the phase of this complex number? If I know the real and imaginary part, yes. How can I comment it? The phase will be tan inverse 2 by 1, correct? And the magnitude will be under root 1 square plus 2 square, correct? Under root 1 square plus 2 square. That is what my magnitude will be, correct? So from the real part is what? 1, imaginary part is 2. So from the real and imaginary part combination, I can comment about the phase and magnitude. So polar plot, that's why polar plot is invented. So this is how a polar plot axis will look. Okay, real part will be on the imaginary axis, imaginary part will be on the y axis. Okay, now few basic things I hope you know already, because I hope you are studying for like GATE exam, and basic things, these things you should know because exam is only about 2 weeks. But still I'm explaining few things. This, right, this particular direction is the positive x-axis, which has an angle of 0 degree or 360 degree. What is the angle? Angle means the phase of the real and imaginary part. That is what I mean by angle. Okay, now the y-axis. Y-axis has angle of plus 90, because if I move in the clockwise direction I will have plus 90 angle, or if I move minus 270 in the sorry, this was in the anti-clockwise direction, this is in the clockwise direction. If I move 270 in the clockwise direction, then I will reach in the positive y-axis. Because I'm moving in the clockwise direction, that's why the angle becomes negative. Basic things I hope you know. Clockwise angle is negative, anti-clockwise angle is positive. This I hope you understood. Okay, so these are the angles. I hope you understand. And x is this, y is this. This you already know. In polar plot, positive angle is measured in the counterclockwise direction of the real axis, and negative will be just in the what is it, clockwise direction. Okay. The instantaneous magnitude of the OLTF is represented by instantaneous value of distance from the origin to that point. Like this is just how you plot a magnitude, right? The instantaneous value like this, right? This 2 plus 1 plus 2j, 1 plus j2. Where will I plot it? It will be somewhere here, right? 1 will be here and 2 will be somewhere here. So this will be the real part is 1, imaginary part is 2. So this will be my point. Okay, 1 comma 2. Okay, in the polar axis. But of course, we don't have this beautiful thing. We have some g of s of h of s, and according to that we have to vary. So I'll come to that. Polar plot describes the stability of CLTF by using the frequency response of OLTF. Now, why are these methods so famous? Now, these methods are famous because we can discuss about the stability of my closed loop system, about the poles, right? Whatever poles I have derived in the just before 10 15 slides, whatever poles I got, it can discuss about the poles of the CLTF by with the help of OLTF. That's why these methods are so famous, because finding the poles is very difficult. Like if the order becomes higher, right, third order, fourth order, finding its pole become higher, difficult. That's why we have these tools to understand the stability. Now I should mention, polar plot actually does not totally discusses about the stability. Okay, it cannot comment about the stability, absolute stability. It can comment about the relative stability. That I will come to just in 2-3 slides. I will come to that. So it talks about relative stability, but Nyquist plot can comment about absolute stability. That also we'll understand later on. Okay, so let's first draw a few basic polar plots, and from there our basics will be strong. Then I will come to the actual questions what they ask, because if you don't know how to draw a polar plot, how will you understand the question? Okay, so there are many ways to plot a polar plot. First way is directly understanding the real and imaginary components. So the first function is g of s h of s equals to 1 by s. So if I replace s with j omega, this will become 1 by j omega. Now I will segregate my real and imaginary parts. So what is real part here? So real of g of j omega, so this will be my x value, right? This will be my x value because x axis is the real of g of h of omega. So that is equals to 0, because obviously omega is real number, omega is always positive and it is a real number. So this will always be imaginary number. Okay, so real it doesn't have any real component. But what about imaginary component? Imaginary component of g of j omega into h of j omega will be straightforward 1 by omega. Okay, is it? No, it is not, because remember, how do I write my imaginary real? It is x plus jy, right? X plus jy. And what is it? J is in the bottom, right? So j will go in the top. If j goes in the top, if j goes in the top, it will be minus, right? This j will go at the top. This will be minus j by omega. This will be minus j by omega. Okay, so this is how you understand this thing. Okay, so your imaginary part will be negative, it will not be positive. So please be careful of the sign as well. Okay, so now we'll plot it basically. So real part I know is 0, so I don't have to worry about x axis. This will never lie in the x axis. Whatever omega value is there, x value will always be 0. Okay, but y value is changing. It is minus 1 by omega. Okay, so y value is minus 1 by omega. That means what? As I increase my omega, if omega is almost equals to 0, right, it will be what? Minus infinity, correct? So I will start from somewhere here. So obviously we don't talk about omega equal to 0, we talk about just above 0, that is 0 plus. And as I increase my omega, what will happen? This 1 by omega will reduce. So the negative value, it will go from negative towards the origin, because x value is 0. So I will lie on this y axis only, but this will go from negative infinity of y to 0. Okay, because as y is infinity, then imaginary part will also become 0. So this will be plus, this will go travel more towards 0. Okay, sorry, this will be at omega equals to infinity. Imaginary part will go 0 at omega equals to infinity. Okay, so yeah, that is the case here. Now is there any other way to solve? Next method is magnitude and angle method. So first method was simply segregating the real and imaginary part. Next method is magnitude and angle method. So magnitude and angle method, what you will do, you will first write the magnitude expression. So if I want to write the magnitude expression for this, what is the magnitude expression for this? So the magnitude expression for this is 1 by omega, correct? Like how do I write magnitude? So this right can be written in a more better manner, 1 plus 0 j omega. Now if I want to write the magnitude, the top part has only real components, it will be 1 square plus 0 square, because it is plus j0, and the bottom part has only imaginary components, so it will be 0 square plus omega square. So this will be 1 by omega. Okay, this will be my magnitude. This is positive. Magnitude can never be negative, of course. So now I will discuss about the phase. So what will be the phase? Phase, can you tell me what phase this will provide? The numerator is providing 0 degrees of phase. The numerator is providing what phase? Sorry, the denominator is providing what phase? So obviously it is the denominator, that's why minus sign will come, then tan inverse y upon x, the imaginary component upon the real component. So real component is 0, imaginary component is omega. So this is tending towards what? This is tending towards infinity. So what is tan inverse infinity? Tan inverse infinity is 90. So this will be 0 degree minus 90. So this will come out to be minus 90 degrees. Okay, this will come out to be minus 90 degrees. So what do I observe? I observe that the angle will always be minus 90. What is minus 90? Just I have explained, right, in the graph itself. Minus 90 means I'm lying in the negative y axis always, no matter what. Phase will never change, so always I lie on this negative y axis, no matter what. Okay, and the magnitude will keep on reduce, right? Magnitude will keep on reducing. Why? Because it is magnitude is equals to 1 by omega. So as omega increases, magnitude will also keep on reduce. Okay, so if I just want to take few values, if you want to take few values, you can take at omega equals to 0. What is the magnitude? Magnitude is infinity. At omega equals to 0, magnitude is infinity. You put omega equal to 0 in this expression, magnitude you will get as infinity. At omega equals to infinity, magnitude will be 0. What will the phase? Phase will never change. Phase is independent of frequency. So phase will always be 90 and 90, minus 90 and minus 90. So what will be the polar plot? Polar plot, of course, will be same. It will not be different. But from where we'll go? We'll go from this. We'll go from, as I am always lying on the negative imaginary axis, the y axis. What is happening? Just initially at omega equal to 0, I have infinity, and at omega equals to infinity, it is going towards 0. Okay, that means this is at omega equals to infinity, and this is at omega equals to 0 plus. Okay, so like I hope you have understood this. So next one, I'm actually like leaving it up to you. A bit of part I have done. Okay, bit of part I have done, the magnitude and phase angle. So I'll just quickly solve. I will not explain here, because I will just tell you the basics, and then I will try to quickly solve, because we have to learn a lot of things in short amount of time. We have to revise the things. So if I want to plot the phase plot, again I can do the same thing. I can either separate the real and imaginary parts, or take the magnitude. So here I have already done the cross multiplication. I'm using the first method. So what do you observe? That my this, like if I separate the real and imaginary part, then my real part is always positive and imaginary part is always negative, because omega will be always positive. As omega is positive, I have no chance of going this negative and no chance of going this negative. Sorry, I have no chance of going this positive and no chance of going this negative. Okay, so what I can say is x will always be positive and y will always be negative. In which quadrant I am? In which quadrant I am when my x is positive and y is negative? That means I am at this quadrant, right? This quadrant, the fourth quadrant. Okay, so your polar plot will only lie here. That much information you know. Now what else? Now you can discuss about the imaginary and the real parts. I can observe at omega equal to 0 what is the real component. Okay, at omega equal to 0 what is the real component? At omega equal to 0 the real component is 1. That is x equal to 0 at omega equal to 0, and at omega equal to 0 what is the imaginary component? Imaginary component, this value will be 0 because this will go to 0, this is finite, so 0 upon finite is 0. So this will be 1 and y will be 0. Okay, so x is 1 and y is 0, so I am lying somewhere here. Okay, then at omega equals to infinity what is happening? Obviously this is like constant 1 and denominator is increasing, it is increasing towards negative, it is increasing towards infinity, so obviously 1 upon infinity will give me 0. This is at omega equals to 0, and at omega equals to infinity my x will be 0 and y, right? If I see here, you can apply the concept of limits. Okay, if I apply the concept of limits, I can see my y also will go to negative, y also will go to 0. Why? Because as omega goes to infinity, this is infinity, fine, but here I have infinity whole square, so the denominator is increasing at a higher rate than the numerator. Like basic limits concept I will not explain here. Okay, these things I will not explain. So denominator is increasing at a higher rate, of course it will go to 0 as well, so y also will be 0. So ultimately I will start from here and then I will end here. And how will I travel? I will travel only in the fourth quadrant. I will always lie in the fourth quadrant. So I will travel something like this. Okay, the actual graph also plot also will be something like this. So the plot will be something like this. Okay, this will be the plot. This is at omega equals to 0 and this is at omega equals to infinity. And generally in polar plot, right, what we do is we tell the direction as well, in which direction am I moving. From 0 to infinity I am moving in this anti-clockwise direction, right, like this. So this is the polar plot. Now, like of course you can do the other thing. What is the other thing? Other thing is that with the second method, it is magnitude and angle method. So if you just do the magnitude and angle, you will see the magnitude function you are getting this, angle function you are getting this. Now you just plot for few values. Okay, for omega equal to 0, what is the magnitude? For omega equal to 0, the magnitude will be simply same only, that is 1, and angle will be 0 again. Okay, angle will be 0. For omega equals to half 1 by tau, for omega equal to 1 by tau, this will be what, 1 square plus 1 square, that is 1 by under 2. Okay, 1 square plus 1 square, 1 by under 2, that is 0.707. And for omega equals, sorry, what is the phase angle? If I put here 1 by tau, this will be tan inverse 1, that is 45 degrees. So this will be 45 minus 45. Remember, this is minus 45. Okay, then for omega equals to infinity, this will go to a 0, this will be minus 90. Okay, so this is how you do. I will not explain much here, I will just quickly go because we have a lot of things to cover. Like this is the graph will be, this is how the graph will be, although it is not like exact like a circle, because this will be more closer and this will be more further. Okay, so just I have shown you how to basically draw the polar plot. So can you just draw the polar plot of this as well? I will not do it, that is up to you. Just get your rough notebook up and just draw the polar plot, because obviously I have to skip few things, I cannot explain everything here. Try to draw the polar plot again, same thing, and you will observe that you will get a polar plot like this, which will lie in the third quadrant. Okay, so obviously the type is increasing, the quadrant is also changing. Previously I was lying in this quadrant, now I am lying in this quadrant. So of course there is a relationship that of course I will discuss later on. Okay, don't worry about that. So these are few homeworks for you. Okay, these are few homeworks for you. Do this on your own. Try to draw the polar plot of the following voltages. I will not do because we have to cover a lot of things. I wanted to, like, this will be a good revision for you. Try to draw the polar plot of all of this and verify, right? Verify. I have all written. I have drawn all of this. just verify with yourself, then you will be like correct. Okay, then you will remember few things if you have revised. So few things are there, these are just terms, you don't need to remember them, these terms. Okay, but important point to note here is like whenever a pole is added at the origin, like first let me define what is head and tail, because I will not like say these names out loud multiple times. So head is the end of the polar plot. Head is like, for me this is just nomenclature, nothing else. Head is the end of the polar plot. What I mean here, right? At omega equals to infinity, where my polar plot ends, it is the head, just like this, where our like eyes end or something like that. So head is the end of the polar plot, and tail is the start of the polar plot. Okay, tail is the start of the polar plot at omega equal to 0. Okay, so this is the tail and this is the head, that's it. Now just few key observations, this is very important. Now this is important for exam point of view, right? This is important for exam point of view. Okay, so when a pole at the origin is added like this, right? If you observe, whenever I have added a pole at the origin, right? If you see, whenever if I add a pole at the origin, what will be the difference from the previous? If the pole was not there at the origin, the difference will be, it will shift the angle will shift by minus 90. If you see, the head and the tail of the polar plot will be shifted by 90 in the clockwise direction, or with sign, if I want to speak, it will be minus 90. Okay, when a pole is added, the angle of the head, like the head and the tail, both will be shifted by 90 degrees. Why? Because what angle does 1 by s contribute? It is 1 by j omega. And what angle does 1 by j omega contribute? Minus 90. That is why everything gets shifted by 90 degrees in the clockwise direction. Okay, basic simple funda. When a pole on the real axis is added, head of the polar plot is shifted by 90 degrees in the clockwise direction and tail remains same. Now why is that? Why here both changes? Because irrespective of the frequency omega, I will always get a minus 90 degrees. So everything will be shifted by minus 90 degrees. But here it is telling that I am just adding a pole in the real axis. That means, let's say initially I have s plus 1, now I added s plus 1 and s plus 2. So what will happen? Initially it will not do much. Initially it will not give any phase. Why? Because my phase will be tan inverse omega minus tan inverse omega by 1 minus tan inverse, like I'm not explaining how I got to this expression, omega by 2. So if I look right at omega equals to 0.1, this will be 0.1 divided by 2, that is 0.05. So this will almost go towards 0. Okay, so this doesn't contribute initially, so the tail doesn't move much. Okay, obviously tail at omega equal to 0, this will not contribute anything. At omega equal to 0, this will not contribute anything. But at omega equals to infinity, the value will increase, right? This will be some, let's take an example, tan like omega equals to 500. So this will be tan inverse 250. So now it is contributing, because previously in the angle expression I only had this. Now I have this, and this is contributing. Tan inverse 250 will be some good number, right? Good value. So that's why ultimately at infinity this will provide how much phase shift? 90 degrees in the clockwise direction. So that's why the head shifts by 90 degrees, but the tail doesn't. So these 2 points are important for exam point of view. So make sure you remember these 2 points. Okay. So like if my OLTF is minimum phase system, then the polar plot will represent the type. Okay. So what is minimum phase system? I will explain while explaining the Bode plot. Don't worry about it. Just this is also another key point to remember for exam point of view. I will explain minimum phase system while studying the Bode plot. Don't worry about that. So the OLTF is a minimum phase system. Then the tail of the polar plot will represent its type. Why am I saying so? So what is type? Type is the number of zeros in origin. Okay, number of zeros in origin. So this is my type. Now for now, just understand, a minimum phase system is a system where all the poles and zero lie on the left hand side of the spline. I will explain this more in detail, but for now this is. So this is important, because polar plot is not a unique representation. That's why it is important to mention that it is a minimum phase system. What do I mean by unique representation? All those we will learn. Don't worry about anything. Just give all the responsibility towards me. So type, number of zeros in the origin. So tail is the start of the polar plot, right? At omega equal to 0. So it doesn't matter if I have 1 by s or 1 by s square, because the starting point changes. If I have 1 by s, then like at omega equal to 0, only this will contribute, right? Why? Because if I write this expression 1 by s into s plus 1 at omega equal to 0, which of the expression 1 by s is contributing or 1 by s plus 1 is contributing towards the phase of the OLTF? Only 1 by s. Why? Let me replace s with j omega. This will be j omega plus 1. Now if I take the angle of this complex number, this will be like this 1 by j omega will contribute how much? Minus 90 degrees of angle, and the other one will contribute minus tan inverse omega by 1. Okay, so of course at omega equal to 0, which is where I am interested because that is the tail, this will go away, right? Any pole that is anywhere in the real axis, okay, that will vanish. Only the angle contribution of the poles at 0 location, poles at like origin, and poles at origin will be seen. The effect of the poles at origin will be seen. So of course if I have 2 poles, this will be minus 180. If I have 3, it will be minus 270. That's why this point is there. So the type of the system can be defined by the tail of the polar plot. Where does the tail lie? So here if you observe, here my tail is lying in the positive x-axis. So it is a type 0 system. There is no pole at the origin. Here like it is a type of system. If you would have drawn the polar plot, you will see the tail will start from minus 90 degrees, and for this also it will start from minus 90, and here also you can observe, right? Here this was a type 0 system, this was a type 0 system. That's why the polar plot started from positive x-axis, that is 0 degree. But this was a type 1 system, right? So polar plot should start from minus 90, which is exactly what is happening. Obviously it will not touch minus 90, okay, because at s equal to 0 something is blowing up, because at s equal to 0 magnitude will be infinity, right? That's why I cannot show it, but it will just be parallel to the y-axis. So that's why it is starting from minus 90 degrees. Okay, so I hope you understood this point. These 3 points are important for exam point of view. Okay, make sure you remember these 3 points. Okay, so now let's come like this, right? This is the summary. The summary I have explained, like where each, if the type 0, type 3, all those things are there, where will my polar plot end? Okay, so okay, where is the points? So here also I have tried to explain this. Okay, so here also I have tried to explain, if I have a type 0 system, the angle at 0 will be 0 degree, type 1 minus 90, type 2 minus 180, type 3 minus 270. Now you can draw the polar plot for all of this. Okay, I will not draw because we don't have time. If you draw the polar plot for all of this, right, ultimately what you will get is in the summary I will explain. If you draw the polar plot for all of this, you will see if I have a type 0 and order. Now order is also very important. Why is order important? Because order can tell you the order can be found out from the head. Okay, how? Here tail is starting from 0, so that means I don't have any pole at the origin, and head is ending at minus 90, because I am going towards this minus 90. I am touching this imaginary axis, right? So I am ending at minus 90. Okay, so if I am ending at minus 90, that means one pole was added. One pole was added. Of course the angle is going negative, so obviously one pole must be there, which is correct. So the order is 1 here. Okay, now here if I see again, I am starting with positive x-axis, that is 0 degrees of angle. I am ending at minus 180. I am ending at minus 180. Okay, so again, how many poles were added? Each pole contributes minus 90, right? At infinity, at omega goes to infinity, each pole will contribute minus 90. So overall I am getting 180 minus 180. That means 2 poles were added, which is exactly the case, right? Order was 2, because initially I had 0 poles at the origin, then 2 poles were added. That's why order is 2. Now same thing, right? I ended at 270, so 3 poles were added. 4 poles were added. I ended at 360, that is 0 degrees only, that is positive x-axis only. Now if I have a type 1 system, this is interesting. If I have a type 1 system, initially I started, if you remember, this was a transfer function, right? This was a transfer function. Initially I started at with the imaginary axis only. I was always lying in the imaginary axis only. Okay, and I ended at origin. So did the angle change? Did the angle change? No, the angle did not change. That means I don't have any poles in the real, I don't have any real poles. Either they can be at the origin. My poles can be at the origin only. That is the only possibility, which is the case here, because it is a type 1 system. Why? Because I started from what angle? I started from minus 90. So of course, if my tail is at minus 90, that means it is a type 1 system. Did my angle change at omega equals infinity? Did my angle change at head? No, the angle is same, that is minus 90 only. That means no pole got added. No pole got added, that means it is a type 1 and order 1 system. Then again, if it was a type 1 and order 2, which is the next example, I started from minus 90, then I ended at minus 180. Of course, in between, minus 90 angle was added, that means a pole was added. That means overall the order becomes 2 because I have a pole at the origin and one other real pole that got added after that. Okay, so that is what about type and order. And this is my like this is, you can like the same analysis only, nothing different for type 2 system as well. The same similar kind of analysis I've done just to have a quick revision for you guys. You can go through this. All the notes will be in the Telegram group. Don't worry about that. Okay. Now one interesting point comes. Try to like solve this. Okay. Until now we haven't solved something like this, and I will just have a quick drink of water. So first thing what we observe is this is a non-minimum phase system, right? This is not a minimum phase system. Why? Because until now what I have defined, for a minimum, like for a system to be minimum, the poles and zeros must lie on the left hand side. I can directly see one of the poles of this OLT is lying on the right hand side. So this is a non-minimum phase system. And then what will be difficulty? I will just explain. What will be the difficulty? I will just explain. If you don't know how to play with angles, how to find the phase angles, then this, right, from this point on it will be very difficult for you. And generally GATE will not give questions on this. Like GATE will not ask you to plot the polar plot of a non-minimum phase system, but if they do, many students will make it wrong because they don't know how to find the angle, they don't know the basics. So if I have to draw the polar plot of this, you have to be very careful. You cannot use the simple basic tricks and techniques like the tails and head type by type and order, right? If my type is 3, order is 3, then where will I lie? You cannot do that. You cannot apply it here, okay? Because the angle contributed by this will be a bit different. So go by the basics. I have taught you two basic methods. One is using the like separating the real and imaginary parts. Other one is simply the magnitude and the phase plot. So the first method is this one, okay? The like real and imaginary parts, okay? Or you can go with the angle and phase. So I will solve using the like magnitude and the phase. You can also solve using the real and imaginary part as well. That also you can do, okay? That is the homework for you, okay? So if I want to find out the magnitude, so first I have to replace s with j omega. So this will be g of j omega into h of j omega. This will be equals to 1 by j omega into j omega minus 2, okay? Now if I want to find out the magnitude will be magnitude of g of j omega, h of j omega. This will be equals to, just hold on, this will be equals to 1 by omega into omega square plus 4 whole under root, okay? This will be the magnitude of the OLTF. Now what about the phase? Okay, the phase, like magnitude I have already found out. What is the phase? So phase of this will be like, this will contribute how much? This will contribute minus 90, that we already know. So angle due to the pole at the origin is minus 90. What about the angle due to this? Now this is interesting. This is interesting, okay? In which quadrant it is lying? So my omega is always positive. So this is a complex number whose imaginary part is always positive, but its real part is always negative. So in which quadrant am I lying? Imaginary part is always positive, but the real part is always negative. So I am lying here, which is in the second quadrant. So what is the angle formula here? If you remember, the angle formula here was like, this is 180 and I have to just subtract the theta, extra theta from it. I will get the angle from the positive x-axis. I have taught this in my control system full course. I will not explain here. So it will be 180 minus theta. So theta is tan inverse magnitude of y, absolute value of y divided by absolute value of x. So absolute value of y is omega and absolute value of x is 2, okay? This is negative, but remember, what did I say? Absolute value of x and absolute value of y. So absolute value of minus 2 will be plus 2 only, okay? So that removes the ambiguity. So angle is this 180 minus tan inverse omega by 2, but this is in the denominator. So of course it will come with a minus sign. When it will go to the numerator, it will come with a minus sign. Angle becomes opposite when it goes to the numerator. So it will be minus 180 and plus tan inverse omega by 2. So this is change. This is change, right? If you would have just simply solved it for s plus 2, then the phase will come different. The magnitude will be same, but the phase will come different. That's why polar plot is not unique. I will explain just in a bit. Okay, sometimes just in a bit I will explain. So this will be plus sorry, this is minus 90 and this is minus 90. Okay, sorry, yeah, plus this is in the color question. Yeah, this plus 180. Yeah, everything is right. Yeah, so this is minus 270. This comes out to be minus 270 plus tan inverse omega by 2. Now I don't like minus 270. I don't like negative numbers. So what I will do, I'll just simply add 360, because adding and subtracting 360 from angle doesn't make any difference, because I'm just rotating a whole circle. So I don't like negative numbers, so I will add a 360. So this will become plus 90 plus tan inverse omega by 2. Okay, so now if I want to like have the table of values, right? So magnitude at omega equal to 0 will be infinity, because I have a pole at the origin, and at omega equals to infinity will be 0. Simple. Okay, but the phases are different. If you see, phase will be a bit different. The angle at omega equals to 0 will be still plus 90 only, because this will be vanished. This will be plus 90. Okay, remember, for just simple a for just simple, what is it, this one, right? If I just see this type 1 system, if you remember, for this system the angle, right, was contributed minus 90, but now I am getting the angle plus 90. So I hope you have understood. Just hold on a second, my PC is getting heated. I have to do something. Yeah, now it should be fine, I guess. Now it should be fine. Okay, so as I was explaining, the angle is minus 90 for a minimum phase system, but for a non-minimum phase system the angle is not minus 90, it is something else, right? Plus 90. Okay, now if I just comment about also the angle at infinity, at omega equals to infinity, what will be the angle at omega equals to infinity? Angle at omega equals to infinity this will contribute plus 90, this will contribute plus 90. Overall the angle will become plus 180. Now if you would have used previous formulas, right, then you wouldn't have been able to like understood, then you wouldn't have been able to recover the transfer function from this much information. From this much information you wouldn't be able to recover the transfer function. Why? Because plus 90 and plus 180 at omega equal to 0 and 180 at omega equals to infinity will be different for other transfer functions. Okay, I will discuss as well. Okay, so the polar plot for this will be something like this. So it will start from plus 90, then it will go to plus 180. Plus 180 is from this, right? So it will, and the magnitude will also go to 0. So like the key point is, I will just tell you this, do the homework. The homework is try to do the polar plot of s plus 1 divide by s cube, s plus 1 divided by s cube. Okay, try to do the polar plot. If you try to do the polar plot of this, you will see you are getting the same polar plot. Okay, but the two OLTFs are different, but I'm getting the same polar plot. Okay, if you just try, that means what? That means polar plot is not unique. Why it is not unique? For two different OLTFs I'm getting the same polar plot. So if I just give you the polar plot and tell you, don't tell you whether this is a minimum phase system or non-minimum phase system, then you won't be able to see the transfer function. If I tell you it is a minimum phase system, then for sure you will say this is the transfer function. Okay, that is why the term minimum phase system is very important to identify whether, like, to identify the transfer function from the graph. So we generally, that's why in the GATE exam as well, very rarely you will be asked to plot the polar plot of a non-minimum phase system. Okay, generally you will get asked to plot the polar plot of a minimum phase system, so that you, the transfer function is recoverable. Okay, so that we can recover the transfer function. So this was important point. This is what is I have written. Okay, so now we will come to the main topic, and this is the most important part of the polar plot chapter, that is gain margin and phase margin. So before starting the gain margin or phase margin, let's understand what are gain margin and phase margin and why are they important. So gain margin and phase margin actually tells us about the relative stability of a system. It does not talk about absolute stability. What do I mean by relative stability? I will just tell in a second. So I have two systems here, S1 and S2. Okay, just by looking at these two systems, like these are the pole zero diagrams, okay, of S1 and S2. Can you tell me which one will be more stable, okay, or which system are stable? So if I see both are lying on the left hand side of the S plane, right? That means both have poles on the left hand, like both are left hand poles. That means both systems are stable. But scientists wanted a better measure. They wanted a better thing. Both systems are stable, but which one shall I choose? There has to be some parameter, right? That helps me decide which one shall I choose. So it is that parameter only, the relative stability parameters. Because until now we have been studying about absolute stability, that is like in time domain analysis, whatever you studied before studying the frequency response, right? You discuss about absolute stability. Okay, both are stable, both systems are stable, but which one is better? Which one should you choose? Here S1 is more stable than S2. Why is S1 more stable than S2? In control systems or any system, right, there is some noise, there is some disturbance. Due to the disturbance, let's say I have the pole locations like this, right, S plus P1 into S plus P2. Due to some disturbance, the pole locations will just vary a bit, just a bit, right, due to some noise or something. So if the pole locations vary, that means this, right, S2 will vary a bit. So although the exact pole location is here, but the problem is it will not lie here exactly. It will not lie here exactly. Why? Because in real life systems, it is not ideal. There will be some noise. There will be some, like, I think just for the 5 minutes, right, you heard a noise. What was the noise? The noise was coming from my laptop, the fan, right? My laptop became heated, so that's why I had to turn on the fan of the laptop. Okay, so there is noise, but the mic has a noise cancellation on. It has a noise cancellation on, but still it isn't able to filter out the overall noise of the laptop. So obviously in ideal system there will be some noise. If there is some noise, then there will be some problems. So that's why we, even though there is noise, we want to lie as further away from the j omega axis, because if I am near to the j omega axis and for some reason due to the noise, for a fraction of a second the pole lies on the right hand side, the system will tend towards instability and it will go towards unstable, right? It will, the like response will be unbounded, response will become unbounded. So I exactly don't want that. I don't want my response to be unbounded. Okay, so that is the reason why I want my poles to be on the very further away from the j omega axis. Even though there is some disturbance, still I have very much room left so that I don't cross it. So these, right, this further away from the j omega axis, this, there has to be some criteria, right? There has to be some numerical criteria. This criteria is given by the two properties, that is gain margin and phase margin of a OLTF. That I will come to. Don't worry about that. That I will come to. So that is what is written. Whatever I explained, that is exactly written over here. Okay, nothing new. Okay, so like it is written here numerically. You can go through this. The notes will be there. Numerically, it is written like settle in time. It will settle much slower. Rise time. All those things. Time domain parameters. That's why we want it further away. So when does my CLTF blow up? When does it blow up? Because when the amplitude of the CLTF is infinity, then only like the output sinusoid will also be infinity, right? Because if you remember this thing, that my input sinusoid was something like this, R into sine omega naught t, and output was C into C, and C is what? R into magnitude of t of j omega. So for some reason, if the magnitude goes to infinity, then it will blow up, right? It will blow up. My output will be unbounded. I don't want that, obviously. So when does it happen? When does my output become unbounded? Exactly when this, right, denominator goes to 0 at a particular frequency. When this denominator goes to 0, then my output will become unbounded, and that is exactly what we do. And when does it goes to 0? When does it goes to 0? It goes to 0 at location of the poles of the CLTF. It goes to 0 at the location of the poles at the CLTF. That's why we don't want to put that frequency. Okay, so there are two measures. I will not go to the proof here. Okay, we don't have time, so I will not go to the proof here. I will just directly say what are the two measures. Okay, so one of the measure, there are two conditions, like for this equals to 0, right? 1 plus g of j, h of s, or g of h of j omega equal to 0, has two conditions. So this, right, g of h of j omega has to equals to -1. So this -1 has two things, one is the magnitude, another one is the angle. So magnitude needs to be 1, right? At a particular frequency, magnitude needs to be 1, and if at the same frequency, my phase is also minus, say, 180, then for sure that frequency will be an unstable frequency. I don't want to be near that frequency. Okay, so these two frequencies have name. Most of the cases these two frequencies are not same, and of course if they are same, then of course I can directly say that the system will totally go unbounded, because the magnitude of the transfer function will be infinity. Okay, so what is the name? Name is for this particular frequency, right, where the gain of the OLTF is 1, it is gain crossover frequency. Simple name, gain crossover frequency. And where the phase of the OLTF is -180, it is phase crossover frequency. That's the simple name. Okay, that's the simple name. Okay, so like the name is written over here, all the names. Okay, I'll not explain much here. So the closeliness of the g of j omega to -1 point in the imaginary and the real g of j omega axis can be defined from the polar plot. And from the polar plot, two quantities come which define this closeliness. From in the polar plot, two parameters come which define the closeliness of this -1, that is gain margin and phase margin. How close I am to this -1 point, okay, of this g of j omega, that is defined by the imaginary real part. Because obviously, what does imaginary, like what does the polar plot plot? What does the polar plot plot? Polar plot plots the real of this g of j omega, h of j omega, and the imaginary of this h of g of j omega. So when the real and imaginary cut the -1, 0 point, of course that point will be instability. But even if it doesn't cut, then also I don't want to be lying nearer to the point. I don't want to lie near to that point. Why I don't want to lie near to the point? If I lie near to that point, then again the same problem will happen, right? Due to some disturbance, it can go unstable. So just be careful regarding that. Okay, so yeah, everything is recording, just checking that. Yeah, so I hope you understood the parameters. So can you just pause the video, try it out by yourself, find the gain and phase crossover frequency for this particular OLTF. Very simple, right? First one I will solve. So what is the gain crossover frequency? Gain crossover frequency is the frequency at which the OLTF is magnitude of the OLTF is 1. So g of j omega into h of j omega is 1 by j omega into j omega plus 2. Now if I write the magnitude of g of j omega, right, magnitude of OLTF, I will not write the whole thing. This will be 1 by omega into omega square plus 4 whole under root. Okay, so this will be right. Now I have to equate this equals to 1. So at omega equals to omega g, this will be equals to 1, that is gain crossover frequency. Okay, so in short form they write omega g as well. So this, right, I don't like under root. Okay, I don't like under root, so I have to square both sides. If I square both sides, this will become omega g c whole square, or in short you can write omega g as well, no worries. Okay, so whatever you wish to write, you can write omega g square plus 4 equals to 1. Okay, so it comes out. Now of course this is becoming a fourth order equation. I don't know how to solve fourth order equation. I will convert this into a second order equation. That is why you will see you will not get very high calculation in gain crossover frequency. So I will replace my omega g whole square to be equals to x. So this will be 1 by x into x plus 4 equals to 1. So this now becomes a second order equation. So ultimately this becomes x square plus 4x equals to 1, or my x square plus 4x minus 1 equal to 0. So now I can simply use the Sridhar Acharya formula. So this will be x will be equals to -4 plus minus b square minus 4ac. So that is 4 divided by 2a. So this will be minus 2 plus minus 4 under root 5. Okay, minus 2 plus minus under root 5. So like ultimately when you solve, right, we'll just quickly write the values. Under root 5 will be something 2.2 something, 2.25 or something. So yeah, 2.23. So 1 will come negative. Okay, and I will ignore the negative number. Why? Because my x is equals to what? Omega gc whole square. Omega gc is a real number. Okay, and if I square, I will get another positive number. So obviously it is not possible for me to get negative number, so I will choose the positive one. So it will be 2.23 plus 2, that is not plus 2, sorry, minus 2. So it will be, ultimately it will come out to be 0.236. Okay, this is not your omega g. Okay, the mistake that you make, this x has to be positive, which is 0.236. Now omega g will be what? Under root of this 0.236 whole under root. If I do, this will be 0.488. okay, this will be my omega g. Okay, this is how you solve. Sometimes this simple questions also sometimes get asked, or you have to find out the phase margin. To find out the phase margin, you have to find the gain crossover frequency. That will discuss later on. Now let's solve for the phase crossover frequency. Phase crossover frequency is the frequency at which the OLTF has a 180 degree of phase shift. Okay, so when does it happen? So let me write the phase expression. So here is my OLTF, right? I will just copy this and paste this here. This is my phase expression, correct? So now what I can comment is that, okay, this overall didn't get copied actually. Okay, sorry. Okay, so the phase of this will be what? Due to the pole at the origin, it will be minus 90, and okay, again it got, okay, somehow, sorry about that, it is getting cut out, okay, for some weird reason. Okay, due to the pole at the origin, minus 90 minus tan inverse omega by 2. Okay, this is simply the angle. Now when does it go to minus 180? Will it ever go to minus 180? So at what? At omega equals to omega p, the phase will go to minus 180. And when it happens? It happens at infinity. Because if I equate this with minus 180, then my tan inverse omega p by 2 has to be equals to 90. And when is the tan inverse of any value or 90? It is when the inside value is infinity. So obviously denominator is a finite value, so omega p, non-zero finite value, so omega p has to tend towards infinity, then only the phase, like the phase will become minus 180. So it doesn't have any phase crossover frequency. Okay, does not exist. Omega p does not exist. Okay, so this was basic about phase crossover and gain crossover frequency. Now I will discuss about gain margin. So gain margin is what? Now we have learned about phase crossover frequency, right? Gain margin is the reciprocal of the magnitude of g of j omega at phase crossover frequency. Now you might have a doubt, sir, why is the gain margin discussing about gain, but here the frequency is phase crossover frequency? Why is it not gain crossover frequency? That is the point. That is the main point. What did I tell you? I told you that when this condition is met, then system blows off, right? Blows off, it is unstable. So if one of the condition is met, that at phase crossover frequency, my angle condition is met, minus 180. Now I am checking the magnitude condition. And what is gain margin? Gain margin is the inverse of the gain. So basically, inverse you will not understand, but what I will explain is how far I am from magnitude equals to 1. That is what my gain margin tells me. How far I am. Because phase is set, angle condition is met, but how far I am. If the gain margin is 1, or the reciprocal of magnitude at phase crossover frequency is 1, that means my system will become unstable. Okay, if the gain margin is 1, that means the gain is 1 and the inverse will be 1 at phase crossover frequency. That means both the condition is met, and if both the conditions are met, that means I am at this condition. So that's why the frequencies are different. So gain margin, yes, you are correct, it is discussing about gain, but it is discussing about gain at phase constant frequency, because one of the condition is met at omega p, one of the conditions is met. Now why we are doing the inverse? Basic mathematics, because I want to know how far I am from 1, that's why we are doing the inverse. If you understand this, great. Don't understand, remember the thing, gain margin is inverse, just remember it. Okay, so this is my gain margin. Okay, it is sometimes written like kg or something, don't have to do, these are just notations, don't have to remember anything, just simple gain margin. Remember, it is inverse of the gain of the OLTF at omega p, not at omega g. You will get confused. Now sometimes gain margin is defined in dBs. So I will explain about dBs in Bode plots, okay, just in a bit, just after this lecture. So if you know about Bode plots, or if you don't know about dBs, how to convert anything into dBs, just take the 20 log of that value. If I take the 20 log of this value, actually this is in 1 by something, right? So this power is what? -1. So obviously -1 power comes here, and 20 is already there, 20 log of something into log of the inside thing, whatever it is. Okay, if you understand this, great. Don't understand dB, just remember. Okay, what can I do? I don't have time to explain dB. I will explain dB in the Bode plot lecture, don't worry about it. Okay, so now what is phase margin? Now phase margin is the amount of phase lag that needs to be added to the phase of the system at omega goes to omega g, that is gain crossover frequency. Again the same thing, the gain condition is met. What is the gain condition? Gain condition is the frequency at which the gain is 1, that is omega g. So gain condition is met, but one more condition is still left, right? That is phase condition. Now I will check how far I am from the negative real axis, or how much clockwise movement I need to make. So let's say at omega g, right? At omega g, that is the gain crossover frequency, my phase is something here. Okay, so and my negative y axis, sorry, negative x axis, or -1, 0 point is here. So how much more do I need to rotate this point in the clockwise direction, so that I can reach my -1, 0 point, so that I can reach my -1, 0 point. That is what the phase margin tells. And put a put a comment below if finally this got cleared, because I know many students, they just remember what they do, they just remember this thing. This is my gain margin, रट्टा मार लो, हो गया, रट्टा मार लो ये gain margin होता है, रट्टा मार लो ये phase margin होता है, बस खत्म. What is phase margin? What is the visualization of the phase margin? Why is phase margin and gain margin important? I think like students who have studied control systems from me, they will know, but who have not studied from me, this is new to them. Okay, and I hope I am able to clear the concepts, the like all the broken concepts that you learn, right? All the rotten concepts. Okay, I hope I am able to clear these things, visualize the things. Okay, give you a clarity. What is phase margin? What is gain margin in actual reality? What is gain margin and phase margin? Why are the parameters so important? Okay, so I hope you understood. Just don't make this silly mistake that the phase margin is calculated at a frequency, gain crossover frequency, not at phase crossover frequency. I have seen many students make this mistake. Don't make the mistake. Okay, don't make the same mistake. So yeah, that is about the gain margin, phase margin, all those things. Now what else do I have to say? What else do I have to say? So this is done almost. So yeah, if the OLTF does not have any poles and zeros in the right half plane, both the gain margin and phase margin should be positive to ensure stability of the closed system. So how do I define stability? So basically, right, so although I cannot define like I cannot comment about absolute stability, but generally what happens is, if my if my gain margin is positive, sorry, if my gain margin is yeah, gain margin is like in this is in dBs actually. Let me now comment about the relative stability parameters. So if my gain margin in absolute scale, in decimal scale, it is greater than 1, gain margin is greater than 1. So if gain margin is greater than 1, what does it mean? Gain margin greater than 1 means reciprocal, the gain of the OLTF at that particular, at the phase crossover frequency is less than 1. Okay, is less than 1. Now generally what happens, generally the zeros are not there. Okay, and I have poles only, so that is where the confusion comes. I will explain. So for these type of transfer function, right, for these type of transfer function, I can safely say, what can I safely say? I can safely say if my gain margin is greater than 1, system, gain margin and phase margin both are greater than 1, then system will be always stable for these type of systems. Why? because once I am able to identify that gain margin is greater than 1, okay, let's say gain margin is 2, gain margin is 2, that means gain will be 1 by 2 at phase constant of frequency. So at minus 180, angle minus 180, gain is 0.5. And these type of transfer function, right, if I replace with j omega, if you understand this concept very well, if you don't, just skip this portion, okay. So if I replace with j omega, this will be j omega plus p1. Now if I try to find discuss about the magnitude, so magnitude, right, will only reduce as omega increases, magnitude will only reduce. So for certain omega value, omega equals to 2, let's like just for example, omega equals to 2, that is the phase constant of frequency. At this frequency, the angle is minus 180. At this frequency, the angle is minus 180 and gain is 0.5. Okay. So now if I go to omega equals to 3, angle will reduce, right? Angle will be minus 220, something like that, and magnitude will also reduce. So actually, it will never cut the minus 180, like minus 1,0 point. It will never cut it. It will never cut it for these type of transfer functions. Now, where does the confusion comes? When there is 0, then the confusion comes, right? So that generally we don't discuss about those type of transfer functions, but there can be zeros as well. So then the gain margin and phase margin sometimes is not able to properly say the stability. That's why we say it is a relative stability parameter. It is not an absolute stability parameter. It cannot totally comment about stability of any transfer function. Like Raut can comment about the stability of any transfer function, okay, but this cannot. That's why they are relative stability parameter. That's why there is so much confusion, okay. So and like now I have a numerical number, right? The higher the gain margin, the more further away from the minus 1,0 point, the more further away I am from the minus 1,0 point, the better my system is, the more relatively stable my system is compared to other system. So that's why the gain margin helps in getting a value numerically as well, okay. That is the advantage of a gain margin, okay. So yeah, that is basically it about gain margin and phase margin and visualization. I hope you understood. So yeah, this is the same thing only, like how understanding the phase margin, gain margin graphically, all those things I've explained to you, how much gain I need to make. So if I'm here, right, if can you from the graph can you comment about the gain constant of frequency, phase constant of frequency, gain margin and phase margin? So what is the gain constant of frequency from the polar plot? Gain constant of frequency is the frequency at which the gain is 1. So here I observe how to identify the gain is 1, that is the distance from the origin should be 1. So here I can observe the distance from the origin is 1. Here I can observe the distance from the origin is 1. And here what do we observe? It is cutting the negative x-axis at some point k, and this is my phase constant of frequency. So this will be my omega p and this will be my omega g, okay. So one more interesting point to note here is, so omega g is coming here, okay, and omega p is coming here. What does it mean? My omega p, obviously this is like I'm moving in this direction, so omega is increasing. So omega g will be lower than omega p because let's say omega g is 2. So after 4 I get to omega p. So if my omega g is here, right, if my omega g is here, what important point I can say? I can say that one condition is met, okay, for instability one condition is met, that g of magnitude is 1, but is the phase 1? No. Sorry, is the phase minus 180? No. When will the phase be minus 180? At phase constant of frequency. So still phase constant of frequency will come later. So if my phase constant of frequency is coming later and my omega g is less than omega p, that means I will never cut the minus 1,0 point. I will never cut the minus 1,0 point. Okay. Why I will never cut the minus 1,0 point? Because for these type of transfer function, k upon s into s plus tau, something like this, the magnitude will only reduce. So here the magnitude was 1, here the magnitude will be, although visually it is seeming like magnitude is more than 1, but it is not. Here the magnitude will be 0.9, here the magnitude will be 0.8, here the magnitude will be 0.7. So here, right, the magnitude will never be 1. So obviously I will never cut the minus 1,0 point. So my system will always be stable whenever this condition is met, okay. So this is also a very, very important condition that you must remember. This is important for gate, okay, very, very important. Now what is the other thing? Other thing is, if my if my system is something like this, right, if this gain let's say is 2, something like this. So if this gain is 2, right, still I can cut the minus 1 comma j point. There is a possibility I can cut the minus 1 comma j point, right? So you have to see before this minus 180 degree whether the gain of the transfer function is 1 or not. Just before this minus 180, if the gain of the transfer function, so not the transfer function, sorry, the OLTF is less than 1, of course here it will be somewhat less than 1 only. The magnitude will be less than 1 only. So that means I will never cut the minus 1 comma 0 point. So that is what this condition emphasizes. This condition emphasizes the same thing. That what does it say? Like in words, what does it say? It says before reaching minus 180 degree axis, that is minus negative x axis, before reaching negative x axis, the gain is lower than 1. Why? Because like omega g, like somewhere here gain will be 1, right? Just after this gain will reduce, right? Somewhere gain will reduce, so gain will be just equals or lower than 1. So it proves, it safely says to me that I will never cut the minus 1 comma 0 point. I will never cut the minus 1 comma 0 point. Now what does the problem come? The problem comes if I have a 0, s plus alpha divided by s plus beta, s plus gamma. Now right now actually then everything messes up. Now I cannot directly say whether the magnitude will always reduce or not, because in the numerator is also a function of omega and the denominator also a function of omega. But in the previous case here, right, 1 k upon s plus tau into s, here the numerator is constant, denominator is a function of omega. If the omega increases, the whole magnitude decreases. But in this case the numerator is also a function of omega and the denominator is also a function of omega. Both are function of omega. So I cannot directly comment about the magnitude. So that's why there is so much confusion around gain margin and phase margin. Okay. So generally when we discuss about all these points, right, these points are valid for these kind of transfer functions. Okay. And so that's why I always tell you to go with basics. I always tell you to go with basics, because if you go with this kind of thing, right, you will say for this case also it will be true. Not always. This will not be true for this type of transfer function, this type of OLTF. Okay. So just be careful about that. Now trust me, these type of things, right, no educator will tell you. Nowhere you can search on YouTube, anywhere you can search on YouTube, you will find this particular research nowhere. Okay. I had to develop this. I had to go much deeper into the concept. Why is this not valid? Okay. Why sometimes it is getting satisfied and not getting satisfied due to these kind of things, right? So if you appreciate, then do comment below how you are enjoying the content and how like if you have learned anything new from this whole video. I hope you have taken a lot of new things from this video. Okay. So from the graph, if I want to just comment about the gain margin. Okay. So here, if I want to comment about the gain margin from the graph, here like they have mentioned that this value is k. What is the gain margin? The inverse of the magnitude of the at the phase crossover frequency. So magnitude is k, inverse will be 1 by k. So gain margin will be 1 by k in absolute values. But in decibels, what it will be? This will be 1 by k. In dBs, what it will be? It will be simply minus 20 log of k. Okay, very simple. I hope you understand how to find the gain margin. Okay, inverse of the gain, that's it. So how did this came? Basically what it tells us, this right, let's say I have, what factor I have to multiply so that I make the system unstable. By what factor of gain I need to multiply so that the system will become unstable, because at phase crossover frequency, if the gain is also -1, then system becomes unstable. So this gain margin, right, exactly tells that factor. So now if I want to prove it to you, so at phase crossover frequency, the gain is k. Now if I multiply the gain margin, right, if I multiply it with the gain margin, the magnitude will become 1, gain will become 1. Is it happening? Yes, it is happening, right? So gain margin is 1 by k, so it will become 1. So that is the physical significance of gain margin. So it tells me how much factor I have left still, so that the gain of the frequency doesn't become, the gain of the system doesn't become 1 at phase crossover frequency. How much margin I have. Same goes for phase margin. Phase margin also tells me how much margin I have before it cuts the minus 180 degrees. So it tells me that from minus 180 how far I am, or how much phase lag. So like at gain crossover frequency, the phase is this. How much phase lag? Phase lag means negative angle. How much phase lag I need to add to this so that I can reach minus 180. That is what my phase margin tells me. So phase margin definition comes from here, that is minus 180 plus the plus 180 plus 180 plus the angle of g of j omega g, gain crossover frequency, into h of j omega g. Okay, that is what my phase crossover frequency tells. And gain margin definition also you understood that what is the magnitude of the OLTF at phase crossover frequency is this, right? How much I need to multiply, that is the GM, so that I make it to 1. I bring it to 1. If I am able to bring it to 1, that means system will be unstable. That is what my gain margin tells me, how far I am. So yeah, so like I hope you have understood how you can graphically locate and all those things I've explained. These are just written here, key points. And yeah, so like these are few key points that I have mentioned there, those are only written. Okay, so open loop system, all those things are there. So like if I have a transfer function something like this, right? If I have a transfer function something like this, you cannot, if I have a transfer function something like this, k upon s into s plus s tau plus 1, something like this, then only this method will work. How, what do I mean by this? So then what you do is, efficiently you will be able to comment about gain crossover frequency and phase crossover frequency. How? Basically what it will do, if you have a transfer function something like this, right, there is no numerator, or it is always a decreasing function. What do I mean by decreasing function? That is the phase and gain both always decreases for increasing values of omega. Okay, so you find the gain at omega equal to 0, and you find the gain at you find the phase as well. Okay, so if I find the gain at omega equal to 0, then it will be something like this, it is infinity, and at gain at omega equal to infinity is 0. Okay, now if I find the angle at omega equal to 0, omega equal to 0 angle will be minus 90, and omega equal to infinity will be minus 180. Okay, so I can directly say for these type of transformation, right, I can say there will be some gain crossover frequency. Okay, like sometimes what happens, there isn't any gain crossover frequency. I'll just comment about that just in a second. So here I can see it is a continuous function and my magnitude is always reducing. That means in between this omega, right, somewhere I will lie where my magnitude will be 1, and that point will be the gain crossover frequency. Okay, now let me come to the phase one. So I can observe the phase will always only reduce, phase will only keep on reducing. If the phase keeps on reducing, if the function is continuous, somewhere will I cut minus 180? No, I am cutting minus 180 at omega equals to infinity. That means I don't have a valid phase crossover frequency. If I will take another example, let me make it square. If I make it square, this will be minus 270. Now if I know that somewhere between these omega equal to 0 to infinity, I will get a point where the phase will be minus 180 of the OLTF. So that means phase crossover frequency and gain crossover frequency both exist. So first check whether phase crossover frequency exists or not. Okay, and you can only check for these type of functions when no numerator is present. If numerator is present, then like you have to directly solve as mentioned, right? So this is just a shortcut. Now I will not write the transfer function. Let's say I have a transfer function, let's say I have a gain function something like this, 10 and 2. Okay, at infinity gain is 2 and at like 0 gain is 10, something like this. I have like this, and the phase is also going from plus 90 to minus 90, some transfer function. Now will I have a phase crossover frequency? No. If it is a non-minimum phase system. Now can you comment if my transfer function is like this, there is no numerator, like there is numerator but there is no zeros, only poles if I have, like for these kind of cases, right, if I have only poles, if I have only poles, then you can safely say omega p does not exist. Okay, because if I have only poles, that means my function will always be continuous and it will always be monotonically increasing or decreasing. In this case, it will be monotonically decreasing only. So it will be always decreasing. That means I can safely say omega p does not exist. Omega g exists? No, omega g also does not exist. Now the problem lies when I have zeros. If I have zeros present, if zeros present, right, I cannot comment, can't comment. You have to solve. If zeros are present, you cannot comment by just this table. If poles are present, you directly by just quickly do this table and see if omega p and omega g exist. If they exist, then you continue with your calculation. If they don't exist, then you simply can ignore this step, right? You can save your time. Okay, so that's how you can save the time. That's how you can understand whether omega p and omega g exist or not. So for this type of transformation, right, you can quickly directly comment if omega p and omega g exist. So if you see the gain, like if I just do I have the table? Yes, I have the table here. So the gain for this, right, at omega equal to 0, it will be infinity. At omega equal to infinity, it will be 0. Okay, it will be 0. At omega equals to 0, the phase will be minus 90, and at omega equals to infinity, it will be minus 180. So if I have only poles, right, I can safely comment that yes, I can directly say I don't need to calculate the omega pc, right? Omega pc does not exist, but omega gc, that is the gain crossover frequency, does exist. So I will calculate for that. Okay, so this is the homework. Calculate the omega gc for this. Okay, this is homework. I will not calculate. Okay, I will save the time. I will not calculate. Now for this will omega gc exist? If I write at omega equals to 0, the magnitude is infinity. At omega equals to infinity, magnitude is again 0. So yes, omega gc definitely exists. Will omega pc exist? Omega pc at omega equal to 0, it is minus 90, and at omega equals to infinity, it is minus 270. Okay, minus 270. So it is minus 270. At omega equals to infinity, it is minus 270. So definitely I can comment omega g exists and omega p both exist. Both exist because I have only poles. If I had 0, I cannot comment, but I have only poles, so both omega p and omega g exist. So this is how just in quickly you can understand whether omega p and omega g exist or not. Okay, so yeah, that is basically it. That is basically it about this. You can, like, this is the homework for you. Homework: calculate the omega g here and omega p both for the previous question and this question. Okay, that is homework for you guys. So yeah, so now I will just calculate the omega p actually, because calculating the omega p, right, there are multiple ways in which you can calculate the omega p. I will show you how you can calculate the omega p. So omega g I have already told, simply you just make x equals to omega g square and then solve. Okay, so now how do you calculate the omega p? So you calculate the omega p like this. Any first one is just using the simple thing whatever I have taught you, using the tan inverse formula. So if I use the tan inverse formula, this will be minus 90 minus tan inverse this, right, like I have directly written the what do you say, the angle expression, tan inverse omega p by 4, all this will be omega p, pardon my handwriting, will be equals to minus 180. So ultimately what comes out, this is tan inverse omega p plus tan inverse omega p by 4 equals to 90 degrees. And when it happens, look, I hope you remember tan inverse a plus tan inverse b. So in the denominator of that particular expression comes 1 minus tan a tan b. Okay, I will not explain here. So basically that needs to go to 0. 1 minus tan a tan b needs to go to 0 for this whole expression to go to infinity. If this goes like inside tan inverse, it goes to infinity, then only I will get 90. Okay, I'm not explaining. I hope you know this basic mathematics. Okay, so that means basically 1 minus a into b. 1 minus a into b. A is this and the b is this. This needs to go to 0. Correct? So it will be omega p into omega p by 4, this needs to go to 0. That means my omega p will come out to be 2. It will not be minus 2, although omega p square is 4. If I take the under root, it will be plus minus 2, but obviously I will ignore the negative solution because it is omega p will be positive. Okay, I hope you know basic tan inverse a plus b. Okay, basic thing you know, I will not explain here. Okay, this is not a time to explain tan inverse a plus b, or look it up, look it up. Now how else can you solve it? How else can you solve it? Like there is another way to solve this particular thing. Find the omega p. So what was my initial transformation? Initial transformation was this, right? Initial transformation was this. So if I take this transformation here, if I take this transformation here, so in this transfer function, what do I observe? Like I need the phase to be minus 180, correct? For phase of cos of frequency, I need the phase of the g of j omega to be minus 180, correct? When does the phase become minus 180? When I have only real of g of j omega and imaginary of g of j omega, right, is 0. Imaginary of g of h of j omega has to be 0, because then only the phase will be minus 180. Because if I see I am lying in this negative real axis, that means I am lying on the real axis, that means I don't have any imaginary component of g of j omega. So I will exactly do that. I will simplify this. This will be 20 by j omega into minus omega square plus 5 j omega plus 4. This is equals to 20 divided by okay, this is this will be, so yeah, this will be j omega will go over there, so this will become 4 minus omega square into j omega. So this is the imaginary component and the real component is minus 5 omega square. So what will happen, like obviously the numerator is real, so denominator has to also have only the real quantities for the phase to be minus 180 of g of j omega. So this component has to go to 0. That means 4 minus omega square into omega has to go to 0. So either omega can be equal to 0 or omega has to be equals to 2. It will not be equal to 0. It will not be equal to 0. Why it will not be equal to 0? Because at 0 I can safely say the phase is minus 90, correct? If I, or no, sorry, the phase is okay at 0 also, phase is minus 180. Okay, just hold on. At 0, no, at 0 phase is minus 90, correct? Yeah, at 0 phase is minus 90. Because yeah, this will always contribute minus 90, right? Yeah. So obviously omega to 0, I already know the phase, that is minus 90. So this is also a very good thing to know. Like this, you can solve using these two methods. These are the two methods which you can use to find out the phase cause of frequency. I've taught you. Okay, these are the main things. Now there's a trick. If you want to remember, I don't recommend remembering it. Just like there's a standard result to remember the phase cause of frequency. The phase cause of frequency for these type of functions OLTF comes out to be under root AB. Okay, I don't recommend remembering this. Okay, so like the next method I've like only mentioned just before this, so we don't need to understand this. I've just mentioned that about that method. Okay, so now let's find the relative stability parameters for the following OLTF. So just pause the video and try it out by yourself. Okay, pause the video and try it out by yourself, then I will solve. So let's start with this first OLTF, then I will gradually solve, and obviously at the end I will conclude what does this 3 OLTF means. Okay, what is the importance? So like from question 13, like this is the same OLTF, so I will not waste time on calculating the gain cos of and phase cos of frequency, like it is already there. So gain cos of frequency will be 4.25 radian per second and phase cos of frequency will not exist because I will cut the minus 180 degree phase at infinity. Okay, I hope this is like you can calculate this, even though I have not solved, you can calculate this. Now calculation of phase margin. So phase margin is 180 plus the phase at gain cos of frequency. So gain cos of frequency is 4.25 radians. What is the phase? What is the value of phase? So I have to quickly copy the transfer function. It will be 20 by g of j omega into h of j omega will be 20 by j omega into j omega plus 2. Okay, so this is the OLTF. Now I just have to write the phase expression. So the phase expression will be 180 degree plus not plus, sorry, minus 90 minus tan inverse this omega by 2. Omega g is 4.25, so 4.25 divided by 2, which will almost be equals to like what do you say, almost equals to 45. So I'll just calculate 4.25 divided by 2, 2.25 tan inverse of this, it will be 64 degrees. Okay, no, it is not almost equals to 45, it is like 64.8, right? So 64.8 minus 90 and plus 180. So still I am like my phase margin is positive, still there is some phase lag left for my system to go unstable, 25.2 degrees. Okay, this much amount of phase lag I need to add to my system so that it becomes cuts the critical point, that is minus 1,0 point. Okay, so this is the phase margin, like I've just calculated. Okay, this is written, but phase margin is already calculated, 25.2. Okay, now what about the what about the gain margin? Gain margin is the inverse of the magnitude of the OLTF. So obviously phase margin, phase constant frequency is infinity. Infinity is not a value, it is a feeling. So like if even though gain margin actually does not exist for this particular function, but still if I want to calculate, so magnitude at omega p equals to infinity will be 0, right? So it will be 1 over 0, so it will tend towards infinity. Gain margin will be infinity. Okay, so if you want to write in log as well, it will be infinity dVs. So although gain margin doesn't exist, but sometimes in question they ask the gain margin, okay, for like for this type of systems. Okay, so if the option is there, gain margin does not exist, then you will tick mark that option. If that kind of option is not there, gain margin does not exist, but a option infinity is there, you will take mark the infinity, because sometimes they like define like gain margin does not exist as infinity as well. Okay, that also they can define. Okay, so for the 16 one, now we have to solve this with basics. So this one, if you want to calculate the phase constant frequency, you can quickly solve. Okay, quickly solve. What you can do, you can directly write this, right? I have just simplified this thing, directly write in terms of j omega, imaginary real. So s cube, right? S cube will be what? So I hope this simplification you can do. Okay, then you replace s with j omega. If you replace s with j omega, this will be 10 by j omega whole cube plus 5 j omega whole square plus 4 into j omega. Okay, so now if I simplify this again, this will be 10 divided by minus j omega cube minus 5 omega square plus 4j omega. So ultimately this comes out to be 10 divided by j omega 4 minus omega square minus 5 omega square. So if you quickly want to find out the phase constant frequency, what you will do, as mentioned, right, you will simply just make this 0, because there will not be any imaginary term. So I will make this simply 0. Okay, I will make this simply 0. So this will be 10, like how do I make this 0? This needs to be 0. So this is 0, that means 4 omega obviously is not equal to 0, that explained is already there. Omega will be 2, negative answer I will ignore. Okay, so omega is 2. That is done. Now now the phase constant frequency is there, so I make the imaginary 0 and I get my omega p to be 2. Now what do I need to find out? I need to find out the gain margin. So how do I calculate the gain margin? Just at this phase constant frequency, I just calculate the inverse of the gain. So gain margin, right, is already written over here. It is 1 by gain of this. So gain of this will be now, like for calculating the phase constant frequency, I will use this expression, that is this expression. Okay, for calculating the gain constant frequency, I will use this expression, not gain constant frequency, sorry, for calculating the gain margin. Why? Because finding the gain of this term, if I replace s with j omega, is easier than this one. Okay, but this is also same only, this is also easier only. Like how do you write the gain? It will be imaginary whole square plus real whole square, but we prefer this one. we prefer this one, that's why we will use this one. Okay, so this will be omega into omega square plus 1 whole under root into omega square plus omega square, did it go, omega square plus 4 square, that is 16. Okay, so this is my GM, and there is a shortcut, basically, right? You know phase constant frequency. If you just find out the real portion, you will get the gain, because obviously the imaginary portion is 0, right, at phase constant frequency. So if you just find out the real portion, you will directly find out the gain. I will explain that. Just before that, we will solve with the basic technique. So omega p is 2, so it will be 2 into 5 into 20. So under root 100, it will be 1 by it will be under root 10, so it will be 1 by 20. So I have to find out the inverse of this, right? This is the gain, this is actually the gain, but I have to find out the inverse. So let minus 1 raised to power minus 1 raised to power minus 1. So gain margin comes out to be 20 in actual scale. In decimal, sorry, in dBs, it will be 20 log of 20, whatever this value is. Okay, 20 log of 20, from what I remember, log of 20 is, okay, this 20 log of 20, right? Yeah, 20 log of 20 will be 26 dBs. Okay, will be 26 dBs. So your value comes out to be 26 dBs. Now if I want to solve using a shortcut, how do I solve using a shortcut? So what you do is that here you are equating the imaginary part. So what will be the real part? Real part will actually be the magnitude of g of j omega at phase constant frequency. Why? Because obviously the imaginary part is gone, so only the real part is left. So if I just take the magnitude of the real part, the absolute value of the real part, that will be the magnitude of the OLTF at that particular frequency. So this magnitude of g of j omega p into h of j omega p, sorry for the disturbance, actually this will be equals to, sorry for the disturbance, this will be real of real part of this, right? Real part of the absolute value of the real part of omega p into h of j omega p. Okay, so what is the real part? Basically the imaginary part is gone, right? So only this part is left, that is 10 upon omega square, 10 upon 5 omega square, and I am ignoring the negative sign because I am only discussing about the absolute value, because magnitude is absolute value. Yeah, sorry for the interruption, actually like few bit of background noise was coming. Also one thing I missed here, this GM, right, is 10 upon this, right? Because sorry, this is 1 upon magnitude, and magnitude was actually 10 upon this. I forgot to write the 10, so this will be 10. So ultimately this comes out to be 2, and if I do 20 log of 2, it will almost be equals to 6 dBs. Okay, this is like log 2 is 6 dB. This is a relation that I tell students to remember. I will explain this in Bode Plot. This is a very good relation. Okay, so same thing I will get here as well. So it will be 10 by 5 omega square, the magnitude. So it will be 10 by 5 into 2 square, that is what do you say, that is 10 upon sorry 5, this is gone, so 5 is gone, so 10 is gone, 1 by 2. So ultimately your gain margin will be inverse of this, that is 2. So like this is just a neat trick, shortcut to remember this thing. If you want to like do it like this, you can also do. Okay, without even calculating omega p, I can directly come to this step. I don't need to calculate omega p, right? Yes, sorry, I need to let me reiterate. Yes, I need to calculate the omega p, because omega is here present in the real part, but I don't need to calculate the whole gain. I don't need to waste my time. Without wasting my time, I can directly come to this GM value. But this only works if the numerator, right, is completely real. If the numerator is not real, then things will become difficult. So I will recommend you to go with basics. If the numerator is real, if the numerator is not real, then you can follow this method. Okay, this will always work 100% of the times. So let us calculate the GM. Let us calculate the gain, crossover frequency, and phase margin. So generally, right, gain, crossover frequency is a bit difficult to calculate. You will see for higher order systems. So the gain expression is this. I have to equate this with 1, If I equate this with 1, then again this will become like I have to square both sides. If I square both sides, ultimately, right, it will come out to be 100 divided by omega square into omega square plus 1 into omega square plus 16. Okay, this is equals to 1. This is what I get, right? So now if I, like, obviously this is like a sixth order equation. I don't solve sixth order equation. I have to lower it down. Okay, so what I will do, I will replace x with omega square. Okay, this is all omega g, so omega g square. So now my equation becomes 100 equals to x into x plus 1 into x plus 16. Okay, so now if I simplify this further, this will become x square plus 17x plus 16. Okay, and you might have a doubt, sir, will I be able to find the solution of this? No, without like a scientific calculator you will not be able to find a solution. So you don't have to worry about this question will not come in gate for like sixth order equation, right? This question will not come in gate. So they will never ask you to find the gain crossover frequency. Only in this type of equations they will only ask you to find the gain crossover frequency in the cases where the roots are very simple. Okay, so whenever you get a cubic equation, right, and if it is coming in the examination, you might have this doubt in the mind, how will I solve a cubic equation? Because cubic equation you will be able to solve without a scientific calculator. Just remember, if the examiner has given a cubic equation and that doesn't involve any scientific calculator, that means the roots will be really simple. Either x equal to minus 1, minus plus 1, plus minus 1, 0, plus minus 2, and plus minus 3. Just go with the hit and trial method and check this, and you will be able to find your roots. But in this case, obviously this is not examination, so I frame the question. So if I frame the question, that means the roots are like not simple. So I have calculated, I have the scientific calculator. So two solutions will come negative, which I will ignore, and one solution will come positive, that is x equal to 1.915, that I will take. I will ignore the negative solution. So ultimately my x value, right, ultimately my omega g will be under root of this. If I take the under root of this 1.915 whole under root, this will be 1.3838. okay, this will be my gain crossover frequency. Okay, this will be my gain crossover frequency. Now I have to calculate the phase margin. Phase margin is just a definition, so I will go according to the definition. So 1 plus angle, so angle, like the transfer function is this is the transfer function, right? I think the angle I have somewhere written. Okay, nowhere I have written. Okay, so this is right. Now, right, for calculating the angle as well, I will take this expression, not the other one. Okay, just be careful. So it is 10 by s into s plus 1 divided by s plus 4. So ultimately the angle will be minus 90 minus s plus 1, that is tan inverse omega by 1 minus okay. So what is omega? Omega is 1.3838, so I will just calculate that values. So this is 54 degrees. Okay, 54.14, and this is 10 inverse of this, so this will be minus 19.08, and minus 90 is already there. Okay, 180 plus this, so this minus 54.14 minus 90 and plus 180. Okay, so this will be 1677. Okay, 0.7. This is the phase margin. So still I have bit of margin left for my OLTF to touch the minus 180 degree. So this is the phase margin. So like this you can solve the other two as well. Of course I'm running out of bit of time, so I will just try to solve this bit quickly. So like here, right, what you can do, again you can write this as 20 by j omega plus 1 j omega plus 4. Okay, so this will be 20 if I want to calculate the magnitude, right? So if I want to write the gain crossover frequency, so the gain crossover frequency, if I want to find out, I have to equate this with 1. Okay, sorry, I want to first I want to find out the phase crossover frequency. So phase crossover frequency will be very simple. This will be 20. Phase crossover frequency, right, will not change. Phase crossover frequency will be simply the same, right, because the denominator has not changed. The new, if you notice, only the numerator has changed. Okay, so if only the numerator has changed, the omega pc, right, will not change. Okay, omega pc will remain same, that is 2. Okay, omega pc will not change. And what about the gain margin? Gain margin will change. Why? Although the denominator has not changed, but the numerator has changed. Numerator has increased to 20. Previously it was 10. If you remember, go back to the slides, it was 10. So it is increased by twice. So what will happen? Gain margin will be halved. Gain margin will be halved because numerator has increased by twice. So gain margin will be halved. So previously, what was the gain margin? Gain margin previously was what I remember. Gain margin previously was 6, right? No, 6. Sorry, gain margin previously was 2. Now gain margin will be 1. You can calculate. I don't have time, so I'm just skipping it. In dBs it will be 0 dB. In dBs it will be 0 dB. Okay, so this is the gain margin. What about the calculation for the phase margin? So again, this time, right, the gain crossover frequency will change because the gain crossover frequency takes into account the numerator and denominator magnitude. So gain crossover frequency will change. Okay, so I have just written the gain crossover frequency. Okay, so that you don't have to calculate. We won't waste the time by calculating the gain crossover frequency. So the gain crossover frequency here, right, comes out to be, like I have just written it on my side, omega g comes out to be 2 radian per second. Okay, if you solve it, like you don't have to solve because you will not be able to solve because it is a higher order equation, but if you solve it, you will get it 2 radian per second. Okay, so at 2 radian per second, but the phase equation does not change. The phase equation remains same because it does not take into account the numerator, because numerator is just real quantity, it is not a imaginary complex quantity, so it does not take into account, but the expression is same, but the omega g has changed. That's why the phase margin also will change. So what is the phase margin now? Phase margin now is 180, like I've already written it here, I think, yeah, 180 plus g of j omega. 180, if you remember, it was minus 90 minus tan inverse omega by 1 minus tan inverse omega by 4. Okay, and omega is 2 right now. So ultimately this and this together provide a minus 90 degree phase shift, because this is 2 and this is 1 by 2. So if one is inverse of the other, then overall tan inverse is minus 90. This I have taught in my full course, a shortcut, but I will not, obviously I don't have time, so I will not explain this thoroughly. So minus 90 and minus 90. Okay, and 180 is added here. So what do I observe? I observe that my phase margin, right, phase margin is also 0 degrees. Surprisingly, phase margin is also 0 degrees. Why? If you notice one thing, my omega g and omega p both are equal, and if my omega g and omega p both are equal, that means what? That means that my OLTF is cutting the critical point. Denominator is going 0, it is blowing up. So this signifies what? This signifies I don't have any margin left. That means my system is unstable. No margin left, system is unstable. That's why I have taken the example. Next example is just, now the gain has increased even further, 30. Gain has increased even further. So the gain has increased even further. What will happen? Again, if I calculate the g of j omega and h of j omega. Okay, so like as like first I will calculate the phase crossover frequency. Phase crossover frequency won't change. Phase crossover frequency will be same again, as it only depends on the denominator, because I have only the numerator is totally real. So phase crossover frequency will be again 2. Okay, I'm not calculating it, I'm skipping it because we don't have time. We have to solve a lot of things. Okay, so phase crossover frequency will be 2. Now what is the gain margin? Gain margin, right? As it has increased thrice, the numerator has increased thrice, so gain margin will be also decreased thrice, right? It will be decreased by thrice. So previously in the first case the gain margin was 2. Now the gain margin will be what? Now the gain margin will be simply, gain margin will be 2 by 3, okay, decreased thrice, like divide by 3, because the gain has increased by 3. So as gain margin is inverse of gain of OLTF, that's why I'm not explaining. I hope you can do all this. So GM is 2 by 3 now. It is 0.67. In dBs, what is it? It is, in dBs, if I want to calculate, right, 0.67 log into 20. In dBs, it is minus 3.48. Okay, dBs. Minus 3.48 dBs. Now, this is minus 3.48 dBs. Okay. So, omega p is this. What about the phase? What about the gain crossover frequency? Again, gain crossover frequency we won't be able to calculate because it is a higher order equation. But ultimately, if you calculate, right, your gain crossover frequency omega g will come out to be, I have already calculated it beside me. It is 2.44 radian per second. Gain crossover frequency is 2.44 radian per second. Okay, so if you calculate the phase margin, right, for this same expression, if you calculate the phase margin, again the expression won't change. It will be again tan inverse, like minus 90 is here, minus tan inverse omega minus tan inverse omega by 4. Now if I calculate this, right, if I calculate this, so it will be 2.44 divided by 4 tan inverse plus 2.44 tan inverse. So this is minus 99 and minus 90, 99, 189, something like that. It is minus 189. Okay, 180 also I have to add, sorry. If I add 180, it will be like minus 9 point something, minus 9 point some value, okay, minus 9 degrees. So phase margin is negative, phase margin of negative. So it has already crossed, it has already crossed the critical point, like already crossed the minus 1, like already crossed the negative real axis. Now it has already crossed the negative real axis. So in this, right, it can be unstable. It can be unstable. Why it can be unstable? Because like first what is happening in the first case, my critical point was here and I was never crossing the minus 1 0 point because I had enough margin left, because my gain was somewhere here 1, and then it will never reach the minus 1 0 point. Now what is happening is that in the second case, what happens, I exactly cut the minus 1 0 point. I exactly cut the minus 1 0 point. If I exactly cut the minus 1 0 point, what will happen is that my system will become oscillatory. Why? Because the response will also be like will also have those terms, right, as explained in the first portion of this lecture. As it is crossing minus 1 0 point, response will have those terms, that is t raised to power m, something like that. It will be something oscillator margin stable. Now in the last case, it is crossing something like this, right? The gain, I am somewhere here. So what is happening is that if you observe one thing, my gain crossover frequency in the last case omega g is happening after omega p. So what does it textually, what does it mean? Textually it means that I am reaching minus 180 point before I reach gain of 1. Okay, that is what it means. Now there can be a possible case where I can cut the minus 1 0 point, right? There can be a possible case. Okay, so whenever these type of condition happens, right, omega g is greater than omega p, then we call our system to be unstable. Although these are all relative stability parameters, we cannot totally comment about stability. But like for this, I can definitely say that if my gain margin is greater than, sorry, if my gain margin and my phase margin both are positive in dBs, that is, and in degrees, then I can definitely comment about stability. But here, right, my system can be stable. My system can be stable in this case as well. But relatively it will be more unstable than this one. That's why we call it unstable. Okay, relatively it will be unstable. This one will be stable no matter what, but this will be relatively unstable. This can be stable as well. This can be stable as well. But relatively this is more unstable, that's why we call it unstable. Complete instability I cannot comment. For that I need to find out the poles of the CLTF. How do you find out the poles of the CLTF? So simple route you can do, right? And check the instability. You can, like, what you do, homework is check the route and check the instability for all of these OLTFs. From OLTFs I hope you know how to go to CLTF. 1 plus g of s, 1 plus g of h of s, simple, equal to 0. Okay, that you can do. So that is how you go to route, and this is the most important slide for the gain margin, phase margin, and for gate. Okay, so you have to know a few things, that what is omega GC, what is omega PC, what is gain margin, what is phase margin, and how can I comment about the relative. These are all commenting about the relative stability. They don't comment about the absolute stability, they only comment about the relative stability. Okay, why we call it marginally stable? Because this is just on the edge of instability, relative instability, right? Before, after this it goes to 0, it goes to like unstable region. That's why we call it marginally stable. Okay, so yeah, I hope you have understood this point, and remember all these points are only valid for a negative feedback system. Whatever I have derived, only derived for a negative feedback system. So like the same thing what I have written there is written here. If the polar plot of the OLTF crosses negative real axis before the critical point, then it is stable, because then the polar plot will never cut the -1,0 point. But what type of transfer function? For those type of transfer function which doesn't have any numerator as a function of s, only have denominator, some constant k and denominator, then absolutely yes, it will never cut the critical point. If the polar plot crosses the negative real axis, then it is called a marginally stable system, because just before and after this it is just cutting the critical point, right? Just cutting the critical point. That's why we call it marginally stable. And if the polar plot crosses the negative real axis after the critical point, what does it mean? So critical point is here, polar plot is cutting the real axis after this, right? Real axis after this. So then we call it as unstable. Then we call it as marginally unstable, because this is on the left. This is on the left of the critical point. That's why we call it unstable. You can calculate the like route parameters, like stability parameters, all those things. You will find the values. Okay. So these are the key points you have to remember. Of course, I know you might feel like, sir, why are you not deriving this? We don't have time right now. Unfortunately, we don't have time. We have to study exam oriented. So I will teach you exam oriented right now. Okay. So these are the things that you need to occur, and like here only same thing I have mentioned here also. Like previously also I have tried to mention, if my gain crossover frequency is less than phase crossover frequency, that is gain crossover frequency happens earlier than phase crossover frequency, definitely it will be relatively stable. If my phase crossover frequency occurs earlier than gain crossover frequency, it will be relatively unstable. If the phase crossover frequency is equals to the gain crossover frequency, it will be relatively marginally stable. All these are talking about relative stability. Nothing is commenting about absolute stability. Okay, so like this is the diagram of a polar plot of a relatively stable system. The unit circle is there. Okay, it cuts the unit circle here. That means it has not reached the critical point yet, and still it is cutting here. That means gain crossover frequency is less than phase crossover frequency. That means I am safe, I am relatively stable. Again, it is cutting exactly at -1,0 point. That means I am not safe, and it is cutting at like it is reaching the critical point here. Omega BC is earlier than omega GC. That means my system can be relatively unstable. My system is more relatively unstable. Okay, so yeah, so these are things that you have to understand. This is only valid for those type of OLTF whose OLTF is already on the left hand side, LHS. Okay, all the poles of the OLTF are on the LHS. If the poles of the OLTF are on the RHS, then this is not valid. This is only valid for those non-minimum type phase systems. And also these are all relative stability parameters. We are not discussing about absolute stability parameters here. Just few things you have to keep in mind. And also one more thing, sometimes there is ambiguity. Whenever you get multiple gain crossover frequency or phase crossover frequency, then you cannot comment about stability. You cannot comment about stability. Okay, so there are few cases. Then you have to go with route. You simply have to go with route, Hurwitz criteria. Okay, so these are few questions this I want to give you as homework. Draw the polar plot of the following voltage and also calculate the gain crossover frequency and phase crossover frequency. You can see, like, I will solve a few. You can see now I have zeros. Whenever 0 is introduced, right, then it is not that easy to draw the polar plot. So now we will draw the polar plot with zeros getting involved. So I will draw for the first two, and for the other two I will give you as homework. Okay, so this one, right, I think, yeah, this one I have already, like, this is already drawn. I will just explain here because obviously we don't have time. So what you do for the 19th one, what you do is you first write the pole 0 diagram. This is like, I have two poles at the origin, one pole at the -1, one pole at 1 0 at -3 and 1 0 at -4. So what is happening, first I am reaching two poles, then I am reaching one pole, then I am reaching 0, and then I am reaching 4. So whichever point omega will be closer to, that particular pole or 0 will be dominant. What do I mean? Let's say I am at omega equal to 0, then which poles or 0 are nearer to omega equal to 0? These two poles. So the angle contributed due to these two poles will be the highest. I can ignore, roughly I can ignore the other poles. Roughly, I will explain. Okay, once I will go into the slides, I will explain. Here, if I am here, right, if I am near this omega equals to -1, so this angle contribution I will already consider. This have been already considered. -180 I will already consider, but I will not consider these angles. I will not consider these zeros. I will only consider the angle contributed due to this -1 and due to these two poles. Okay, once I am here, I will consider, of course, these are already taken care. I have to consider these three poles as well, and also I have to take care these 0 as well. I can ignore this 0 if it is very far away. If it is very far away, I can ignore. Okay, once I will come to the angle calculation, I will explain. Okay, so like if I see the magnitude, right, magnitude is this simple thing. And can you comment whether this magnitude will be decreasing or increasing? So here, like, the highest power is what? Highest power, if I take omega square common, this will be omega raised to power 4. Outside I will come omega square. Okay, and here if I take omega square common, outside it will be omega. So denominator has the highest power. So at infinity, it will go towards 0. The gain will go to 0. But in between, right, I cannot comment that simply. I cannot comment that simply in between what will happen to the magnitude. At omega equal to 0, I can comment definitely 9 into 4 divided by 1 under root. Then this is basically blowing up. So at omega equal to 0, the gain will be infinity. At omega equal to infinity, I can safely say the gain will be 0. Okay, because like this omega square term is dominating. But in between omega equal to 0 to infinity, I cannot exactly comment about the gain. It is very difficult for me to find out the gain here. Okay, so I'll just take help of the phase and then I will plot the polar plot. So like, I'm not expecting GATE to ask this question, but when a difficult question paper will be set, right, they can ask this type of question. So here the angle, right, if I write the overall angle expression, this is the g of j omega. If I write the overall angle expression, this will come actually okay, this, right, actually this is written -180. Okay, -180 is due to this minus sign. Okay, -180 due to this minus sign. -180 I will get. Then I have two zeros. So zeros will obviously contribute positive angle. So tan inverse omega by 3 plus tan inverse omega by 4. Then I have a, like this one, right, tan inverse omega by 1 minus tan inverse omega 1. This is the pole. This is the pole. This is the pole. Okay, and these are the zeros. These are the zeros, and this is the negative sign. Negative sign contributes a -180 degree, right? Now just take few examples. When I will calculate the phase at omega is to 0.1, then what will happen? This will be 0.1 divided by 3, this will be 0.1 divided by 4, almost negligible. This will be almost 0. So I can ignore these two. Only this is getting into effect and this -180. So what are the values? This is the pole and this is the pole at origin. So what I explained that when I'm near here, right, whichever pole or 0 are nearer, those will be dominant, other I can ignore. So this distance is very large. So here near -1 is present and these two poles are present at origin. So the effect of phase will be dominant due to these two things. So what will happen? This will dominate, this will dominate, and this will dominate. This I can ignore. So value will roughly come almost equals to -180. This, right, I can roughly write, if I have written it, next slide. Yeah, value will roughly come. Value here, right, will roughly come as minus 180 minus tan inverse omega. So for lower values of omega, my phase got reduced to this value. Okay, for lower values of omega. For higher values of omega, what I observe, for higher values of omega, right, these are nearer and these are gone. So for higher values of omega, the effect of this will be what? So if my omega is very high, this will contribute to what? Tan inverse 5, tan inverse 7, tan inverse 10. You see, it is almost equal to 90. So this will contribute almost equal to 90. This will contribute to 180, no matter what. And for higher values of omega, right, these two will be equal. These two, tan inverse, okay, sorry, one mistake I made. So for higher values of omega, all these, right, will almost be similar, all the values. You want to check, just check. Put omega equals to 500. You will see you are getting all, this is almost equivalent to 90, this is almost equivalent to 90, this is also almost equivalent to 90. Just put omega equals to 500, you will see both are this almost equal. So what will happen? This will cancel out, and ultimately my expression comes out to be minus 180 tan inverse omega by 4. It will be, yeah. Why omega by 4? Because these two will be almost equivalent, so these two will cancel and this will be remaining. Why? Because if I just calculate here, right, if I am somewhere here, which 0 or pole is nearest? This one. So the effect of this will be still left. The effect of these two, this will contribute minus 90, this will contribute plus 90, this will contribute minus 90, will be cancelled out. But as I am nearer to this one more, so this one will be still left. Okay, I will take into consideration this one. So it will be tan inverse omega by 4. So just a rough estimation of the transfer function. So like you can see, like if you put actual values, right, then also you can see sometimes the phase is reducing, sometimes the phase is increasing. So it is not like the previous cases where my numerator was constant. If my numerator is constant, then things become very, very easy. If my numerator is not constant, then things become very, very difficult. Just be careful about that. Okay, so this is the polar plot. You have to go with this lengthy method only. Just check the variations, then put the values and then solve. Or what you can do quickly, is you find out omega equal to 0. Omega equal to 0 is the point where magnitude is infinity, so I will be either here or here, somewhere outside. And what is the phase? Phase was minus 180, so I have to lie somewhere around here. Phase was minus 180. At infinity, what is happening? At infinity, phase is, if you remember, phase is minus 90 and magnitude is 0. So I will come back to origin about this, like this, right? I will come back to origin, minus 90 and origin. Now in between, what will happen? Initially I am encountering poles. Initially, as my omega is increasing, I am encountering a pole. So the effect of pole will be higher. And what does a pole do to the angle of a OLTF? Pole reduces the angle. It gives a negative angle, right? So I will go more in the clockwise direction due to the pole. Initially, effect of pole will be dominant for lower values of omega. Now next, as my omega increases, the effect of pole has been reduced. What is dominating? Just 1 0 is left, right? If you remember, for higher values of omega, this was the expression. So what will happen? Now initially my angle was reducing. Now due to the 0, the angle will increase. As my angle is already negative, it will go towards the like angle will increase. So basically the negative angle will reduce. So it will again cross the minus 1, like this negative real axis, and then ultimately it has to reach to minus 90, right? So ultimately it has to cross this point because it has to go to minus 90, because this is something less than minus 180 and this is minus 90. So obviously it has to cross this minus 180 point. It is a continuous function. So later stages, the effect of 0 is dominant. So from the actual calculation, you can cross verify whatever I have told you. The method is same as this. Okay. So instead of calculating, you can roughly estimate what will be the behavior of the polar plot. So basically, right, this is how you solve where numerator is not constant. It is a function of s. Okay. So next one also I will give you homework. Just pause the video and try it out by yourself. Same thing, similar analysis, everything is same only, nothing is different. Okay. Same analysis. I will not do it for you. You have to do it by yourself. Okay. Then only you will understand the concept better. If I explain everything, you'll not understand the concept, okay? But you have to understand the concept. So now what will come to this one, okay? With some different things, with polar plot for exponentials. How can you plot the polar plot exponentials? So pause the video and try to plot the polar plot for exponentials. So first of all, whenever you have to find the stability for any of these type of OLTF, right, just simply use root locus or orthogonals. How will you use root locus? So directly, right, you can comment about stability. What do you do? You have to do some approximation. So for lower values of s, what happens is my e raised to power minus s becomes almost 1 minus s, okay? Then you can solve this using root locus, but you have to identify you're only commenting about lower where s is very less than 1. S is very less than 1. Okay, if s is greater than 1, then this approximation will not work, and then you will not be able to solve. You will not be able to solve. Okay, but polar plot, right? Not stability, but if you want to just plot the polar plot, how will you plot the polar plot? So you replace same thing, right? You replace s with j omega. So this will be 2 e raised to power minus 2 j omega. I will write down the phase and magnitude. So magnitude will be 2 only, because any value, right, minus e raised to power jx, the magnitude of this is simply 1, correct? Because 2 is there, so 2 will come outside. Now what about the phase? This is the magnitude of j omega. H is there, I am not writing it. And phase of j omega. Phase of j omega, right? It will come out to be minus 2 omega. Okay, I hope you know how to calculate the phase of exponential of a complex exponential. Just one thing you have to keep in mind, that this is in radians, this is not in degrees. This only you have to keep in mind, okay? Or even you can convert this in cos omega j omega, that like that you can do, okay? So I'm not proving it. So like here I have converted it into a sinusoid, then I have written the values, okay? So phase is always at omega equal to 0, phase is 0, then it is always going towards negative. So phase is basically I'm moving towards the clockwise direction. And what about the magnitude? Magnitude is constant. Magnitude is 2. So it will just be a circle. It will just be a circle, correct? Because actually the direction is, yeah, it will be like this. The direction will be like this. It will not be like in the anti-clockwise direction. Direction will be like this, right? Because phase is always reducing, and I am moving in the clockwise direction. So I will always move in the clockwise direction like a circle, and the radius of the circle will be 2. That's it. Magnitude is constant, phase is just changing, so I will just rotate. I will just keep on rotating. Now the next one, this one, right? For these kind of cases, if you remember, the magnitude of the numerator, what is the magnitude of the numerator? It is simply 1, right? Magnitude of the numerator is 1. Magnitude of this is omega into omega square by plus 4. So magnitude is a decreasing function. What about the phase? Phase contributed by this j omega will be minus 90. Phase contributed by this e raised to power minus j omega will be minus omega only. This is in radians. This is in radians, okay? You can obviously convert it in degrees, no worries. Then the phase contributed by this j omega plus 2 will be omega by 2, 10 inverse omega by 2, okay? So here, right, angle also is always decreasing again I will rotate in the clockwise direction, but what will be different? The magnitude will also reduce. So I will rotate in the clockwise direction. Okay, this is something I've done this wrong, because okay, I will start from here, because at omega equals to 0, what is the magnitude? Omega equal to 0, in this case magnitude is infinity. Previously it was constant 2, okay? So omega equal to 0, magnitude is infinity, so I will start somewhere from here. And at omega equal to 0, what phase I am getting? If I put here omega equal to 0, my phase will be minus 90. So at omega equal to 0, my phase will be minus 90 and my magnitude will be infinity. So I start somewhere from here. Then my phase will just keep on reducing. Phase will just keep on reducing. So phase keeps on reducing, so I will go in the clockwise direction. And magnitude also keeps on reducing. So magnitude is also reducing. It will be just like a spiral. Just like a spiral. Okay, so magnitude will also keep on reducing, and my phase, I will move in the clockwise direction. Okay, so this is basically for exponential, polar plot of exponential. This was one topic. Now next topic is the gain phase plot. Okay, so like gain phase plot, actually what it does is it also combines the gain and phase together, but the phase is in the x-axis and the gain is in the y-axis. Okay, because previously we were plotting the real and imaginary part of the OLTF, but now like this is also like a separate topic. In ESC this gets asked, but in GATE also sometimes they can ask this type of question, gain phase plot. So where the phase, like if I rotate, I'm rotating from not rotating, I'm moving from omega equal to 0 to omega equal to infinity. So let's say for any type of transfer function, right, where let's say the like the transfer function is exactly the previous transfer function only, that is this, but numerator is constant. So numerator is some k divided by s into s plus 2, something like this. So what will happen or s plus 2 into s plus 1. So what will happen is at omega equal to 0, what will happen, I will get a phase of minus 90, which is here, and gain will be infinity, so I will be somewhere here. Now as omega increases, so phase also reduces from minus 90, it also goes towards minus 270 at the end, and gain also goes towards what do you say that, gain also goes towards the minus, sorry, gain also goes towards the 0, because as omega increases, because numerator is constant, denominator is there, so gain also goes towards 0. So I will go towards minus infinity, because log of 0 is in minus infinity in dBs. I'm commenting in dBs, so that's why it will be like this. So just you should know how to plot the gain phase plot and how to find out the gain margin and phase margin from gain phase plot. So gain margin, how you can find, just first you find out the omega g and omega p. What is omega g? Omega g is the point at which the gain of the LTF is 1. So I will just extend this 0 dB line. If I extend this 0 dB line, I will check where it is cutting. It is cutting here. So this point will be my omega g. This point will be omega g. Now I will extend this line in the phase plot. If I extend this line in the phase plot, this is exactly not accurate, drawing is not accurate. Now from here directly I can see what is the phase, and from here directly I can calculate the phase margin. How I can calculate the phase margin? I will extend the minus 180 degree and check how much more negative angle I need to add to get to minus 180. So that's why this gain phase plot is helpful, because directly from the gain phase plot I can directly comment about the phase margin and gain margin. So my omega g is here, so and my minus 180 degree line is here. So how far am I from the minus 180 degree line, that I can directly see and directly say that it is a positive phase margin, so system will be stable. Also I can comment about the gain margin as well. So gain margin is what, calculate the point at which it is cutting the minus 180 degrees. So this is my omega p, and then obviously this 0 dB line is already extended, so this is some negative dB, right, negative gain. So gain margin will be how much gain in degrees I need to add to reach to 1. So I have some positive GM, right, I have some positive GM, so I have to add some gain margin so that I can reach to this 0 dB line. So that's why this is positive GM, that's why this is positive, and directly I can directly see this is the gap, this is the gap. Now if my graph, let's say, was something like this, okay, then the phase margin is positive but the gain margin is negative, okay. So you can directly visualize if my graph is something like this. So if my graph is something like this, okay, just hold on, if my graph is something like this, right, so here, actually no, previous question also is wrong, like this is positive gain margin only, but if I am here, so if I'm here, right, so where does it cut the, like if I want to comment out phase, I am here, the omega g is here, right, so phase margin, I'm sorry, previously I messed up, I think phase margin here will be negative, because the angle here is something minus 190, minus 200, something like that, and I have to add a positive angle so that I can reach minus 180. That means I'm not adding phase lag, I'm adding phase lead. That means phase margin is negative. What about gain margin? Gain margin, you can see that where is it cutting minus 180? Minus 180 is cutting here. So again, I had to subtract some gain in dBs to reach to 0 dB line. That means again gain margin is also negative. So like this you can identify the gain margin and phase margin from the gain phase plot. So this is also very interesting thing to note. Like I have shown you 3 cases where it is exactly cutting, here the phase margin and gain margin is 0, and where like it is not cutting, like basically it is on the left hand side. So I have some negative phase margin and negative gain margin. I've already explained in one graph only, so I hope I don't need to explain it again. So there is a question. From the gain phase plot of the linear control system, can you comment about the stability of the system? Can you comment about the stability of the system? So here, right, can you comment what is the phase margin and gain margin of this? So if I see that 0 dB line is here, right? So I'm cutting the gain phase plot 0 dB here. So I have to again subtract some angle. So phase margin is positive, positive phase margin. What about the gain margin? 0. The gain margin is where, like, if I extend this line, okay, I'm cutting here. So again I have to add some gain margin. If I add some gain margin, again this will be 0 dB. This will be 0 dB. So if I add some gain margin, I get I am adding some positive gain margin. So of course, if I am adding some positive gain margin, this will be 0 dB. So it is happening, right? It is correct. So both are positive. So system is stable. System is stable because both gain margin and phase margin are positive. System is stable. Okay. Directly you can solve. Now another thing is there for exponential. Comparing the gain margin, phase margin between normal OLTF and if a exponential is multiplied with the OLTF, what will happen? Now you might have this doubt that gain margin is the inverse of the gain of OLTF, right? Gain margin is the inverse of the gain of OLTF. So as the gain of this, right, will be simply magnitude of j omega for the first one, h of j omega, and the gain of next one will be e raised to power minus j omega, which again the magnitude of that is 1 only, g of j omega, h of j omega. So gain of this will be 1 only, so it will be g of j omega into h of j omega, magnitude of g of j omega and h of j omega. You might feel that gain margin will be same in both cases. No, gain margin will change. Why? Because omega g will change. As omega g will change. Why omega g will change? Because this exponential will contribute some phase, extra phase lag. So that's why the phase crossover frequency will change. Gain margin will not remain same. Okay. So in case 1, without time delay, let us take an example. These type of questions I have solved in PYQs as well. Okay. Let me take a short example. S into s plus 1 into s plus 2. Okay. So I have written down the examples and all those things. If you calculate the phase crossover frequency for this case, right, will come out to be 6. Okay. You can directly no, phase crossover frequency will be what? Sorry, it will be under root 2, right? The shortcut is there. So under root AB. So under root 2 is 1.414. Phase crossover frequency will be this. And what will be the gain margin? Gain margin for this particular case, gain margin will be, if I calculate the magnitude, it will be 2 into 3 into 4 plus 2, that is 6 whole under root, correct? So 3 into 3 into 2, so it is 2 under root 2 into 3, so it is 6 under root 2, 6 under root 2. Okay, so 6 into under root 2, so it is 8.4 something like that. Okay, if I am not wrong, yeah, it is 8.4 something like that. Okay, so that is the gain margin. Sorry, this is not 2, right? This is under root 2 because omega p is under root 2. Sorry. This will be under root 2 into under root 2. Ultimately, it will come out to be 6. Sorry, this will be 6. Gain margin will be 6. Okay. Now, in the second case, if I have exponential adverse as well, e raised to power s capital T divided by s into s plus 1 into s plus 2. Now, right, you will not be able to simply find the phase crossover frequency. It will be a bit difficult because if I now write the phase expression, it will be minus j omega, not j omega, sorry, minus omega into t. Like this is also known as TD, the transportation delay, TD, because it provides some time delay. That's why minus 90 minus tan inverse omega minus tan inverse omega by 2. Okay, now I will not be able to solve this. This is in radians. I will not be able to solve this unless and until I get some value. But what I can say is that previously the expression was this, correct? Now this is also adding extra phase lag. So I will reach my minus 180 much faster. Okay, so my omega p2, right, will be much lower than omega p1 because I am subtracting some extra angle. So I will reach my phase much earlier. So if we solve this equation for some TD value, TD, let's say TD equals to 1, you will get your value omega p dash equals to 0.664 radian per second. Okay. So phase crossover frequency reduces. As phase crossover frequency reduces, as the numerator is like gain of the numerator is constant, so overall gain increases at phase crossover frequency. If gain increases, that means the gain margin reduces. Okay, so it makes the system more unstable. Okay, gain margin will reduce, it will make the system more unstable. Okay, what about the gain crossover frequency? Gain crossover frequency won't change. Why? Because obviously the gain expression hasn't changed, so gain crossover frequency will not change. So omega g1 will be equals to omega g2 because the gain expression has not changed. What about the phase margin? So phase margin, right now in the phase margin expression, 180 plus it is angle of g of j omega g into h of j omega g. So what will happen is that with the angle expression, due to the delay, extra phase lag will be added. So phase margin also reduces, right? The e raised to power minus omega t, it adds extra phase lag. So the phase margin will reduce. So stability ultimately, right? What can I come to in the like conclusion? Stability reduces. Okay, so if I add an exponential at transportation delay, the stability of the system will reduce. Okay, so that is what is written in the summary part. Here I've written it. Okay, so these are all key like key points. This will happen. Okay, just I have explained in very short because obviously we have to cover a lot of things. So now, right, we'll just solve questions. Like 2-3 questions we have, we'll solve questions. Okay, after this you can go and attempt the FYQ series of polar plots. Okay, then in the next video I will bring Nyquist plot, and the video after that I will bring Bode plot and second order systems. Okay, so the frequency response of a linear system is given, the gain margin and phase margin. So what is gain margin? Gain margin is the inverse of the gain at phase crossover frequency. That is when my angle is minus 180, what is the gain? Gain is 0.5 and it is the inverse. So gain margin will be inverse of this in decimal scale. But in decade scale, what it will be? It will be 20 log of 2. 20 log of t is 6 dB. If you remember this identity, it will be helpful because in Bode plots, anyway you have to remember. So 6 dB is present here and here. What about the phase margin? Phase margin is the phase plus 180 at which gain crossover frequency. So this will I will add 180 with this, so that it will be 30 degrees. So I have 30 degrees of phase margin, so plus positive phase margin, so it will be A. So option A will be correct.
Let's begin with few gate PYQs of polar plots. So this is the first question. This was a gate 2020 EC question. A system with transfer function 1 by this is subjected to the input this. The steady state output of the system is this. The value of E is. It's very simple. Basically, they have given me the input. If they have given me the input, what I can find out? I can understand the amplitude of the input, also the frequency of the input. So because we know, if I have a transfer function, we know the output, let's say C of S upon H of S on the frequency domain would be basically my transfer function. So if I put S equals to j omega, right, then my C of j omega magnitude would be equals to magnitude of T of j omega. So basically I can write my C of j omega would be equals to T of j omega into H of j omega. And of course, these will have some phase that will give me the phase. Okay, I can just okay I can get the phase here, phase difference, and as well as I can get the amplitude. So for this question I only need the amplitude. I don't even need to calculate the phase difference, but you can verify whether whatever you have calculated is correct or not. So let's first of all compare the magnitudes. So if I compare the magnitudes, the magnitude on the right hand side is 1 by root 10 and the magnitude on the on the left hand side is 1 by root 10. On the right hand side, what is the magnitude of my transfer function at S equal to j omega? Omega is 3. Omega is 3. So omega is 3. So this would be 1 by under root of 3 square plus 1 plus, sorry, not plus, into 3 square plus e square multiplied by the input magnitude. What is the input magnitude or the amplitude? It is 5. So it is 5. So now let us solve this basically. So I can write here 3 square plus a square or 9 plus a square will be equals to this will automatically get cancelled, right? Under root 10 will be cancelled is equals to 5.
so not 5, sorry. So this is under root 3 square plus a square is equals to 5, or I can write a square will be equals to 25 minus 9, that is 16. So a has to be positive mentioned in the question. So a will be equals to 4. A can be plus minus 4, but of course a is positive, so a will be 4. This will be your simple answer for the question. Now if you want to, you can go one more step, of course not in the actual exam, but after the exam, that you can verify whether you are correct or not. So let us verify what is my uh, phase shift. So if I see what will be my phase shift, so angle of C of j omega, if complex numbers are multiplied, angles will be added. So angle of T of j omega plus H angle of H of j omega. So the angle on the right hand side, remember everything is in radians here, right? Degree is not there, this is in radians actually. So keep this in mind. It is negative minus 1.892 angle of my transfer function at omega equals to 3. So this would be basically minus of tan inverse 3, and a I have got, a value is what, a is 4, right? A is 4, and minus of tan inverse 3 plus tan inverse of 3 by 4. So what will be this value? Let me calculate this value. Radians, remember you have to calculate in radians. So tan inverse 3 plus 0.75 tan inverse, so that would be 1.892. 1.892, this is 1 point minus 1.892, sorry, this is the h of omega plus input, right? This is the sorry, this is not h, sorry, this is not h, sorry, c upon r, sorry, this will be r of s, right? Generally we denote the input to be r, just a small change. So this will be r. Now if I see that r of j, the frequency, the phase of my input at this particular frequency is coming out to be 0, right? If this will be cancelled, it is coming out to be 0. Is it supposed to be 0? Of course. What is the phase shift here? Input 0 degree. This was my reference, so it is verified. Whatever you have calculated, it is verified. So that's how you can verify through the phase condition. Now let's come to another question. This is a gate EE 20220 question. A stable real linear time invariant system with single pole P is given, has a transfer function this, okay, stable linear time. Now it is a stable linear time invariant and it is a stable system. If it is stable, right, this obviously means that P has to be negative. If P is positive, then I will get a pole at the right hand side, otherwise system will become unstable. So assumption is P is negative, then only I will get a pole on the left hand side, because this is the transfer function. DC gain is given as 5, with the DC gain as 5. So if the DC gain is 5, so if I put here uh, s equal to 0, it will be 100 upon minus P. Now P is of course assumed to be negative, so which is 5. So from here I get the value of P, that is minus 20. Okay, value of P is minus 20. The smallest positive frequency in radian per second at unity gain is closest to. So basically they're asking what is the frequency at unity gain. Unity gain basically meaning when the magnitude of my transfer function will be 1, when it will provide unity gain. So omega, this will be, if I replace my s with j omega, this will be j omega whole square plus 100 upon j omega. P is minus 20, so this will be plus 20. This is my h of j omega, which will be minus of omega square plus 100 upon j omega plus 20. Now if I calculate the magnitude of this, so if I calculate the magnitude, this would be yeah, just give me 1 second. This would be, this is the top part is real, so I don't need to worry about the top part. This bottom part would be 420 square, that is 400, that is equals to 1. So if I assume one thing, so either there are two ways, either you can put the values here or you can solve. So let's solve actually. Let's assume that x is equals to omega square, that is the gain crossover frequency or whatever you want to assume. X equal to omega square, so this equation will be converted into x plus 100 whole square equals to x plus 400, right? I am squaring both sides. This will be x square minus 200 x plus 10 raised to power 4 equals to x plus 400. So this will be x square minus 201x
plus 10 raised to power 4 minus 400. So if I solve for this particular thing, this will be actually 9600. So this will be minus of b, that is 201, plus minus b square, that is 201 whole square, minus 4ac, that is plus 9600 into 4 upon 12. So if I solve for this particular value, I can get the value, solve for this. So this will be 201 whole square. Of course, I will ignore the negative solution under root 280. I will ignore the negative solution. This plus 201 upon 2, which is coming out to 240. Now x is omega square. So omega would be this under root, which is 15.512, which is not actually matching with any of our answers. So I have to again verify this, whether I have solved this correctly or not. So b square, one second, b square minus 4ac. Oh, sorry, this will be negative, right? What am I doing? B square minus 4ac. Sorry, there will be negative sign, minus 4ac. Small mistake on my behalf. So this will be 44 actually. So 201 plus minus 44 by 2. Okay. There are two positive solutions. Both of them are positive solution. So this will be, if I choose, like they have asked in the question, the smallest positive frequency, smallest. So I will choose the smaller value obviously. Like I will calculate both values, then I will explain. So this plus 201 upon 2, that is 122. One of the x value comes out to be 122, and the other x value comes out to be, let me calculate, 78.133. So I got two x values. So omega would be under root of this, right? Smaller omega would be 8.84. Of course, I will get another omega, another solution, that is 122 under root, that is 11. But in the question, what have they asked? They have asked me the smallest one. So I will not tick mark this one. I will tick mark this one. But if it was MSQ and smallest was not mentioned, just it was mentioned what are the positive frequencies for which my transfer function will provide unity gain, then both of them I will tick mark both of them. Both of them are valid. Actually, these are the squares. So they have given all the options basically. Because if you're in a hurry, you will say this is my solution. X is my solution. No. X is omega square. So under root x is your solution. So this is the solution of this particular question. Let's solve this question. The loop transfer function of a negative feedback system g of s h of s is this. The phase margin of the system will be, what is the phase margin? So open loop transfer function is given basically. Phase margin is nothing but the 180 plus have they asked in the phase margin in degrees? They have asked in degrees. So 180 degree plus angle of g of h of j omega equals to omega gc at given cos of frequency. Okay. So yeah. Now let us calculate that. Let us first of all calculate what is my omega gc. Omega gc would be the frequency at which the gain of my OLTF would be 1. Magnitude of the gain of the OLTF would be 1. That is omega g square plus 1 upon omega g is anyway square only, because you will take the magnitude, that is equals to 1. And of course, don't forget there would be a under root here as well, right? Don't forget, like you are taking, like I'm just skipping few steps. My expectation is you already know all these things. So now if I square this will be 4. So yeah, let us square this. on both sides. If I square this, right, this will be 4 omega g square plus 1 is equals to omega g raised to the power 4. So again omega g square is x. So this equation would be x square minus 4x minus 4 equal to 0. So minus of b plus minus b square minus 4ac, which is plus 16 upon 2a. So 32, 16 into 2, so 4 root 2. So this will be actually 4 if I take common 2, 1 plus root 2, which is like a very weird value. Let me first write down the value. Actually, okay, there will be plus minus, plus minus. So of course I will ignore the negative solution. We only choose the positive solution. So x is 4.828. Then if I take the under root, this will be, so omega g would be 2.2 basically, 2.2 radian per second. You can again verify this. You can put omega g here equals to 2.2 and check, cross check whether you actually are getting the magnitude to be 1 or not. Let us verify. If I do the under root, then if I multiply by this, then divide by 2.2 whole square, yeah, approximately it is almost coming out to be 1 only. Yeah, it is coming out to be almost 1. So it is correct. So yeah, let us now calculate the phase margin. So for calculating the phase margin, I have to do 180 plus angle. So how much phase shift does this one provide? Do you understand? So if I have only 1 by s, that is 1 by j omega, so this provides a minus 90 degree phase. If I have 1 by s square, this is minus omega square, negative provides a minus 180 phase shift, right? Negative sign I can write here as well. It will provide either you can say 180 or plus 180 or minus 180. Both are same. Both are same. So I will write here minus 180 is providing minus 180 phase shift. The numerator is providing tan inverse omega upon 1, omega g upon 1. Omega g is supposed to be 2.2. So remember to put in degrees. Everything is in degrees. So your answer would be tan inverse 2.2 basically, which is 65.55. Okay, this is your final answer for the question. They have asked you to round off to one decimal place. So you'll write 65.6. I think 556 is there. So 65.6 degrees. This will be your final answer of the question. Let's solve this one. So here an input x of t is applied with a transfer function given by h of j omega. Phase and magnitude both are shown. If y of td equals to 0 for x t equals to ut, the time td would be in microseconds. So basically, right, they're telling me that whenever my input is a step function, xt is a unit step. Basically, xt is unit step. So its frequency domain would be, Laplace domain would be 1 by s. Then it is telling me that the output after a delayed time, that is td, is going to 0. So what is the value of the td basically? Okay, what to do with the value of td? So apply it with the frequency transfer function is shown. So this, right, is a DC signal. This is a DC signal. So if this is a DC signal, what is the gain of DC signal? 1. It is always constant, correct? The DC signal is always constant. Now this is interesting. Phase response is shown, and now they are asking me what is the time. Okay, so this, right, I'm saying that as the frequency is increasing, the phase is going to minus 180, but the gain is always constant. So this behavior is like just like a all pass filter, because for an all pass filter the gain is always constant, but the phase will change. It will go to plus 180 to minus 180. So there can be, like, I can assume my transfer function to be something like this: s plus a or s minus a plus s by s minus a by s plus a. This can be my transfer function. So if I calculate the gain of this at any frequency, it is always 1. But the frequency, sorry, but the phase would change. So for the top one, it will be minus of, so A is negative, right? If A is negative, that is real part is negative, imaginary part is positive. Imaginary part is positive, real part is negative. So I'm lying here. So this would be 180. So yeah, if I calculate the theta here, yeah, 180 minus theta, or no, sorry. So yeah, I'm going, yeah, 180, yeah, minus theta, that is correct. And the bottom one, both are positive. So this will be minus of theta only. Theta is, where theta is tan inverse omega upon a, like I hope you are understanding, like I will replace my s to j omega, and because this real part is negative, so this will be, the angle will be theta, like 180 minus theta, and this will be minus theta, so which is 180 minus 2 theta. At omega equal to 0, it is providing 180 degree phase shift, but here I am observing that omega equal to 0, it is providing me 0 degree phase shift. So what I can do, I can just add a negative sign. If I add a negative sign, automatically it adds a another 180 degree phase shift. So overall my angle becomes, so there will be another, either you can add or subtract 180, right? So okay, yeah, I can add subtract 180, like does not matter, right? So I'm just adding a negative sign outside, so this will become minus 2 theta, and at when my omega is infinity, what is my theta? Theta is 90, so this will be minus 2 into 90, that is 180. So I'm actually getting this transfer function. So this is my transfer function. So I got my transfer function. Now they are telling me that in time domain, what will be this? Okay, so can I find out my location of poles as well? Can I find out my location of poles as well? So one thing is there, one interesting fact is there, that at omega equals to 10 raised to power 4, my phase is 90 degrees exactly, right? This is matching exactly. So this is the exact plot. So if I put omega equals to 10 raised to power 4, I should here receive 90 minus 90 degrees. So when will minus 90 occur? So tan inverse of omega by a, when my omega is 10 raised to power 4, 10 raised to power 4, that is my theta, right? So I'm replacing my theta with this, my actual value, minus 2 tan inverse is equals to minus of 90. At this particular frequency, the phase is exactly minus 90, right? So first of all, I compared the phase, I just figured out what is my transfer function, then from that I'm just directly finding out the value of a, because that will be helpful to exactly find out when my output will be exactly equals to 0. So if I solve for this, this would be yeah, whenever this is 45, so tan inverse omega equals tan inverse this upon this is equals to 45. When it is 45, when both this numerator and denominator are same, then only it will be 45. So a is actually equals to 10 raised to power 4. From that I got to know a is equals to 10 raised to power 4. Uh, that is my solution. Now let us find out what is my output y of s. Y of s would be my transfer function, that is h of s, into the input, that is r of s or u of s, whatever, which is basically what is my transfer function, s minus negative sign is there, don't forget the negative sign, into s minus a, that is s minus 10 raised to power 4. Let me first of all keep it a only, s plus a into 1 by s, this unit step function. Let me basically break this down. So so if I solve for this, right, so I can do partial fraction. So at s equal to 0, this will be minus of a upon a, this is minus 1, so this is 1, so 1 by s, and s equal to minus a, s equal to minus a, minus a would be, I'm just doing partial fraction, okay, minus a 2a upon minus a, this will be 2, so minus of 2 upon s plus a. Let me figure out whether I'm doing it correctly or not. So if I again solve it, this will be s plus a minus 2 into s upon s into s plus a. This would be, okay, I have not solved it correctly, it seems, because if I replace s with 0 here, this will be minus 1 into 1. That is correct. Okay, if I replace this with minus a minus 2a to 2 into just 1 second, 2 into this, 2 should be there. So what is it coming? It is correct only, yeah. Oh, sorry, it is correct only, right? So this is coming out to be a minus s. This is correct. A minus s, yeah. A minus s upon s into s plus a. So this is correct. So that's how you do the partial fraction. Just I'm trying to figure out on the go, on the fly, whether I'm doing it correctly or not. Okay, this is correct. So now this is my y of s, correct? So we can simply take the inverse Laplace. So y of t would be u of t minus 2 e raised to power minus at. So when does it become 0? So for t greater than 0, u of t is simply 1, right? So 1 minus 2 into e raised to power minus 80 has to be 0 at t equals to td. So I can say my td would be equals to, this will be 1 by 2, yeah, 1 second. Okay. So td would be, so if I solve this equation, right, so this will be e raised to power minus a td is 1 by 2. So my td would be negative of ln. So I can take the ln inside. This will be 1 by a ln of 2. Like I just taken the negative sign inside and flip the 1 by 2. Now remember, in what units have they asked? In microseconds. So what is your a? A is actually 10 raised to power 4. A is actually 10 raised to power 4. So if a is 10 raised to power 4, correct, and this value is in seconds, 1 by 10 raised to power 4 ln 2 in seconds, but they have asked in microseconds. So what I'll do, I'll multiply and divide by 10 raised to power 6, right? 10, yeah, 10 raised to power 6. So what will happen? Automatically this will become 100 ln 2 microseconds. I hope you know how to convert seconds to microseconds. So 100 ln 2 is present in option A. So option A would be a correct answer. So you have to actually calculate the whole transfer function. You cannot just simply solve it. So they are asking you questions from basics. It's not like they are asking you polar plot, gain margin, phase margin. They are asking gain margin, phase margin. Yes, but they have also asked this basic kind of questions, which even if you don't know anything regarding the concept of polar plot, still you can solve it. Let's solve the next one. The open loop transfer function of a unity negative feedback system is this, where k, t1, t2 are positive constants. The phase crossover frequency would be equals to what? So generally there is a shortcut to this. The phase crossover frequency is basically the under root of t1, t2. Okay, that will be option B. So option B would be a correct answer for this question. How else can you verify? First of all, you can verify simply with the dimensions. So only this one has dimension of 1 by second. All other, this has a dimension of 1 by second square. That is totally incorrect. This has a dimension of, again, some 1 by second raised to power 3 by 2. This has a dimension of 1 by second raised to power 3 by 2. So only this one is matching the dimensions, right? So only this one will be answer. Actually, it is t1 is not exactly seconds. Actually, your s omega would be omega radian per second. So this will be in second per radian. So this will be second per radian. Radian will go at the top. So this will become radian per second. Okay. So yeah, that's how you solve basically these kind of questions. So of course I will solve you using the lengthy method. The phase crossover frequency. The phase crossover frequency is the frequency at which the phase of my OLTF becomes minus 180. So when will it become minus 180? When this bottom part will be completely real. Basically the imaginary part will be 0. So this will be, if I replace s with j omega p into 1 plus j omega p. Of course you can calculate the angle, that is also one way. Calculate the angle becomes minus 180, but I am solving using this method, omega p t2. So the denominator has to be completely real. So let me cross multiply a few things. J omega p, this will be 1 plus j omega p. If I take common, this will be t1 plus t2 plus, sorry, minus omega p square t1 t2. Now let me just not multiply omega p, let me just multiply the j. If I multiply j, I'm just concerned about the denominator because numerator is already real. So j, this will become minus, actually this will become real now, minus omega p t1 plus t2, and this will be minus of j omega p square t1 t2. And of course I know the imaginary part has to be 0 because overall my OLTF has to be completely real, because the phase is minus 180. When it is minus 180, it is real but negative. So it is still real. So the imaginary part has to be 0. So imaginary part is 1 minus omega p square t1 t2 has to be 0. So omega p would be 1 by under root t1 t2. So omega p is 1 by under root t1 t2. That is your solution. Anyways, we solved it already, but yeah, this was the lengthy way. Let's now solve the next question. So this is the next question where we have to we have been given the magnitude and the phase plots for LTI system. The transfer function of the system would be what in in Laplace domain only. So I'm observing that the magnitude of my uh, this transfer system is always constant, which is 8 dBs. So what is 8 dBs in uh, decimal scale? So actually this will be taught to you in Bode Plot, but for those guys who don't know, so basically we can convert from decimal scale. Let's say x is a decimal number to log number like this, 20 log x. So 20 log x will be my dB value, log value, that is decimal value, that is 8. So x would be basically uh, 10 raised to power 8 by 20. So I hope we can do how to take the, I hope you know how to take the inverse log. So 8 by 20, 10 raised to the power this, so it is 2.511 2 volts. So not volts, right? Whatever this value, x is this 2.512 value. So this is the magnitude of my transfer function. So I'm observing this, yes, this has always constant magnitude. This again, this magnitude is constant, but it is 1.04 wrong. This is constant and 2.151. So either this will be true or this will be true. Again, here I'm observing if I calculate the magnitude is reducing because I have a s plus 1 that will only make it 0 at omega equals to infinity. But here I see magnitude is constant. So only option A and D are my possible solutions. Now I see the phase is decreasing linearly. So if I calculate the phase of this will be basically minus 0.032 omega, and this would be minus, basically not this is the angle, minus 0.0232 omega, and this will be minus 1.047 omega. Now we can compare this, right? So I see at omega equals to 1, phase is minus 60. Now remember, this is in radians. So if I put omega equals to 1, it is minus 0.47 in radians. So what is 60 degree in radians? So let me compare 60 in radians. So 60 into pi upon 180, which is 1.047, which is here also it is coming negative, here also it is coming negative. So this is matching. Here the phase will be something else, which is wrong. So option D will be a correct answer for the question. Very simple question, right? Basics question. They will not ask you very difficult questions. So let's solve this next question. The phase margin of the transfer function g of s is equals to this. Is equals to what in degrees? Phase margin. Again, they are asking me what is the phase margin. So yeah, let's calculate. We have to round off to the nearest integer. Okay. So yeah, let me solve this. The phase margin of the transfer function would be g of s equals to this. So phase margin, first of all, for that I have to find out the gain crossover frequency. Like basically, so what is the gain crossover frequency? This will be 1 by 1 minus j omega upon 1 plus j omega whole square. So if I calculate the magnitude of this will be 2 into 1 plus omega square under root upon 1 plus omega square. Correct? I'm squaring it, so under root is gone. That is equals to 1. So from this I can write this will be, if I again I have to assume that x is equals to omega g square. X equals to omega g square. So omega g square. So this, if I square both sides, this will be 4 1 plus x equals to 1 plus x whole square. That will be 1 plus 2x plus x square. So x square minus 2x minus 3 equal to 0. So 2 plus minus b square uh, uh, minus 2 plus minus b square is 9, sorry, hold on, minus b plus minus b square minus 4ac upon 2a. So yeah, if I solve this, yeah, this will be 2. So of course I have to ignore the negative solution. This will be 4 plus 2, that is 6 by 2, that is 3. So x is 3. So omega g will be under root of 3. So I got omega g, that is under root of 3. So now I have to calculate the phase. So phase margin will be 180 plus now remember this is minus of j. So your imaginary part is negative and your real part is positive. So I am lying here. So the angle provided will be minus of tan inverse omega by 1, that is omega is root 3 at omega g, right? That is root 3. Then I have a square here. So I will have minus, because it is in the denominator, into 2 into tan inverse root 3. So what is root 3? Tan inverse root 3, it is basically it is actually 60, right? So it is minus 3. So this will come out, this should be 0. This should come out to be 0. There is some sort of, let me just verify, because there is a I am like my in my answer key it is 2. I will just verify the answer. Yeah, so I verified. I had written 2 there, but I forgot to write the range. Range was minus 2 to 2. So basically 0 is of course a correct answer. 0 is the perfect answer, but they have given you enough range, minus 2 to 2. That is a large range. So yeah, let's solve the next question. Consider the stable closed loop system. The magnitude and the phase values are given of g of s. The value of the gain ki for a 50-degree phase margin is the value of the gain ki for a 50-degree phase margin. So I need a phase margin of 50 degree. Okay, what will be the value of the gain ki? Okay, so at phase margin what happens? Uh, so I need a phase I need a phase margin of 50 degree. That means 50 degree equals to 180 plus angle of my this and this. This is my, let's say, whole OLTF. angle of OLTF at omega equals to omega GC. So my angle of OLTF at omega equals to omega GC comes out to be minus 130 degrees. So that is the angle of my OLTF at omega equals to omega GC. Now, yeah, the gain of Ki. Okay, I got the so what is the angle provided by this particular fellow? The angle provided by this particular fellow is always minus 90. Right? The angle provided by this particular fellow is always 1 by 90. Sorry, minus 90. So angle provided by G of S at omega equals to omega GC would be like this, will be the addition of this plus the angle provided by this, right? Because it is in the multiplication. So minus 90 plus this equals to minus 130. So angle of G of S would be minus 130 plus 90, because minus 90 was there, plus 90. So this would be minus of 40 degrees. Minus 40 degrees. So minus 40, when is the phase of my G of S? Minus 40, this particular case, right? So what is the value of omega? 0.5. What is the magnitude provided? Minus 7 dBs. Minus 7 dBs. Now one thing we know, simply in dBs, if there, let's say there is a multiplication, let's say magnitude of G of j omega into magnitude of this Ki or whatever h of j omega, let me assume h is to be Ki by s, Ki by j omega, this is some x magnitude, right? And we know that it is unity gain frequency, right? This magnitude has to be unity gain frequency, that is the definition of phase margin. So if I take the log on both sides, simply the things will be added. 20 log base 10, if I do 20 log base 10, because it isn't given in dBs, that's why I'm doing all this. 20 log of x is 1, right? Unity gain frequency. 20 log base 10 of 1. So it is inverse 0. So it is 0 basically. 20 log of 1 is 0. So this will be this value plus this value. 20 log of this value plus 20 log, because in log multiplication will be converted into additions. So I will have 20 log of G of omega, that is given. I know the magnitude already, because from there I got the phase. From the phase I got the information about the magnitude at this particular frequency. So my omega GC is 0.5. So this will be 7 dB plus 20 log, let me write this as y. 20 log of y is equals to 20 log base 10 h of j omega. That is equals to 0. So y has to be minus of 7 dB. So let me convert this into decimal scale, otherwise you will be scared. So if I convert this into decimal scale, so your magnitude of h of j omega would be equals to 10 raised to power minus 7 by 20. So if I do that, just give me 1 second. Seven by 20, 10 raised to power this 0.44. It is coming out to be 0.44. And what is your magnitude of h of j omega? 0.44. So 0.44 is this. So 0.44 is this, right? So this will be Ki by S. So Ki by, this is my Ki by j omega, magnitude of j omega is omega only, omega g. Omega g is 0.5, right? 0.5, omega g is 0.5. So this will be Ki by 0.5. So Ki would come out to be something half of this, right? 0.5 times 0.44. So this into 0.5, which is coming out to be 0.223. They have told us to round off to 2 decimal places. So we will do that. Correct? I'm just thinking whether I'm doing everything correctly or not. Just give me 1 second. Okay. Okay, I'm extremely sorry. Gain is minus 70. We don't mess up. Gain is minus 70 because my answer was coming out to be different. That's how I got to know. So this, right, 20 log of this is coming out to be negative because this is something, the value in decimal scale is something less than 1. So that's why it is negative. You will ask, how is the gain negative? No, gain is not negative. But I'm taking the decibel scale, right? 20 log of that. So gain is positive only, but it is less than 1. Whenever it is less than 1, log of that value will come out to be negative. That's why it is negative. So actually your y is supposed to be plus 7, not minus, sorry. So to be plus 7. So basically, right, so 7 by 20, yeah, 2.238. So yep, so now if I so k value, what is the k value? K value will be sorry, this value is 2.238. 0.5 into this is coming out to be 1.12, almost 1.12. So ki will be 1.12. This will be an answer for the question. Let's solve the next question. So yeah, let's solve it. The sinusoidal transfer function corresponding to the polar plot shown in the figure. What is the sinusoidal transfer function? I can observe that as the the real part of my transfer function is constant. The real part of my transfer function is constant, that is 1. This is the plot between real and the imaginary part. Okay. So the real part is always constant, that is 1. The imaginary part is always changing, correct? It is always going, it is going to something negative value. So which of my options has the real part to be constant? The real part I see, option A has the real part constant. Option C also has the real part to be constant. Option B and D, if you see, the magnitude is constant, but the if you see real part is changing with omega, real part will change, and for option D also same will happen. So out of option A and C, what is my answer? So I see that if I'm increasing my omega, the imaginary part, I'm going towards negative. So here, if I increase my omega, what is happening? It is 1 plus j, then 1 plus 2j, then 1 plus 3j, and so on. So it is increasing, right? So this is not correct, right? My imaginary part is going towards the negative side. So this is correct actually. This part is correct. Okay. So yeah, this part is correct. So option A will be correct because of course if I increase omega, this will be 1 minus j, then 1 minus 2j, then 1 minus 3j, and so on. So this part is correct, this part is incorrect. Okay. So yeah, that's it basically. That's the solution. I think with that we are done with the uh, polar part and the frequency response of second order. Now we will discuss about Nyquist plot. So let's start with Nyquist plot. So first I will discuss about the mapping theorem, because actually what Nyquist plot does is basically it maps. Okay, what is mapping? Mapping is the relation between points in two planes as mapping or transformation. Basically, if you don't know, don't worry, I will come to that. I will come to the visualization, don't worry about it. So Nyquist plot, each and every point in S plane will be mapped to corresponding imaginary and real plane, okay, of G of H of S, of the OLTF. So this I already know how to plot imaginary of G of H of S and real of G of H of S, I know. But here, right, what we're doing, we are actually mapping, we are doing some transformation. I will explain that, don't worry. Where G of S and H of S is a function of S, okay. So like this will help us in finding the stability, don't worry, I will discuss about this. So why is mapping important? Why do we need it? For CLTF to be stable, no poles should lie on the right hand side of S plane, that we know, right? That we know. But to find the poles, right, it is very difficult. It is very difficult. Why it is difficult? If I have a fourth order equation, if the characteristic equation is fourth order, let's say s raised to power 4 plus 3s cube plus 2s square plus 1 equals to 0. Now can you tell me, without the like you have to do Routh, obviously Routh is very good,
But without doing route, or can you exactly tell me the stability? No, right? You cannot. So we had to search for some other method as well which can discuss about the stability. So one of those method is Nyquist plot, which uses mapping. Okay, I know you don't understand what is mapping. Slowly we will get to that, don't worry about it. So hence is as it is very difficult to check for the whole right hand side, because what like how we used to check, you can check if I have a right hand pole or not. Just choose all the values of the right hand side, like let's say s equal to 1. If I choose s equal to 1 and put in this equation, right, and put in this equation, if this equation is satisfied, that means I have a pole at s equal to 1, that means I have a right hand pole. So like this also, again I will check for s equal to 2, s equal to 3. Route you can do, okay, route is one method, but I'm ignoring the route. Okay, without route, if you just want to check, you have to use the hit and trial method. There is no other option left. So if we have to use the hit and trial method, then it becomes very difficult. Then it becomes very difficult, right? I have to check for all the points. I have to check for 1.1 as well, 1.2 as well. It becomes very difficult. So what we do in turn is we map all the right hand side of s values, right, into some other plane. Okay, and through there we check it. Okay, don't worry, slowly we'll understand. Just I'm giving you a basic idea, basic idea. So let's do a basic example of transformation. So this, right, is a complex number, right? X equal to x plus iy plus r e raised to power j theta. Now in the rectangular coordinate system, I can write it as 2 1. What is 2? 2 is the x value and y is the 1. Okay, y is 1. Now if I want to write it in polar, can I write it in polar as well? Yes. In polar, how will you transform it? In polar, if you want to transform, like this point will be same because the planes have not changed. Okay, don't worry, later on the planes also will change. There also we'll discuss what happens if the planes change. But for now, just hold on, bring this camera down. Yeah, but for now it is, no, this is too much down. Yeah, now it is, I guess now it is fine. Yeah, for now just understand what do we mean by transformation. If I want to transform this point, I can write this like this as well. This will come out to be under root 5 1. Okay, this will come out to be under root 5 and 1. So like the point get transformed to under root 5 and 1. So that like these are same points only, but in a different manner I am representing it. So like it doesn't matter. Okay, they are telling the same thing. Okay, but sometimes with the help of this transformation, maybe it will be easier for me. So not, this will not be 1. Sorry, this will not be 1. Like how do I got under root 5? So basically I am writing magnitude and angle format, right? So it will be 2 square plus 1 square whole under root, that is under root 5, and obviously tan inverse y by x, that is the argument of the complex number, right? Tan inverse y by x is tan inverse 2, and tan inverse 2 is, in short, we know tan inverse 2 is 26.6 degrees, something like that. Okay, so like this is just a shortcut. This I recommend students to remember what is tan inverse 2. But if you don't, you can obviously use the calculator. You always have the freedom to use the calculator. Okay, so this will be 26.6 degrees. So this will be 26.6 degrees. Okay, so this is my point in the polar plane. Now like these are the transformation that we do. Okay, so now what is mapping? Mapping is I have a function fz, okay, z square. So in the z plane, that point 2 comma 1 is here. Okay, it is somewhere here. But in the fz plane, where it will be. So now I am mapping. What does mapping mean? Basically it is transforming this point to something else. So if I am plotting now fz, so if I put z equals to this, where will I lie in this plane? So now I will put z equals to what? 2 plus I, that is 4 minus 1 plus 4i. Okay, so this will be 3 plus 4i. Okay, so this is my point in the fz plane. So in the fz plane I will be lying somewhere around here. Okay, this will be my 3 comma 4. Okay, this is my fz plane. Now you might say, what is the advantage of this? That obviously I will tell you later on, but there is certain advantage, and that we'll understand. Basically we don't have to check all the values of s here. Okay, so for particular value of z
in the FZ plane I'm getting some different point, and we'll map all the points in the FZ plane, and through that FZ plane only we will discuss about stability. Okay, so just giving you another thing, like this was about the mapping. Okay, this is about the basics of mapping, that is done. Now let us understand what is contour. So contour is basically the shape of the outer surface of a curve is known as the contour. Okay, because it is important in Nyquist plot. Sometimes the word contour will be there and you don't know what is the definition of contour. So that is also very important to understand the definition of contour. So contour is basically any closed surface I have and the curve enclosing the surface, right? Curve enclosing the surface is known as contour. So this is a contour. Okay, this is the contour here. Okay, so these are all contours of a surface. Just a quick definition to explain. Okay, so let's now discuss about few observations of mapping theorem. So these are the conclusions after a few derivations that I have derived in my full course. Of course, we don't have time, so I will not do the derivations. I will directly tell you the observations of mapping theorem. So first observation is, if 0 of the mapping function lies inside the contour, then direction of the mapped contour won't change. What does it actually mean? So first of all, I have told you what is a contour. Okay, I've explained you what is a contour. This is a contour. Now once you map a function, right, in some other plane, let's say I'm mapping like this, my fz is equals to z plus 2. If I'm mapping this like from the z plane to this fz plane, and if my contour is like this, I have a closed contour, then the mapped contour will also be like so. Then the mapped curve, right, mapped curve will also be a contour. It will also be a closed contour. Now there are a few properties of the mapped contour that I can explain. So if my initial contour, right, has a anti-clockwise direction, and if a 0 lies inside the contour, what do I mean by 0 lying inside the contour? Let me take an example like this, right, and let me take the points, extreme points, this as 3, minus 3 in the x-axis, this will be plus 3, minus 3 in the y-axis. Okay, now if this contour, right, is mapped to this fz plane, fz is here. Okay, fz is here. So fz has a 0 at z equals to minus 2. So the 0 is lying somewhere here. So the 0 is actually lying inside the contour. Okay, I have explained you what is the contour. So 0 is lying inside the contour, and the conclusion tells us that if 0 of a mapping function lies inside the contour, then direction of the mapped contour won't change. Basically what it is telling, that when I will map the contour, right, in the fz plane, I will also get, when I will map the this contour in the fz plane, I will also get a contour, and that mapped contour will have the same direction as the initial contour. So if it has anti-clockwise, this will also will have anti-clockwise direction. This is just example. Okay, this will also have anti-clockwise direction. Now let's say if it is outside, then I cannot comment. If the 0 is outside, then I cannot comment. Okay, now here next point, if poles of the mapping function lie inside the contour, then direction of the mapped contour will change. If poles of the mapping function, now let's say the fz is like this, z plus 1. So I have a 0 and a pole. What will happen due to the multiple, like for now let's just take one pole only, one pole and one 0. Later on I will discuss when multiple poles and zeros will be there, I will discuss about that as well. Don't worry regarding that aspect. Okay, I will discuss about that. So when I have a pole, then I know that pole is lying inside this contour, and if the pole is lying inside the contour, I have told you with one of the point that if I will map this contour, right, in the fz plane, then that map contour will have its direction change. So that will also be contour, but that direction will change. So what is the direction? Direction is anti-clockwise. So here the direction is clockwise. So exactly this is what will happen. Direction will change. So this is one of the observation. Origin will lie inside the mapped contour in f of s plane if either poles or 0 lie but not all inside the previous contour. So my new mapped contour, right, will include the origin if either pole or 0, either one, pole or 0 is inside the previous contour. So if I observe that the pole is inside the contour, that means I will, in the mapped contour, I will pass the origin. Okay, this is the conclusion. If this 0, if this pole was outside, right, let's say if the pole was something like this, z plus 4,
this is -4. So for sure I can safely say that I will not include the origin. The mapped contour will not include the origin. Okay, so these are few conclusions about mapping. Now let's do a basic mapping. This is also a mapping, right? Whatever we have done in polar plot, that is also a one type of mapping. What do we map in polar plot? Actually what we do is, first we write this function in terms of j omega. So we write this 1 plus s j omega tau. Then what we do, we vary our omega from 0 to infinity. So this is what? This is the initial function. This is the z, right? This is the z. And I'm mapping to f of z. In this case, f of z is this function, or this function, right? So from this, I'm mapping to this function. That is exactly what we do. So in the S plane, I am varying my omega from 0 to infinity. So I'm mapping this straight line, okay, mapping all the points, this straight line to my g of j omega plane, g of j omega into h of j omega plane. So this is also mapping of what? This is mapping of j omega, mapping of j omega. Okay, so mapping of j omega. Now I hope you remember the polar plot for this. The polar plot for this was supposed to be like something like this, right? It was something like this. So this is also a type of mapping. So in polar plot also we do mapping, okay, mapping of positive values of omega from this straight line to this g of h of j omega plane. Now let's do a few more mapping examples. I will just directly solve. I will explain you what are the solutions. So let's say if I have a function fs equals to like this, right, and I have to map according to the given contour. So this is the first contour, second, third and fourth. Okay, so you don't have to solve because you don't know. I have not explained you about the mapping and all those things, so I will solve directly. So in the first case, right, I will quickly write the f of s. F of s is 1 by s plus 1 into s plus 3. Okay, so it is s plus 1 into s plus 3. Now what will be the mapped contour? Now I have explained, right, 3 points I have told you. So if a pole lies inside the previous contour, that means in the new contour that direction will change. And I forgot to tell you that how many contours we will get. How many contours we will get? The number of poles or zeros that lies inside the contour is that many amount of contours we will get in the new fz plane, in the mapped plane. So I have 2 poles that is inside the given contour. So I will have 2 contours on the map plane, and both of those contours will include 0. Sorry, but yeah, we'll include the origin, not 0. We'll include the origin. So my contours will be something like this. Okay, roughly my contours will be something like this. Both of them will include origin because both of them are inside the previous contour. Now, what was the direction of the previous contour? Clockwise. And what have I told you? If I have a pole inside the contour, that means in the new contour, the direction will be in the anti-clockwise direction. Okay, this is in the same point. So somewhere they will touch. Okay, roughly it will be like this. This will be the mapped contour. Now let's solve it for the like second part. Second part, I observe that only one pole is lying inside the contour. So I will only get a single contour. And what will be the direction of the contour? Now this is clockwise. Okay, in the part B this is anti-clockwise. So the direction of the contour again will change. It will be clockwise, and I will get a single contour. And as one pole is lying inside the contour, that pole, hence I will cover the origin as well. And direction will be in the anti-clockwise direction. Okay, let's move on to the third contour. So in the third contour, what do I have? I don't have any poles of 0 lying inside the contour. So the mapped contour, right, will get a contour. Okay, but that contour will not include the origin. Okay, and direction of that contour will be same as the previous contour, that is in the clockwise direction. This is in the clockwise direction, so this will also be in the clockwise direction. Even if one pole is inside the contour, right, then that the contour calculations will be due to that pole. Don't worry, this is not like this will not come. Just few basic things I have to explain before coming to the main Nyquist plot. Okay, don't worry, this is not that important. Okay, I will explain. I will say to you which is important and which is not important. Now, if my
contour is on a pole, if my contour is on a pole, right, then on the mapped function, actually I will get a function something like this. It will be something like this. It is like it will not be a contour anymore. Why it will not be a contour? I will prove it to you why it will not be a contour. So what I am saying, that my contour is passing through this, right? What is a contour? Contour is the values of the S-plane for which I will map. That is a contour, right? This is how I am varying my S, and according to that I am getting a mapped function. Now in this point, right, at this point, like my function is what? My function is this, right? S plus 3. And at, like, what is this value? This is S equals to minus 3. So at S equals to minus 3, if I put f of s, right, what will be f of minus 3? It will blow up. It will blow up, it will be infinity, because I have a pole at that point. Exactly that is what I am showing. So these points, right, these points are actually what? These points actually tell me that this is, right, some, if S is very near, if S is very nearer to minus, this will be not minus, this will be, yeah, minus 3.00001, something like this. Why? Because if you put minus 3.001 in this f of s, right, what you will get? This will be minus 0.001 into, this will be something negative, right? Something negative. Negative will be positive. This will be a very large number. Very large number. You can choose even smaller numbers like 0, 0, 0, 0, 1, and here, right, at this point the s value will be minus 2.999999, something like that. Okay. So if you understand this, great. If you don't, like, you can ignore this, but I think in the coming years GATE can frame a question from this mapping theorem. Okay, so that is how we get, that is the reasoning behind why are we getting infinity. Okay, so like this you can plot, all those things you can do. This was the basic overview about mapping of functions. Now I will discuss about the principle of argument. What is principle of argument? So if there are p number of poles and z number of zeros that are enclosed by any randomly selected contour in the S-plane. So until now I have not told you any like formulas or something. Now I will tell you about formulas. So p is the number of poles inside a contour, and z is the number of poles, number of zeros enclosed by a contour. Okay, I hope now you understand all these words. By any randomly selected contour in the S-plane, then the corresponding plane will encircle the origin n times. Then the corresponding plane will encircle the origin n times. N amount of times it will encircle the origin. Okay, so this is a formula. This is the the conclusion that I want to come to. I hope now bit of mapping and all those things I have explained. Now main thing is this n equals to p minus z. What is the visual significance? How did it came? That I wanted to explain, because many teachers directly start, your Nyquist plot directly starts from here. Okay, I have given you some foundation. Okay, so then what does this formula mean? This formula means if p is the number of poles lying inside the contour, okay, and poles of what? Poles of the mapped function. Z is the number of zeros lying inside the contour of the mapped function, and these are all values of S-plane. Okay, then n will be equals to p minus z, where n is the number of encircle about origin. About origin means how many contours, how many encirclement I will have about the origin. Okay, so this is told, this is given by this formula. Now again, as I have told, right, if the pole, what does pole do? Pole actually reverses the direction of the contour, correct? If initially my contour was in the clockwise direction, then in the mapped contour the direction will be anti-clockwise. So that's why it is written direction will be opposite of the given contour, because I'm writing p minus z. So if I have more poles than zeros, then ultimately net I have more poles and zeros inside the contour. That means the mapped contour will change its orientation, because the pole, domination of pole is there. If the number of zeros is more, that means domination of zero is there. So what does zero do? The zero doesn't change the direction. That's why what will come ultimately, let's take a few example. Let's say if p is 1 and z is 3. Okay, so z means number of zeros is more inside the contour. That means zero domination is more. So ultimately n will be come out to be minus 2.
But what do we mean by minus 2? Minus 2 means minus 2 is the number of encirclements about the origin. But obviously number is a positive, right? Number of encirclements about the origin has to be something positive. So if it has to be something positive, the negative sign represents the direction. So whatever direction I had chosen, right? Whatever direction chosen, that will be opposite. So what do I mean? So this formula is written for the direction opposite to the given contour, but I am getting minus sign. So I am taking one opposite, then again I have a minus sign. So ultimately it becomes in the same direction as contour. It is same as writing minus of minus 2, because already I have given a minus sign due to this opposite, and then again I am writing in minus 2. So ultimately it becomes plus sign, plus of 2. So same thing here only. So ultimately initially we derive the formula as whatever output I will get, that direction will be opposite. But as I am getting negative, that means again I have to take another opposite, and opposite of opposite will be in the same direction. I hope you understood this point. So ultimately it will be in the same direction of the contour, okay, of the given contour. So I hope you have understood this point. Now if my P is equals to 3, P is equals to 3 and Z is equals to 1, then what does N come? N comes as 3 minus 1, that is 2. 2 is what? 2 is the encirclements about the origin. And in what direction? Direction is already defined. It is opposite to the given contour. Now it will be opposite to the given contour, as there is no minus sign with it. If there was some minus sign, that means I have to take opposite twice. First according to the initial formula, then again negative due to the opposite sign. So I have to again opposite. So opposite becomes same. I hope you have understood this point very well. Okay, so I hope this formula right now is into your head, how this formula came and what is the actual meaning. Obviously I don't have time, so I cannot prove everything, but still I have tried to give my best. Now obviously that is what I have meant here. I've written it only that if P is greater than Z, then, and if N is positive, and if your direction of the previous contour is clockwise, then obviously your mapped contour will change its direction. If Z is more than P, then your mapped contour will not change its direction, and same cases have been written. So let's again solve few questions. Map the following contour in f of s plane. So now can you solve it? Okay, I have given you few formulas. Now can you pause the video and solve these 4 questions? Now I will solve. Okay, so first I will take the function f of s equals to s plus 3, s plus 3, s plus 2, s plus 1. Okay, so now if I want to map this, right, what is P minus Z? P minus Z is 1, because number of poles is 1 inside the contour and number of zeros is 0. So I will get a contour that will encircle the origin. What will be the direction? Direction of the contour will be in the anti-clockwise direction, because it is coming positive. Here again, what is P minus Z? If I do P minus Z, I will get 2 minus 1, that is 1. So here the direction of, I will get a single encirclement about the origin, and what will be the direction? Direction will be in the anti-clockwise direction. Again, number of poles is more than the number of zeros, so it will be again in the anti-clockwise direction. Now here the initial contour is clockwise. How many poles I have? 2. How many zeros I have? 0, so it will be 2. So now I will have 2 encirclements about the origin. So it will be something like this. Okay, something like this. Obviously I am not drawing it exactly, it will differ, but roughly it will be like this. There will be 2 encirclements about the origin. Okay, so and what will be the direction of those encirclements? Both of the directions will be in the anti-clockwise direction. Why? Because the initial mapped contour had a clockwise direction. Now here again, what is P minus Z? P minus Z in this case is 0 minus 1, because number of zeros is 1, so it is minus 1. So I am getting a negative sign. That means the direction that I am supposed to get, I have to oppose it. So it will be in the same direction of the contour only. So what is the direction of the contour? Is clockwise. So direction of the mapped contour also will be in the clockwise direction. Okay, and number of encirclements of course will be 1, as I have written. Okay, now if the below closed contour is mapped into f of s, where f of s is this, then like what they are asking, when the closed contour is mapped into f of s, then the number of encirclements about the origin of the new mapped contour is 0. So you have to solve this, like this is a statement based question, like this can come as a MSQ. Okay, so what they are telling, just hold on, what they're telling is that I'm mapping this, like mapping this contour into this fz plane. Okay, f of s plane, sorry, f of s plane. Now this is the statement. They are telling me that the number of encirclements around the origin of the new mapped contour is 0. Then which of the following options or statements are correct? So when it can happen, when can it happen that the number of encirclements about the origin is 0, that is p minus z is 0? When can it happen? Actually, it can happen then when p is equals to 0, p is equal to z, right? Because p is equals to n minus z, p minus z. So p is equals to p minus z. So number of encirclements is 0, that means p is equals to z. So this is the information that I know, that number of poles must be equal to number of 0. But here, right, what I see, that I have three zeros and I have 2 poles. So what guess I can make? If the number of poles has to be equal to number of zeros, what is this p and what is this z? This p is the number of poles inside the contour, right? Inside the previous contour, old contour, and this z is also this z is also the number of zeros inside the previous contour. They are not the number of poles and zeros of the mapped function. They are not that. They are just the number of poles or zeros inside the mapped contour. I can comment that the number of poles inside the mapped contour will be equal to number of zeros inside the mapped contour. This I know. So what they're telling me, all the poles and the zeros lie inside the contour. All the poles and the zeros lie inside the contour. Is it possible? If all the poles and zeros lie inside the contour, then what will be my number of encirclements? How many poles I have? Total number of poles is 2. How many zeros I have? Total number of zeros is 3. So n will be equals to 2 minus 3. So it is minus 1. So total I have minus 1 encirclement, but in the question they have told me I don't have any encirclements about the origin. So not possible. There are 2 zeros and no poles inside the contour. Is it again possible? No, again it is not possible, right? Because your n is p minus z, and they're telling me that I don't have any poles inside the contour, but I have 2 zeros inside the contour. So it will be minus 2. Okay, here all the zeros cannot be inside the contour. Now this statement is absolutely 100% correct. Why? Because if all the zeros are inside the contour, right, then I need 3 poles, because ultimately n has to be 0. If z is 3, then p also has to be 3, but only at maximum value of p can be 2. So of course all poles of all the zeros cannot lie inside the contour. This is absolutely correct statement. If all the poles lie inside the contour, then 1 zero must lie outside the contour. Again, this is again absolutely correct statement. Why? Because if all the poles are lying inside the contour, then my p is 2, then my z also has to be 2, right? So if z also has to be 2, that means I have 1 extra zero left, and that has to lie outside the contour, and that is exactly what is written in the statement. So option C and D will be correct for this question. Okay, so like these type of MSQ can be framed from mapping theorem. Trust me, this type of MSQ, simple MSQ, right? And you will not be able to answer this, because you just have understood this formulae, p equals to n minus z. You haven't understood the actual concept behind it. Of course, I don't have enough time to explain you the mapping theorem, but I have sufficient time to explain you the conclusion of the mapping theorem. That is also very, very important. If you know that, that is also enough for GATE examination. Now like here, right, bit of summary is given about the mapping theorem. N is equals to p minus z, number of encirclements about the origin. All these things are, like I have already explained to you all these things. Now there is another way to find the number of encirclements from mapped contour. One thing is, just you can directly see like how many contours I have about the origin, or you can draw a straight line from the origin and just see how many times that straight line is getting cut, except this intersection point. This cannot be the point, right? This cannot be a point. This is not valid. This is not a valid point where the contours are intersecting. I will not choose that straight line. I will choose the other straight line where the contours are not intersecting. Okay, so I will choose that straight line and I will check how many times this straight line is cutting the contours. Here I can observe it is cutting twice, so I will have 2 encirclements about origin. That is what is n, right? So from like this also you can understand, or by just watching, seeing like I have two circles, that means I will have two encirclements, that also you can see. That is what is written in this text. Okay, same thing is written. Okay, now there is small difference between enclosement and encirclement. So enclosement means like here, right, if I'm varying my omega from omega equal to 0 to omega equal to infinity, and this is like a mapped function. If you remember, this is a polar plot of a famous map function, right? Now by enclose, what I mean is like this is tending towards infinity, right? This tending towards infinity. So by enclose, we mean that this A point is getting enclosed by this curve, but this B point is outside. Although this is not a closed curve, but still I can comment about this because this enclosed, right? I will use this enclosed term later on. So I can comment that this A is enclosed by this curve, but B is not enclosed. That is just the definition of enclosed. Okay, so like here also I have written, when we vary omega from 0 to infinity, if any point lies to the right hand side of the plot, it is said to be enclosed, and points to the left are not enclosed. So points to the right is enclosed and points to the left is not enclosed. Okay, if any point lies inside a closed curve, then it is said to be encircled. Okay, so that is the difference between enclosed and encirclement. I hope you have understood this point. Now of course, what is that like until now what we have been studying, that is just the mapping theorem, but we have to apply it. So we apply the mapping theorem in this. Okay, because what we know, that we have to check if the poles of this transfer function lies on the right hand side or not. So basically I have to find out the roots of this 1 plus g of h of s, that is also known as the characteristics equation. So if poles lie on the right hand side, then it will be unstable. So I can do few modifications. I can write g of s into h of s equals to n naught divided by d naught of s, that is numerator upon denominator. So this is my initial function. Now I need to find out this, right? I need to find the roots of this. So if I write this as 1 plus g of h of s, now this will be my mapped function. What will be 1 plus g of h of s? So 1 plus g of h of s will simply be 1 plus n naught of s divided by d naught of s. Okay, that is equals to d naught of s plus n naught of s divided by d naught of s. Okay, so I need to find out like this. I need to equate these equals to 0. Correct. So what I observed is that poles of 1 plus g of h of s is equals to open loop poles d of s, right? This is the OLTF and this is the 1 plus g of s h of s. So the poles of these two equations are same, that is d naught of s. But the zeros of 1 plus g of s h of s is equals to the closed loop poles. This is my closed loop pole, right? This is my closed loop pole. So please remember these things. Now it is very, very important. Remember the zeros of 1 plus g of h of s, that is d naught of s plus n naught of s, that is 1 plus g of h of s, because when this will go to 0, right, that means this will be equal to 0. If this is 0, if this is 0, that means this is equal to 0. So the zeros are same as the closed loop poles of this particular equation, and the poles of 1 plus g of h of s is same as open loop poles. I have described visually, I have told you. Okay, so like I can simplify this transfer function as well. So if I simplify this transfer function, like I can directly observe that this will be equals to 1 plus g of s h of s equals to g of s divided by 1 plus g of s divided by 1 plus, this will be n naught of s divided by d naught of s, and this, right, I can further write this as d naught can go at the top, but I don't care about zeros of the transfer function. I only care about the poles of the transfer function. This will be n naught of s plus d naught of s. Okay, so
Of course I can see, right? This is the roots, right? I need to find out the roots of this transfer function. Roots will be poles, and in that just the top expression I have proved to you as well that this is equals to 0. So zeros of 1 plus u of h of s is actually poles of my closed loop system. Okay, so why is it so important? Now it is important because from OLTF we will be able to comment about the stability of CLTF using the mapping theorem, and that is exactly what we do in Nyquist stability criterion. Okay, so that is what we do, because whatever we have done, right, these are all OLTF. These are all equations of OLTF, correct? This is also OLTF. Okay, so with the help of OLTF I want to discuss about the closed loop stability. So first of all, what we do, first thing, in the starting of this lecture, what I've told you, that of course we have to choose each value of s, right? S equals to all the values, all the positive values of s. S equals to 0.1, s equals to 0.2, and then 2, s equals to 1, s equals to 3, and so on. All the positive values of s. Okay, so we have to choose those. So what we do, we are very smart. So what we did is, we of course covered the whole imaginary axis, and this is a huge semicircle with infinite radius. Why infinite radius? Because why is it semicircle? Because I only want to cover all the values of s on the right hand side. So like I'm at this point. Let's say this point is 1 plus j. Then I'm at this point. This point is 1 minus j. Frequency can be negative, but all the real part, right, this will be something 3 plus 0.5 j or something like that. So frequency, like all the x values will be always positive. So I'm covering the whole right hand side, and this is the Nyquist contour. This is also known as the Nyquist contour. Why? Because I want to check for all positive values whose positive real portion of s is like, sorry, I want to check for all the right hand side values of s plane. Okay, all the positive values of s plane, so that if any of those values are satisfying my, like if any of these values are roots of my CLTF, that means like my system will be unstable. That is what we want. That's why the Nyquist contour is chosen like this. I think this was also new to you, that why we choose Nyquist contour like this. The reason being that I want to have all the positive values of s, positive real values of s. That's why Nyquist contour is chosen like this. Okay, so Nyquist contour is generally chosen in the clockwise direction. If nothing is mentioned, you will assume Nyquist contour to be clockwise direction, but it can be in anti-clockwise direction as well. It can be in clockwise direction as well. There is no boundation to the direction of Nyquist contour. Okay, so coming back to our point. So our point was this. This is my, what we do is, we tell that this is my mapped function. Okay, this is my mapped function. Now I know in the mapped function, what I can say, that if p is the number of poles of f of s inside the Nyquist contour, okay, p is the poles of the f of s inside the Nyquist contour, and z is the number of zeros of f of s inside the Nyquist contour, then what will be my n? That is the number of encirclements about the mapped contour. It will be p minus z. Now what is p actually? P is the poles of f of s inside the Nyquist contour. P is the poles of f of z inside the Nyquist contour. And what is the poles of f of z? Do you remember what is the poles of f of z? Poles of f of z, that is this 1 plus j of h of s, is the open loop poles. And open loop poles are very easy to find. Okay, you can easily find out open loop poles. So this is actually talking about the open loop poles. Open loop poles. And exactly what type of poles? Exactly what type of poles? Open loop poles inside the Nyquist contour. That means open loop right hand side poles. Why? Because my Nyquist contour is on the right hand side of the S-plane, right? All the positive real values. So here also, if a pole is lying inside the f of s, that means it is a right hand side pole. Okay, so p is this value. Now what is z? Z is the interesting thing. Z is what? Number of zeros of f of z inside the contour. That means it is the number of right hand zeros, because my initial contour, right, was right hand side, so it is right hand zeros. And what is zeros of f of s? Zeros of f of s actually is equals to the closed loop poles. Closed loop poles. So ultimately, like indirectly, it is telling me that it is poles, closed loop poles. Closed loop poles. Okay. So like this, I can comment about absolute stability. Directly from the open loop poles and the Nyquist plot, I can directly comment about the closed loop poles. That's why it is so fascinating, and that's why it is so important. So if your system is stable, that means z should be equal to 0. You should not have any right hand poles. If you should not have any right hand poles, that means right hand zeros of f of s, that is the mapped function, should be 0. That means then this result comes up as n equals to p. Okay, and direction is given as such. So this was basically, this is all. This is the main thing, the most important slide. Of course, I will summarize it at the end. That is written at the end. Few more points are there, but the most important point is written over here. Okay, in this slide. That's it. Okay, this is it. Just one slide is for Nyquist plot. Okay, that's one slide. Next, obviously, we'll draw a few Nyquist plot. We'll understand the drawing as well. But for now, this is the most important part. So what is written? For closed loop stability, we want z equal to 0, that is zeros of this equal to 0. That means the contour in the 1 plus g of h of s plane should encircle the origin p times in the counterclockwise direction, because Nyquist plot will be in the clockwise direction for my system to be stable. Like there are many things saying the same things. All these things are saying the same thing. Ultimately, your system has to be stable. That means your n has to be equals to p. Now, whichever way you want to say, in terms of word or mathematically, you can say. Now there is another special case, that if my poles, number of poles on the right hand side is 0, basically none of the poles are actually inside the contour, inside the Nyquist contour. If none of the poles are inside the Nyquist contour, that means my p is equals to 0. So for closed loop stability, then the actual like equation becomes n has to be equal to 0. That is, I don't have any encirclement about the origin. Okay, that is what Nyquist contour tells us. Now one more thing we do, one more basic thing we do, what we do is we actually, because what was our function fz, what was a mapped function? Mapped function, if you remember, it is this is my mapped function, right? 1 plus g of s h of s. Now plotting this, right, is difficult. What we used to plot, g of j omega into h of j omega. This is what we used to plot, the real part and the imaginary part. We didn't plot this one, if you remember, in the polar plots. So what we'll do is we will convert this. Okay, we will convert this. If I map this here, right, if I map this, now actually we will plot this one, because plotting this one will be very difficult for us. So when I will map from 1 plus g of s into h of s to g of s into h of s, what will change? So initially this point was here, right? It is x equal to 1, y equal to 0. Then what will happen here? For this x equal to 1, y equal to 0, I was getting a value 0. I was getting a value a. Okay. And let's say this a value, for now, let's say this a value is 1, right? Sorry. This is not x equal to 0, 1. Sorry. This is not x equal to 0, 1. Sorry. This is equals to, this is the real portion of 1 plus g of h of s, and this is the imaginary portion of 1 plus g of h of s. Now, if I want to exactly plot this a point here, what will happen? From the real portion, 1 will be subtracted. Why? Because this, right? What will be real of 1 plus g of h of s? Let's say currently, like the real part of 1 plus g of h of s is 1. Okay, real part of 1 plus g of h of s is 1. And let's say this value is something, some complex number, x plus iy. Okay, so what will be the real portion then? It will be 1 plus x plus j y, real part of this. So real part will only include this one, right? It will ignore the y part. So ultimately it will be 1 plus x. So 1 plus x will be equals to 1. So x is equals to 1. Okay. This is the actual value of this. X is what? X is what? X is basically x is equals to real part of g of j omega into h of j omega. That is what my x is. That is what my x is equals to. Correct. So x is equals to this real part of j omega and into like h of j omega. Okay. So ultimately my x is 0. So here, right, the same a point in the g of s h of s will be mapped to 0. Okay, it will map to 0. So what about the other points as well? And what about the imaginary part? What about the imaginary part? Imaginary part will not change because I am not messing with the imaginary part. I can prove it to you. I can prove it to you. What will be the imaginary portion? Imaginary portion, okay, sorry for the white background. Imaginary portion here, right? Imaginary portion of 1 plus x plus iy. Previously it is equals to what? It is equals to 0. It will stay. So it is equals to 0. So this left hand side will be, this is all real, this is the imaginary portion. So it will be y will be equals to 0. And in the mapped g of h of s plane also it is 0 only. So it is not changing, right? Y is 0 and this is also 0, right? So it will not change. Y value will not change. Just all the x values. Actually, what will happen? All the x values will be left shifted by 1. If I move from this plot to this one, if previously I was plotting 1 plus g of h of s, now I will plot g of h of s. Now you might say, sir, why are you emphasizing in plotting this? Because in polar plots, we have learned how to plot this, right? Imaginary of OLTF and real of OLTF. We didn't learn how to plot this. This also we can plot, but it makes bit complex, task bit complex. So to make our task bit simple, I am mapping this because I know how to plot this one. We have to make our task simple. Now, while making our task simple, one thing got changed. What did change? The origin, which was here, now it got here minus 1 comma 0 point. It got shifted because all the points got shifted by left shifted by 1. Okay, so whatever x values I had, everything will be minus 1. So the origin here will be minus 1 here. Now if, let's just listen to me, if I say that I am encircling the origin in this first function once, then how many times will I encircle in the origin in the second function? Okay, can you tell me in the comments below? बोलो बोलो भाई, comments में बोलो क्या होगा आंसर. ठीक है, it will be once in the minus 1 comma 0 point. If I am encircling in the origin in the first function, then I am encircling in the minus 1 comma 0 point in the second function. Okay, second map function. So origin shifts. So now previously origin was very important because origin used to tell us about the stability in the previous n equals to p minus z. Now origin has shifted. Origin has shifted to minus 1 comma 0 point. Now in the question, right, trust me, when some difficult question will come, they may give you this plot, and then from this plot you have to comment about the stability. So here what will be the value of, like, where you will check what will be the critical point here, right? In this particular plot, in this particular function, the critical point will be origin, but here the critical point will be minus 1 comma 0 point. Here only where the students lose marks, and here only where you don't get the whole concept, because I know you have just learned one formula, n equals to p minus z. You don't know what is n, you don't know what is p, you don't know what is z. Okay, and where it is valid. So GATE, if they really want to trick you, they can give you this plot, because most of the students they just remember for this plot, and sometimes they have tricked you. Okay, it has happened in the past. So you have to remember both of these things. So in this plot, the critical point will be minus 1 comma 0 point. In this plot, the critical point will be 0 comma 0. Why am I repeating? Why am I emphasizing so much? Because this is the most important portion of this lecture. Okay. So origin in 1 plus g of h of s plane is equivalent to minus 1 comma 0 in g of s h of s plane. Okay. Exact same thing is written. So now, like one formula I can tell you, if you like, if you can relate this formula, that will be very good for you, because sometimes they have asked this question as well. if the number of encirclements about the origin of 1 plus g of h of s plane is equals to n1, and then the number of encirclements about the minus 1 comma 0 point will also be same of what, of g of s into h of s plane of this plane. Both of them will be same, both of them, let me write this, will be equals to n only. Okay, now if I have some random transfer function, if I have some random transfer function a plus b into g of s h of s, because this has came in examination, if this is my mapped function, and if I know the number of encirclements about the origin of the map function is equals to n, then can you tell me what will be the number of encirclements? Tell me in the comments below. Now what will be the critical point, what will be the critical point of g of s h of s? If in this case the critical point become -1, then what will be the critical point of g of h of s if my mapped function is a plus b g of s h of s? If my mapped function is this, then basically the critical point, right, will be equals to this number of encirclements will be equals to same as the number of encirclements about the critical point. And what is the critical point? Critical point will be minus a by b comma 0. Imaginary portion will not change because whatever I have multiplied, all real components I have multiplied. Okay, it will not mess up the imaginary portion. So this side, obviously there is a derivation, this I have taught in my full course, we don't have time, so I am directly writing this thing of number of encirclements about minus a by b of which plane, of g of s h of s plane, because this is what we'll plot. Now how can they twist? Basically they will give you this information, now you have to tell this information, like it will be asked in the question, but you will not understand the question itself, because if you don't know the concept. So critical point will change, critical point will become minus a by b. This I hope you can remember, because I have derived, we don't have time for derivation. Okay, so all these things are same thing, only whatever is written, these are the same things. Okay, whatever written. So this is the main summary, and this is the most important slide. Okay, like the previous slide only. So n, right, n will be number of encirclements in the opposite direction of the Nyquist contour about origin. This was the initial formula that I had derived for 1 plus g of h of s plot, or 1 plus g of h of s plane. Okay, now this same critical point changes to minus 1 comma 0 in g of h of s plane from this to this. Okay, and this pc is what? Pc is the number of poles of f of s in the right hand side of the plane, because my Nyquist contour is on the right hand side, it has to be inside the Nyquist contour, which is also equals to number of open loop poles on the right hand side of S plane. This I have told you previously. And what is ZC? ZC or Z plus also I sometimes write this as Z plus, because sometimes it is easier for you to understand like Z plus. Okay, so this is equals to number of zeros of f of s h of s 1 plus g of s in the right hand side. Okay, and this is equals to number of closed loop poles. That is what we need to find out. We need to find this one out. Okay, so like I will also summarize this later on as well, but this is the most important portion. So like all the stability functions are written over here, I will skip it for a second. So there can be many types of Nyquist contour. Generally this is the default Nyquist contour. Of course I have told you that we will not pass through any pole, right? Our Nyquist contour must not pass through any pole of OLTF. If it passes through the pole of OLTF, right, then there will be problems. Then it can blow up, right? Then it can blow up. I have told you, right, previously as well. If there are no poles in the origin, of course I can go by the origin, no problems, because like ultimately what we map to this g of s h of s, right? We map to this function. If we map to this function, then the poles, right, pole does not change. Pole is this 1 plus st, and this becomes 2 plus st. So I have a pole, right, at s equals to minus, this time there is no pole at the origin. If there was a pole at origin, then there will be problems. So here, right, there is a pole at origin. If there is a pole at origin, we will not take our Nyquist contour through the origin. Why? Because at the starting of this lecture I have explained why. Because our transfer function will blow up, our Nyquist contour will not be able to encircle anything. So it will be like an infinite half circle, right? When it passes through a pole, it is like an infinite half circle. So we ignore that. So here, right, our Nyquist contour is simple. It is a semicircle of infinite radius. So what we do is, our S is a complex number, right, r e raised to power j theta. So there are many curves that are hidden inside. What are the curves? The curves are this, right? First I vary my omega, like you can vary any way you want, but generally what we do, we first vary our omega from 0 to infinity. Okay, this already we have learned in polar plots, but few new things will be there. What new thing? Now after this, right, after I reach this point, then I have my omega is infinity, that is my r is infinity. Okay, in this point my r is infinity, right, radius, it is an infinite half circle, but my theta is varying. Theta is varying from what? Theta is varying from plus pi by 2. Theta is varying from plus pi by 2 to minus pi by 2. Theta is varying from plus pi by 2 to minus pi by 2. So in the clockwise direction, that's why. Okay, so then S is equals to r e raised to by j theta. First I will vary my omega, then I will vary my theta. Theta will vary from plus pi by 2 to minus pi by 2. Okay, then I will vary what? Then I will vary negative omega. Omega will vary from minus infinity to 0. So I have three curves here. Of course I will draw the Nyquist plot for these three curves. Don't worry about it. I will draw all those things. Okay, don't worry about it. Now these are, if I have a pole at the origin, of course I will ignore the pole. Then what will happen is that here, right, I will have four curves. First curve will be this one, positive plus 0 to infinity for omega. That is basically what is happening, that my r is going from 0 to infinity. My theta is basically plus pi by 2. Theta is constant here. Theta is constant here, right? Theta is plus pi by 2. Here theta is again varying from plus pi by 2 to minus pi by 2. R is always infinity. Again this is from omega equals to minus infinity to 0. Here just before 0 I will stop. What am I observing? I am observing this is also a half circle. This is also a half circle of almost negligible radius. So that's why, right, here actually this should be 0. This should not be infinity, sorry. This should be 0. This is a half circle of almost negligible radius. R will tend to 0. Okay, because I have to cover all the points near the origin. So R will tend to 0, and here S will be r j theta, and your theta will vary like what? Your theta will vary from minus pi by 2 to plus pi by 2. Theta will vary from minus pi by 2 to plus pi by 2. So if you have multiple poles, right, like here I have told the same thing only. Okay, and I will discuss how we will plot these curves. So this first curve I know, polar plot. This curve also actually we know it will just be a mirror of the polar plot, mirror image of the polar plot. This will be symmetrical. Nyquist plot will always be symmetrical. Okay, I will explain this. This how to plot, and this one how to plot, I will explain. Don't worry, I will explain. Okay, so like now if I have told you this, that for if I have a pole at the origin, then of course I will ignore that pole, but I will try to cover as much points as possible as near to that origin, right? Now if I have a transfer function like this, okay, can you tell me what will be the Nyquist contour for this? The Nyquist contour for this will be like, if my this is my minus omega n, this is my plus omega n, and this is one of the pole. Of course I cannot touch the poles. Now my Nyquist contour, my contour cannot touch the poles. If the contour touches the pole, then there will be huge problem, huge problem, right? Then my mapped function will blow up, and I don't want my mapped function to blow up. So it will be like this. It will be something like this. Okay, then again I will go to infinity and I will stop here. Okay, so I hope you have understood these points. So these are the things that you need to understand, because in the never ever no one will teach you how to take Nyquist contour. No one will teach you this, but I am teaching you, because someday I am expecting they will ask a good question from Nyquist contour as well. So these are few key points whatever we have discussed. I tell you, in Nyquist plot we vary our frequency for both positive and negative values, that is from omega equal to 0 and infinity. Of course we vary our phase as well, theta as well, okay, because S is a complex number. Nyquist plot describes both absolute and relative stability, because Nyquist plot, inside the Nyquist plot itself, inbuilt we have polar plot. So with polar plot we tell relative stability, so we can discuss about relative stability. Of course Nyquist plot discusses about the absolute stability as well. Why? Due to the mapping theorem, okay. And all these things are there. Nyquist plot will be symmetrical about the real axis. Nyquist plot also tells us about the range of k for which stability. This also we'll understand later on. Okay, so now let's draw few Nyquist plot to understand this concept better. So I have this g of s, h of s, okay. Assume tau 1 and tau 2 are both greater than 0. So let's draw. I will draw the Nyquist plot. So what will be the Nyquist contour? Here I can observe I have two poles at the origin. So of course I will skip the origin, okay, just near the origin. So I will have four curves. This will be my first curve, C1, and in C1 what will happen basically, like my S is, first of all, in Nyquist plot, right, we actually plot, we just don't plot the frequency response because we are talking about absolute stability. We also plot the complex number S equals to R e raised to power j theta, all the possible cases, not just the imaginary cases of S, all the possible cases. So C1 is the place where my S is j omega, that means my theta is constant, that is plus pi by 2, okay, theta is constant, that is plus pi by 2. My R is going from 0 to 0 plus, that is just greater than 0 to infinity, okay, that is how my R is varying. And this is the second curve, C2. So C2, my theta is going from plus pi by 2 to minus pi by 2, okay. My R is going, R is almost infinity because it is half circle, so it is almost infinity. In the third curve, C3, what is my theta? Now, right, I am actually in the downward direction. I am in the downward direction. So ultimately what is happening, my omega is negative. Both ways you can say that, you can say S equal to j omega, where my omega is varying from minus infinity to 0 minus, that means this is negative, that means the angle is minus pi by 2. Or you can say something like this, that my angle will always be minus pi by 2 and R is varying from infinity to 0. Both way works, either way works, okay. This or this, both are saying the same thing. And this is the final curve, that is C4. What does C4 tells me? C4 tells me that R is almost tending towards 0. And how is my theta varying? So first I was seeing from the origin, where I am looking downwards. So downwards means minus pi by 2. Then I am looking upwards, that means from minus pi by 2 I am going to plus pi by 2. So theta will go from minus pi by 2 to plus pi by 2. That is how my theta will vary, okay. These are the curves. Now how do I plot it basically? So I hope you know how to, like this first curve, right, is just polar plot. It is just polar plot, right? So what was the polar plot for this? Now remember few things. This is a type 2 systems. So type 2, in the type 2 system, that means from where I will start from the minus 180 degree. I have taught in the polar plots. I will start from the minus 180 degree. So I will start from minus 180 degree, and obviously I will be at something more negative because order is 4. So my angle is reducing more. So at omega equals to infinity, what will be the angle? Angle will be minus 360. So basically, like, I will not explain. I hope you have learned the polar plot from me. So angle will just keep on reducing. It will go more negative, and obviously gain will keep on reducing. Magnitude will reduce. Okay. So this will be the polar plot for omega equal to 0 to infinity. So this is the curve C1 mapped. This is the curves mapping of, this is the mapping of C1. This is the mapping of C1. Okay. Now what about the curve C3?
Okay, I will solve the curve C3 because that is more easier. Okay, why? Because it will be just the mirror image of the initial polar plot. Why? What we have to do? We just have to replace omega with the negative values. So whatever we have got here, right, I will just make them negative. Negative means the phase will be just opposite. So this will be just a mirror image about the x-axis, about the real axis. It will just be a mirror image about the real axis. Whatever, if you replace here whatever the function, right, you replace here with, instead of plus j omega minus j omega, it will just come out to be a mirror image. It will just come out to be a mirror image. This will be the mirror image. Okay, I will not derive it because in my full course I have derived, but obviously we don't have time, so we would derive it here. So it will be just the mirror image, mirror image. Okay, so this will go to omega equal to 0 minus 2 omega equals to infinity, omega equal to 0 minus 2 omega equals to infinity, not 0 minus, sorry, 0 plus 2 omega equals to 0, infinity plus. Okay, so what about the other curves? For the other curves, right, you actually have to derive the expression. So for curve 2, what was the thing? The thing was that my r is tending towards infinity and my theta is going from plus pi by 2 to minus pi by 2. So in the g of s, h of s, if I replace that limit as r tends to infinity divided by 1 by r e raised to power, like I will just replace s with r e raised to power j theta, right? S is equals to r e raised to power j theta. So j theta whole square into 1 plus r e raised to power j theta into tau 1 is there, then 1 plus r e raised to power j theta into tau 2 is there. Now what we know is r will tend towards infinity, right? If r tends towards infinity, this 1, right, I can ignore. This 1 is very small number if r is very, very large. If r is very, very large, this 1 I can ignore. So roughly, I can roughly say this will be equals to 1 by r raised to power 4, because here I have r square. This will become r into r raised to power 4, and this will be r raised to power 4. This will be e raised to power 4 j theta into tau 1, tau 2. So ultimately your value comes out to be what? If r is going towards infinity, right, ultimately this will be 0, limit as r is tending towards infinity. So ultimately this will be 0, right? Ultimately this will be almost equivalent to 0. So actually what is happening? Actually what is happening is that this expression is equals to e raised to power minus 4 j theta divided by r raised to power 4. So as my theta is varying from plus pi by 2 to minus pi by 2, then my minus 4 theta will vary from minus 2 pi to plus 2 pi. Okay, so what am I getting? What am I getting? So a semicircle covers what? 180 degrees, right? 180 degrees from, sorry, yeah, from minus pi by 2 to, sorry, from plus pi by 2 to minus pi by 2. That is what a semicircle covers. That was the previous semicircle, right? Initial contour. But now I am going from minus 2 pi to plus 2 pi. So this was in the clockwise direction. This will be, I had one semicircle. So as it is 4 pi, so now I will have 4 semicircles. Of what radius? The radius will be tending towards 0. Okay, why? Because this is 1 by r raised to power 4, that's why the radius will be tending towards 0. And what will be the direction? Direction will be anti-clockwise. Why? Because previously contour direction was clockwise. I was going from plus pi by 2 to minus pi by 2. Now I am going from minus 2 pi to plus 2 pi. Okay, so that's why it will be in the
anti-clockwise direction. If you want to understand why are there 4 semicircles, okay, although no one will tell you, trust me, no one will tell you, and someday GATE will give good question on this. So because what is the total angle covered? Total angle covered is minus 2 pi minus of minus 2 pi, that is 4 pi. What is 4 pi? 4 pi is 720 degrees. Divide by angle covered by each semicircle. Angle covered by each semicircle is 180. So if I divide by 180, ultimately I am getting this as 4. So I am covering 4 semicircles. Okay, I am covering 4 semicircles. So I hope you have understood the summary. The summary I will tell, don't worry. Curve 2 has a own summary, I will tell about that. So how will the curve look? How will the mapped function look of C2? Mapped function of C2 will be something like this. I will start from minus 2 pi. Okay, I will start from minus 2 pi. Minus 2 pi is here only, and I will go in the anti-clockwise direction. Okay, anti-clockwise direction, and radius will keep on reducing. Okay, so I will start something like this. Okay, this will be in the anti-clockwise direction, because this is the first semicircle, second semicircle, third semicircle, fourth semicircle. So I'll have 4 semicircles. Okay, and of course the radius will, like, they have all 0 radius, but just to show you I'm showing it to you. Okay, but actually they have all 0 radius. You will not be able to see that. You will not be able to see this direction. Now what about curve 4? In curve 4, something similar happens. So I replace my s with r e raised to power 0 theta. So here, right, my r is tending towards 0. My r is tending towards 0 for the curve 4. If you go back and see, for the curve 4, r is tending towards 0. So again the same thing, I will replace all this r. If r is tending towards 0, right, ultimately this will be converted into r square only. Sorry about that. This will be converted into r square e raised to power j 2 theta. Why? Because if r is tending towards 0, right, this term will not be dominant at all. This will go towards 0. So ultimately I will have only this term left. And here obviously limit as r tending to 0. If r is tending to 0, that means what? This is e raised to power minus j 2 theta divided by r square. That is limit as r is tending to 0. Okay, so this is actually telling us what? This is telling us that the magnitude of this function is infinity. So I will get again 2 circles, because again my theta is varying from, this time my theta is varying from minus pi by 2 to plus pi by 2. But how will my minus 2 theta vary? Minus 2 theta will vary from plus pi to minus pi. Okay, plus pi to minus pi. So if my r is 0, this will be infinity. This will be infinity. So basically this will be raised to power minus j to 2 theta. So yeah, basically again I will get how many semicircles this time? 2 semicircles. Okay, I will not explain why. Of what radius? Of infinite radius. Why infinite radius? Because as r tends to 0, this magnitude tends to infinity, blow up. That's why infinite radius. In what direction? In clockwise direction. What was the previous direction? Anti-clockwise direction. So always direction will change, of course, for a proper transfer function. Okay. Now of course you don't need to remember all this. Like you can do this in the examination hall. Basics you can do. Someday they will ask you a question from basics as well. But there is a method to it. I will explain the method just in a second. So what will be the plot basically? Plot will be, I will have 2 semicircles, of which will rotate in the clockwise direction, right? Because the initial contour was in the anti-clockwise direction. Okay. So like these are the 4 curves that you will see. Most cases this will be the 4 curves that you will see. Okay. So Nyquist contour will contain the polar plot. I hope you know how to draw the polar plot. Inverse polar plot, just the mirror image of the polar plot for the curve 3. Now for the curve 2, that is the anti-clockwise or opposite to the Nyquist contour. Okay, how many semicircles you will get in the direction opposite to the Nyquist contour of 0 radius? That will be equals to what? That will be equals to the order of the transfer function. That will be equals to the order of the transfer function. Now this is equals to what is order? Order is the number of poles. Sorry, not the order. Sorry, not the orders.
sorry, not the order of the transfer function, it is equals to, simply it is equals to the number of poles of the, sorry, number of poles of the OLTF minus number of open loop zeros. Now do remember here, right, I don't have any right hand zero or right hand pole. Okay, I don't have that. Why? Because if you remember, right, I replace here with R j omega. Did I consider any right hand poles or something like that? No, I did not consider, right? So here, right, just few small things but very important things you have to identify. Here nothing is mentioned about right hand poles or zero, simple poles and simple zeros. Whatever poles I have, how many number of poles? So that many number of zero radius half circle or semicircle we will get in the opposite direction of the Nyquist contour. Always we will get in the opposite direction of the Nyquist contour. Why we will get in the opposite direction of the Nyquist contour? Reason being, I have poles here and zeros here, right? So ultimately, always for a proper transfer function, my number of poles will be greater than number of zeros. That means ultimately I will have some, let's say, e raised to power n theta here, and I will have e raised to power e raised to power j m theta. Now ultimately this comes out to be n minus m, right, into theta. So most cases proper transfer function m will be greater than n. So ultimately this whole thing will come out to be negative. So theta reverses the sign. So that is the reason I will get a semicircle in opposite direction of my initial Nyquist contour. Nyquist contour can be in the clockwise or anti-clockwise direction. It can be anything. Okay. Generally it is in the clockwise direction, but it can be in the anti-clockwise direction as well. Just be careful about that. Someday gate will play with these type of small things, okay, of zero radius. So this is one formula that you have to remember. This is also very important, and this is also important. Number of clockwise semicircle of infinite radius, that is the curve 4. This is the curve 4. This will be equals to the type of the system, that is number of poles at the origin. Because if you observe for the last curve, right, what mattered? These all went away because they were tending to 0. Only the poles at the origin left. And what is the poles at the origin? Type of the system. So that is why the type of the system decides the infinite radius, okay, and this, right, will be in the same direction will be in the same as Nyquist contour. Just be careful about the directions, okay. I have explained this, okay. So ultimately what will be the complete Nyquist plot? So for the curve 1, the Nyquist plot was something like this. For the curve 3, the Nyquist plot was something like this. For the curve 2, the Nyquist plot was something like this, right? There were 4 semicircles. Although you will not be able to see this. I am showing it here, but you will not be able to see this because the radius is 0. You will not be able to see this or observe this, okay. Now last curve was this, right? I had this curve like this, okay, and this was in the clockwise direction and this was in the anti-clockwise direction, in the opposite direction of the Nyquist contour, okay. So this will be like this. So now I hope you have understood the whole Nyquist contour and the directions and all those things, okay. So now like again I will come to a summary point. We generally plot the Nyquist plot for g of h of s, and then from there we discuss about the stability. So these two are the critical points. Origin is for what? 1 plus g of s h of s. Origin is not here, okay, and this minus 1 comma 0 point is the critical point for what? This is the critical point for this plane, okay, and this is the critical point for 1 plus g of s h of s, okay. Just you have to remember this. So this tells us what? This from diagram, this is the number of encirclements about the origin of this Nyquist plot, okay. Then what can I comment about this? Now forget everything. What was the initial formula I gave you? If I have some Nyquist plot and the encirclement about the origin of the Nyquist plot will tell me about the poles and zeros inside the Nyquist contour for that mapped function. So currently my mapped function is g of s h of s. So
number of encirclement about the origin will tell me the right hand side poles of the OLTF, because my mapped function is the OLTF, minus the number of right hand side poles of the OLTF. Not poles, sorry, if I said poles, I'm sorry, I meant number of right hand side zeros of the OLTF. This is the first formula that I have told you, right? Remember this. Now what is this? Number of encirclements about the minus 1 comma 0 point. Now this is also a critical point, okay, but this tells me what? This will tell me about the number of right hand side poles of 1 plus OL, okay, because everywhere, like, I hope you remember what is 1 plus OL? 1 plus g of s h of s. I hope you remember, right? This minus 1 comma 0 point in the g of h of s plane is the origin in the 1 plus g of h of s plane. I hope you remember, just 20 minutes back I have told you. So this will give me this number of right hand side poles of 1 plus OL, which is also equals to the open loop poles. Why? If you remember, this was equals to 1 plus n naught of s by d naught of s. So the open loop pole and the this 1 plus g of s poles does not change. So it will be same as p over OL of s. This is why the confusion lies. Okay, these two values will be same. Okay, this is what? This is the closed loop poles, right? This we learned, and this is also equals to what? This is the zeros of the 1 plus g of h of s. This is the thing that we have to find out. Okay, the closed loop poles. So take a screenshot of these two equations. Trust me, we have come through so many variations, right? I have told you the same equation so many times, but every time there were different meanings. But this is the ultimate summary. Ultimate summary. These two equations are ultimate summary, and these two equations will be the most helpful for this topic, Nyquist plot. Okay. Now, how to solve the Nyquist plot problems? If the Nyquist plot is given, then see the Nyquist plot, directly discuss the stability. If the Nyquist plot is not given, then if the OLT, obviously then the OLTF will be given. If the OLTF is given, that means you can directly find the stability through the RH criteria, because that is the easiest. Okay, Nyquist plot is also important, but you have to solve in the examination. If you want to get full marks in the examination, you will choose this method. You will choose the RH criteria. You will choose the RH criteria. Okay, instead of Nyquist plot. Sometimes you get confused. That's why you ignore the Nyquist plot. Now you draw the Nyquist plot, else or you draw the Nyquist plot. I will not recommend this. I will recommend this one. If you don't have any option, then you go with the drawing the Nyquist plot. Okay. So now let us draw the Nyquist plot for a few of the functions, and our concepts will be more cleared. Okay. So of course, first of all, I want to discuss about the Nyquist contour, right? If I am plotting the Nyquist plot, I will first discuss about the Nyquist contour. Nyquist contour is this. Nyquist contour is this. I hope you remember. In this case, right, I don't have to skip the omega equal to 0 point. So simply I have only three curves. This first curve, second curve, and third curve. So this R infinity will discuss about the R0. Even if you forget, right? If you forget that those points, that how many semicircles I will get, how many infinite radius semicircles I will get, that's why I have derived. Because even if you forget in the examination hall, still you will be able to solve the Nyquist plot question, because you know the derivation, you know the concept behind that point. Because educators, what they do, directly teach you that point. They don't derive. Okay. So I have derived so that even if you forget that point, right, still you can do it. So I will do it like that only. So I have only this circle, that is R tending to infinity. If R is tending to infinity, that means this magnitude will tend to 0. So I will have 0 radius circle. How many, I don't care, because anyways in the Nyquist plot I will not be able to see it. So I will ignore that. So ultimately I have to just plot the Nyquist polar plot and the mirror image of the polar plot. That's it. Okay. So polar plot, I hope you know how to plot it. Polar plot for this transfer function is very simple. What is it? At omega equal to 0, it is 1. At omega equal to infinity, it is 0. So ultimately my polar plot will be something like this. Okay. And what about my Nyquist plot? What about my Nyquist plot? Nyquist plot will be something like this.
sorry, not Nyquist plot, sorry, the mirror image of the polar plot. Okay, that's it. That's it. This is the Nyquist plot. That's it. Now from here, can you comment about the stability? Can you comment about the stability? Actually, there will be a zero radius circle like this. Like if you want to show this precisely, right, they will be connected like this. It will not touch the origin. They will be connected like this. Okay, this is how they will be connected. But we don't have to go into the technicalities. Now directly from here, you can directly talk about the stability and all those things. Okay, for the second transformation, again, what will be the Nyquist contour here? Nyquist contour will be different for the second transformation. I'm ignoring this. Nyquist contour will be this, right? Why? Because I have a pole at the origin, so I cannot choose the origin. Okay, so I will have 4 curves now. So due to this R infinity, I will get a zero radius circle, which I will ignore. It is not that much importance to me. And of course, if I'm going from plus pi by 2 to minus pi by 2, that will be from minus pi by 2 to plus pi by 2. And how many, like, will it be from minus pi by 2 to plus pi by 2? No, it will be minus pi to plus pi, because number of poles I have 2, number of zeros I have 0, so ultimately it will come out to be 2. Okay, you can derive it. So that is a zero radius circle which I will ignore. The polar plot you will be able to plot. The polar plot, right, curve 1 will be very simple. Okay, if I put s equal to 0, my magnitude is blowing up, it is going to infinity. But in what angle? At s equal to 0, at omega equal to 0, the angle is minus 90. So I will be lying somewhere around here, correct? Here or here. After that, I have another angle, that is tan inverse omega by 2. That will only reduce the angle. So ultimately, I will go somewhere here, right, on along this line. So ultimately, I will be starting like this. Okay, and I will never cross this minus 180 degree line, because at omega equals to infinity, the phase angle is minus 180. All these have been taught in polar plot. Okay, next is at from omega equal to, like, the what will be the curve 3, that is the mirror image. Mirror image will just be the mirror image, so it will be something like this. Okay, next is this one. Okay, next is what? Next is like the curve 2 is radius 0 curve, right? Radius 0 curve. Radius 0 curve, how many I will have? 2 half circles I will have, right? Why? Because number of poles is 2, number of zeros is 0. So ultimately, and what will be the direction? Direction will be from minus pi to plus pi. Okay, so I will start from here, minus pi, and I will go to plus pi, something like this. Okay, so that is how they interconnect. But of course, in the actual Nyquist plot, right, you will not be able to see it, because it is zero radius. How can you see zero radius? You cannot see zero radius. Okay, so this also is not completely correct, right? This I had drawn previously. Just to show it to you, I had drawn it, but this is not actually correct. What is the correct one? Correct one is this. Okay, so what happened? Correct one is this. This is infinite radius, right? I cannot draw infinite radius. I can just show that, okay, this is infinite radius. So this is not actually a total curve. This is extending to infinity. I cannot show infinity, right? That's why somehow I have to show. So I had shown you straight line, but actually it is dotted. It is not touching. This is not a curve. Okay, so that's why enclosing is very important. I will explain what is enclosing and all those things. So here, right, curve 2 is done. What about curve 3? Curve 3, what is the type? Type is 1, right? So when my R tends to 0, I have only this one that actually is important to me. So I get one semicircle which starts. How is my R varying? R is varying from minus pi by 2 to plus pi by 2. So how will this vary? This will vary from plus pi by 2 to minus pi by 2. So plus pi by 2 is somewhere around here, and minus pi by 2 is somewhere around here. So ultimately, right, ultimately my semicircle will something come like this. Okay, this will be my semicircle, and what will be the direction? From plus pi by 2 to minus pi by 2. So it will be in the clockwise direction. Okay, am I correct? Yes, like this, right? This will not be here, the direction will be something like this. Okay, so now I hope you have understood the whole Nyquist plot. Very simple, very easy. Okay, of course we will discuss about the stability, don't worry about the stability. So just let's do few questions on Nyquist plot, then I will discuss about the stability, and of course we will discuss about the stability. So this is the first question. Origin of 1 plus g of h of s plane correspond to which point in the minus 2 g of s h of s plane? Okay, so this is just a mapping, right? So if you remember, origin of 1 plus g of h of s will correspond to what in minus 2 comma g of h of s. Okay, so I know 1 plus g of h of s. What is the origin point? Origin point is where the real and imaginary parts both are equal. Okay, both are 0, sorry. If I just discuss about the real part, dl will be 0. Okay, so let me assume the g of h of s is equals to, it is a complex number, is equals to x plus iy or jy, whatever you want to say, x plus jy. Okay, anything you want to say. So origin means real part is also 0, imaginary is also 0. So that means my x plus 1 is equals to 0. That means my x is equals to minus 1. Okay, and the imaginary has also be equals to 0, right? G of s h of s, this is equals to 0. That means 1 plus x plus iy imaginary is equals to 0. That means y will be equals to 0. Okay, now then this origin will correspond to which point? So my x and y I have got. So now I will just write minus 2 plus g of h of s. For some, this is for some s equal to s, some point, right? S equal to p or some point, some value, s equals to some value. My g of h of s is this x plus jy, because g of h of s will be a complex quantity. So for that same s equal to value, where will I map? So this will be equals to minus 2. My x is what? This will be x plus jy. So this will be minus 2 plus x is minus 1 plus jy. Jy is j0. This will be equals to minus 3. Okay, and imaginary part is 0. So ultimately, to answer the question, origin at 1 plus g of h of s will correspond to minus 3 comma 0 point in the minus 2 g of h of s plane. If you ever tend to get confused in this question, just solve with basics, you will never go wrong. Okay, just solve with basics, you will never go wrong. Okay, so now let's solve this question, right? Pause the video and try to solve all the, draw the Nyquist plot and try to solve the questions, the stability questions. Let's solve this question. Find the number of encirclements in the minus 1 j0 point and the direction of the complex g of s h of s plane by the Nyquist plot of g of h of s if the Nyquist contour is taken in the clockwise direction. So they have mentioned the direction of Nyquist plot. Okay, so these are my g of h of s, and I will first plot the Nyquist plot, and then obviously I will discuss about the encirclements and all those things. So if I observe that I have a 0 at s equal to 2 and I have a pole at s equals to 4. Okay, so then of course my Nyquist contour will be something like this, right? Because I don't have a pole at origin. I don't have a pole at origin. If I don't have a pole at origin, this will be something like this, right? In the clockwise direction. Okay, and what I can see is this is this is the 0 at s equal to 2 and this is the pole at s equals to 4. Okay, and you will directly write in quick succession, in hurry, that n is equals to p minus z. So it will be pole minus number of poles inside the contour, number of zeros inside the contour, that is 0. So 1 minus 1, that is 0. So you will say number of encirclements will be 0 in a hurry. But have they asked that? What is this? This is number of encirclements about origin, correct? About origin. But what they have asked? They have asked the number of encirclements about minus 1 comma 0 point. How will you find out the number of encirclements about minus 1 comma 0 point? So what you have to do is, if they are asking about minus 1 comma 0 point, plotting the Nyquist plot for this, right, will be a bit difficult. Why? Because I have a minus s sign. Why? Because this will be r e raised to power j theta minus 2 divided by 4 minus r e raised to power j theta. Now this r, right, is a negative sign. I have not taught you how to solve with negative sign, because the phase will change. Many things will change. Many things will change. So I am avoiding plotting the Nyquist plot. Without plotting the Nyquist plot, can I still discuss about the encirclements of this? Yes, I can. Yes, I can. How? So I have to tell the encirclements of minus 1 comma 0 point, right? So minus 1 comma 0 point in g of s h of s plane is actually same as the origin in 1 plus g of s h of s. That I have taught you, right? I have taught you. So it is same as that. So what I will do is I will change my mapped function. I will write 1 plus g of s h of s. So if I write 1 plus g of s h of s, if I change the definition of the mapped function, this will be 1 plus s minus 2 divided by 4 minus s. This will be 4 minus s plus s minus 2 divided by 4 minus s. So ultimately it comes out to be 2 divided by 4 minus s. So now if the contour will be same, of course, but how many poles or zeros of the mapped function is inside the mapped contour, if inside the contour? Only I have one pole, s equal to 4, right, clockwise. So now my number of encirclements of origin of what? 1 plus g of h of s plane will be equals to what? Number of encirclements about minus 1 comma 0 of what? Of g of h of s plane. Trust me, this much clarity no one will give you. This much clarity no one will give you. No educator will give you. Okay. This will be equals to what? This will be equals to p minus z. Okay. According to this formula, p minus z. So p is what? 1, z is 0, so it will be 1. So 1 will be the answer in this case. 1 will be the answer in this case. Okay. I hope this concept got clear. Again, same I will do for the next function as well. Again, I will convert this to 1 plus g of h of s, because obviously I haven't taught you how to plot the Nyquist plot for this, right? Minus s. And we obviously you don't have to do it as well. This will not come in examination to plot the Nyquist plot, but this question can come in the examination. Okay, just be careful about it. So it will be g of s h of s. So this will be 1 plus 2 minus s divided by 4 minus s divided by this will be 6 minus 2s divided by 4 minus s. Okay, so again the Nyquist contour will be same, because I don't have any poles at the origin. This will be, I will have a pole at s equals to 4 and I will have a 0 at s equals to 3. So now the encirclement about minus 1 comma 0 of what? Of g of s h of s plane will be equals to p minus z, that is equals to 1 minus 1, that is 0. Okay, so I hope you have understood this point, right? We had only we had 3 questions. So this is again in the last one. The Nyquist contour will be a bit different, right? Because Nyquist contour will be something like this. Of course I will not include the origin. Of course I will not include the origin. Okay, so what will be 1 plus g of s h of s? It will be a bit difficult, but still we will do it. It will be s plus 1 divided by s square minus 2s plus s plus 1 divided by s into s minus 2. This will be s square minus s plus 1 divided by s into s minus 2. Okay, So this, right, this is like a complex conjugate poles. So like not pole, sorry, this will be complex conjugate zeros. So actually my Nyquist contour, right, should not, it can include zeros, it can include zeros, there is no problem with zeros. Okay, so where are the location of the zeros? So the real part of the zero, right, will be of minus b, that is plus 1. Like if I just find out the location of the roots, if I just find out the location of roots, minus b plus minus b square minus 4ac minus 4 divided by 2a. So this will be 1 plus minus 1 by 2 plus minus j root 3 by 2. Okay, so this now I can directly solve it, right? I can directly solve it. So this will be rather simple. So how many right hand, like the zeros will be somewhere here, right? And the pole is like one of the pole is here, that is not included in the contour, and other pole is here, that is included in the contour. So number of poles, like number of encirclements about minus 1 comma 0 will be poles minus 0. So this will be uh, number of poles is 1, zeros is 2. So I will have minus 1 in anti-clockwise direction because my contour was in the clockwise. So it will be 1 encirclement about minus 1 comma 0 point about the clockwise direction. Okay, so I hope you have understood this concept. Pretty simple. Now the same concept actually came in examination, gate exam, but very simple concept. The number of times Nyquist plot, this came in gate 2016, very recent year. The number of times the Nyquist plot of g of s will encircle the origin. This is very simple, right? Very simple. You have to directly use the formula n equals to p minus z. Okay, of course there can be variations which I have already taught you, already taught you. Okay, the variations is this. So what is the Nyquist contour for this? Nyquist contour for this, right, will be something like this. I don't have any poles at the origin and nothing is mentioned. By default I will take in the clockwise direction. So how many poles are there? None of the poles are lying in the clockwise direction. Okay, none of the poles are lying in the clockwise direction. I have a 0 in the, sorry, not clockwise, none of the poles are lying in the contour. I have a 0 in the contour. Okay, so it will be 0, number of poles on the contour inside contour is 0, number of zeros is 1, so it will come out to be minus 1. In what direction? In anti-clockwise direction, right? Because Nyquist contour was in the clockwise direction, so this can also be written as 1 in the clockwise direction. So here, right, answer will be 1. If in the question they would have told about the anti-clockwise direction, then this would have been minus 1. Then this many students would not have been able to solve it. They would not have been totally confident. Okay, so like I hope you have understood this point. Now let's come to the like next question. This question came in gate 2009 doubly. The polar plot of a open loop stable system is shown below. The closed loop system will be stable, marginally stable, unstable. How can you comment about the like the stability? Okay, so can you draw the Nyquist plot from this polar plot? Yes, we can. What is the, like, this is of a polar plot of a open loop stable system. Basically they are discussing that open loop minimum phase system they have given us. If it is minimum phase system, all the poles will lie on the left hand side. Okay, I am talking about the open loop poles. Okay, from this polar plot, can you say what is the type of the system? The type of the system is 1, because at omega equal to 0 I am getting minus 90 degree angle. That means I have a single pole at the origin. Okay, I have a single pole at the origin. So that means this is a type 1 system. If it is a type 1 system, then it will be something like this: s into s tau plus 1. Why it will be s tau plus 1? Ultimately, right, it will not be s tau plus 1, sorry. I am starting from minus pi by 2 and I am ending at what angle? Plus pi by 2. So how much angle I moved? Pi. So 2 poles got added, right? All this I have taught in my polar plot. So 2 poles got added. So it will be, I will have 2 poles here. Obviously nothing is mentioned about zeros, so I will assume that I don't have any zeros. So this will be just a constant. This you have to assume, unfortunately. And like this is the polar plot
it's just like this, right? Although it is not a unique representation, you have to assume the like the transfer function OLTF is this. So of course you will not be able to use the Routh because the plot is given, right? Now can you say me what will be the Nyquist plot? One thing I know, if the polar plot is given, the curve 3, remember, is the mirror image about the polar plot. So the mirror image about the polar plot will be something like this. Okay, so direction will be something like this, and curve 2 was the zero radius, which I don't care, okay, because I will not be able to see that. Just connects these 2 points. I don't care about that. Okay, the last curve I care, the infinite radius curve, right? So how many infinite radius I will have? So this is a like order 3 system, right? If R is tending to 0, only this one will be dominant, right? Only the type. I only take care of the type of the system. I don't take care of these 2 poles. So these 2 I can ignore for R tending to 0. That's why I told you, even if you don't remember this points, right, still you can solve with basics. So if R is tending to 0, that is for the curve 4, right? I have told you what is curve 4 previously. So R is tending to 0, this will tend to infinity. And how will my angle move? So I have only single pole at the origin. That means my angle for the Nyquist contour, it goes from, if you remember, minus pi by 2 to plus pi by 2. Here it will come with a negative sign, so it will go from plus pi by 2 to minus pi by 2. So I will have a single half circle. So without mugging up any concept, okay, I solve with basics. Okay, so this will be from plus pi by 2 to minus pi by 2. This have been explained. So this will be from plus pi by 2 to minus pi by 2. Okay, so that is the case, that is the Nyquist plot. So I have drawn the Nyquist plot. Now can you talk about the stability? How can I talk about the stability? If you remember, number of encirclements about minus 1 comma 0 point of the G of S of S plane is equals to number of poles of the OLTF, or 1 plus G of H of S, which is same as the number of poles of the OLTF. This also I hope you remember, minus the right hand zeros. What was the zeros? The zeros was the closed loop poles, right? CLTF poles, right hand CLTF poles. This is what I am interested to find out. So how many times am I encircling the minus 1 comma 0 point? If you see, this is 1.42. So minus 1 comma 0 point, my drawing is not perfect, will be somewhere here. Okay, this will be minus 1 comma 0 point. So if I just draw like a straight line, how many times am I encircling? Okay, how many times am I encircling the sorry, what do I say? How many times am I encircling the minus 1 comma 0 point? I am encircling the minus 1 comma 0 point 2 times. In what direction? In the clockwise direction. What was my Nyquist contour direction? Assumption is Nyquist contour direction is in the clockwise direction, because I am moving from omega equal to 0 to omega equal to infinity according to the direction given here. So Nyquist contour is in the clockwise direction. This is also in the clockwise direction. So n is 2, but in the clockwise direction. So actually n is equals to what? Should be equals to minus 2, right? Why? Because I am getting clockwise direction and Nyquist contour is also in the clockwise direction. If both are same, that means n has to be minus sign. I will not explain this, I have taught previously. So n is minus 2, that is equals to poles, right hand side poles of the OLTF. Question have mentioned it is a stable OLTF. So this will be 0 minus z plus, this is the right hand side closed poles. This is equals to z plus is equals to 2. That means my OLTF is not stable. I have 2 right hand side poles. So it is unstable with 2 poles on the right hand side plane. This is a very good question, and trust me, if your basics are not good, you will not be able to solve this question. Okay, so like that is what I have drawn here, written here, all those things. So the next question is the polar diagram of a conditionally stable system for open loop gain k equals to 1 is shown. Okay, this is the polar diagram that is shown for of a conditionally stable system, because if for the value k, like k will be something like this, right? This will be transfer function will be something like, it will have some zeros and something s. So of course if you do 1 plus g of h of s, right, the characteristics equation will change, of course. Then depending on the value of k, the stability will change. Okay, that is what I meant. So it is a conditionally stable system with k equals to 1 is shown. Okay, the polar plot is shown.
the open loop transfer function of the system is stable. That means there are no poles on the right hand side. That means P plus is 0. Okay. The closed loop system will be stable for what values of k. Okay. So let's check first for this particular polar plot, is the system stable or unstable? Let's first check this. Okay. So if I check, right, if I check, let me draw the polar plot. So here again, this is a type 1 system because at omega equal to 0, my angle is minus pi by 2. First I will draw the polar, like the mirror image of the polar plot, something like this. And as it is a type 1 system, again I will get one half circle whose direction will be opposite in the clockwise direction. Now if I draw a now if I draw a straight line, how many times will it encircle minus 1 comma 0 point? That we have to understand, right? So minus 1 comma 0 point will be somewhere, this is my point minus 0.2, it will be somewhere here, right? So how many times it encircles? I will draw a straight line from here, right? If I draw a straight line from here, this minus 1 comma 0 point, it is encircling here once and it is encircling here again, this one, right? This is in the anti-clockwise direction, this is in the clockwise direction. So ultimately it is 0. So my n comes out to be 0 and my p is also 0 because it is a stable OLTF. So my z also is 0. So for k equals to 1, system is stable. Okay, for k equals to 1, system is stable. So what will happen is that somehow if k is getting multiplied, right, all these values also will get multiplied by k, because currently I am plotting for imaginary of g of h of s into real of g of h of s. Now it is some k into g of s h of s, right? So just a constant k is getting multiplied. What will happen? Simply all the points also will be scaled by k. That's it. All the points will be scaled by k. Okay. So this point will be k. This point will be k. This point will be minus 2k. This one will be minus 8k. Now I have to find out the region of stability. So one region I know, k has to be, like, if k is equals to 1, then the system is stable. That much I know. So this, right, this is also a possible thing. All these are possible. I will check which one is the most possible. Okay. So if I choose my k value, to be equals to 5, I will check for the limiting case analysis. If I choose my k value to be equals to 5, if my k is equals to 5, right, then this point will lie exactly here. So my minus 1 point, if my k is equals to 5, for k, I will just write here, for my k is equals to 5. Okay, just I will solve for k equals to 5. If my k is equals to 5 somehow, then this, right, if I multiply 5, this will become minus 1. So this will be my minus 1 point. So I will draw my straight line from here. Okay, draw my straight line from here. Now this, right, this will not encircle anymore, because this will be just tangent. This will not cut. This point, right, will not cut. Okay. So now how many encirclements I have about the critical point? If now I have the encirclements about the critical point, this is 1. Okay, this is 1. If my k, right, if my k is just below 5, if my k is just below 5, then, right, this, right, will be like my minus 1 point will be somewhere here. Then if I draw this straight line, again it will cut it twice. If my k is just 5, then it becomes tangent. So then my n becomes 1, that is non-zero. So my n must be 0 for the system to be stable. So my k, right, my k cannot be greater than 5. My k has to be less than 5. If k is greater than 5, then my minus 1 point, like, let's take a number. Let's take k equals to 10. If I take k equals to 10, then this number will be what? Minus 2. Then minus 1 point will be lying somewhere here, right? then I will draw a straight line. How many times am I encircling? 1, 2. Okay, it is not subtracting because both are in the same direction, that is in the anti-clockwise direction. So it is not subtracting simply. So it is 2, non-zero. So that means my system will become unstable. Correct? My system will become unstable. That's why my k must lie less than 5. Let's check for the upper limit. If I check for the upper limit at this range or this range, okay, let me check for first this range. This is not the actual point, actually I should delete this. This is not the actual point. Now if my k is less than half, if my k is less than half, then what will happen? Let's take an example. If my k is equals to 1 by 4, if my k is equals to 1 by 4, then what will happen? If my k is equals to 1 by 4, that means this, right, this point will be what? This will be minus 0.5. So my minus 1 point will be lying somewhere around here. Then again I will draw a straight line. Again I am cutting twice, right? N is non-zero. N is non-zero. So again I cannot do it. I cannot do it. My k must be my minus 1 point, right? Minus 1 point must lie here within this 2 points. Minus 1 point must lie here. If my minus 1 point lies here, then only the number of encirclements will be 0. If it lies here, number of encirclements is 2. If it lies here, number of encirclements is 2. That is the problem. I don't want that. My minus 1 point must lie here. So my k, right? So basically my minus 1 point must lie between these two. So my minus 1 point should be less than minus 0.2k. So ultimately my 0.2k must be less than 1. So k must be less than 5. First condition. Okay. Next condition is that my minus 2k must be more or less than minus 1. So my k must be greater than 1 by 2. So this is one of the range. K, it is between 5. K is between 5 to 1 by 2. Okay. Next is like k is between 5 to 1 by 2. Only I can see in this option. So obviously this option will be correct. Let me check for the other one as well. If my minus 1 point is lying here, somewhere here, will I ever cut the circles? No, I will never cut the circles, right? N will be 0 again if my minus 1 point lies here. So minus 1, also there is another possibility, minus 1 must be less than minus 8k. That means my k must be, I am solving inequalities and my expectation is you know how to solve inequalities. Okay, these are all basics. Okay, so this will be k must be less than 1 by 8. This is also another condition which is written in the option. So option B will be correct. This is a very good question. Try to repeat this solution again and you will understand. Now the method 2 is simply solving using route. If you don't like this method, you can solve using route, but for you to solve using route, right, you have to identify the transfer function as well. Okay, you don't have the transfer function, so you cannot solve with route. Okay, so that was basically how you can solve this question. Let's solve few more questions. This is one of the questions. So the Nyquist plot of the OLTF, this does not encircle the critical point when k is 10, but does encircle the critical point once in anti-clockwise direction when k is 100. Then the closed loop system is stable, unstable. How we can comment about the closed loop system? Okay, you can solve this using route. Route is up to you. That is the homework. I will tell you the Nyquist plot method. So it is telling me it does not encircle minus 1, 0 point for k equals to 10. So that means my n of minus 1, 0 is 0. Okay, minus 1, 0 is 0. What it is? It is actually the origin of 1 plus g of h of s plane. Origin of 1 plus g of h of s plane. What it is? It tells us about p plus minus z plus. What is p plus? P plus is the poles of the OLTF. And what is z plus? Z plus is the poles of the CLTF. Okay, so 0 is equals to how many poles I have of the OLTF on the right hand side. If you see, like this is a quadratic, you can simply identify the real part of the pole is negative. Here also the pole is negative. So none of the poles of the OLTF are on the right hand side. So this will be 0. This is 0. So my z plus is also 0. So yeah, for k equals to, this is for k equals to 10, the system is stable. because z plus the right hand side poles is 0. So for k equal to 10, system is stable. This will be correct. Yeah, system is stable. Option B and C. Let's take for the option, last option. So again it is telling me it encircles once in the anti-clockwise direction. Nyquist plot is in the clockwise direction, so it will be 1 equals to p plus, will not change obviously, it will be 0 only, minus z plus. Okay, so your z plus is coming out to be minus 1. Your z plus is coming out to be minus 1. Now is it possible? No, not possible. Z plus can never come negative, not possible. So what went wrong? The thing that went wrong is we assume it to be in the, we assume the Nyquist contour to be in the clockwise direction, but actually the Nyquist contour is in the anti-clockwise direction. Nyquist contour is in the anti-clockwise direction. So what we have to do? We have to change our assumption. If Nyquist contour is in the anti-clockwise direction, so then n is coming out to be 1 in the anti-clockwise direction. So actually the value of n will be minus 1. So minus 1 will be equals to 0 minus z plus. So z plus will be equals to 1. Now I am getting a right hand pole of CL tip, that means system is unstable. Okay, so I told you, right, they will play a trick with you, not giving you the Nyquist contour. You have to assume the Nyquist contour. Okay, so option B will be correct. Unstable for k equal to 100, stable for k equal to 10. Okay, verify with Routh-Hurwitz criteria. Verify this. Okay, that is your homework. Okay, so let's solve the next question. This is the next question. A unity feedback control system is characterized by the open loop transfer function. This one, the Nyquist path and the corresponding Nyquist plot is shown in the below figure. Okay, this time they have shown the Nyquist contour. Okay, Nyquist plot is also shown. What are they asking? They are asking if k is between 0 to 1, then the number of poles of the closed loop transfer function that lie in the right half plane. Okay, again this came recently only. So simply what you can do is you can solve using Routh-Hurwitz, because the OLT is given. You can solve using Routh-Hurwitz, that is up to you, but you can solve using Nyquist contour as well. So they are telling me k is lying between 0 to 1. Okay, let me take the maximum value. If k is 1, so this point will become minus 1 comma 0. Okay, so do I have any encirclements about minus 1 comma 0 point? No, I am just starting from this point, right? So there is no encirclements about minus 1 comma 0 point. So n is 0. Okay, do I have any poles? So this, right, you directly cannot comment about the poles like the Nyquist poles, right? Can you comment about the Nyquist poles? No, you cannot comment about the poles of the OLTF. What are the location of the poles? But you have been given extra information. You have been given the encirclement about the origin as well. So this is the encirclement n minus 1 comma 0 is equal to 0 for k equals to 1. What is the encirclement about origin? Encirclement about origin in this case, right? How many encirclements I have? So encirclements about origin, this is one of the encirclements and this is the other encirclement, correct? So have they given the direction? Actually, I think in the question, right, they must have given the direction as well. I think they messed up in the direction. The direction is missing. So direction will be something like this. Okay, yeah, I think the direction will be something like this. So now if I find out the number of encirclements about the origin, this is one of the encirclement that is in the anti-clockwise direction, another encirclement in the anti-clockwise direction. So this will be 2. This will be equals to what? P minus Z. P is what? Number of right hand poles of G of H of S. Okay, that's why the two formulas are very important. Don't रट्टा मत मारो फॉर्मूले को, समझो कॉन्सेप्ट, उसके बिहाइंड में कॉन्सेप्ट क्या है. ठीक है, मैंने इसलिए इतना समझाया है आपको, इतना समझाया. So it will be P plus, that is what we need to put in this formula, minus Z plus. This is of, so this will be minus zeros of the OLTF. Do I have any right hand 0? No. So that is the secret of this question. That's why this question is very, very good. I don't have any right hand 0. So this will be simply 0. So number of right hand poles, right, is equals to 2. Even though without finding the route, right, without finding the roots of this, I can directly say the number of right hand poles will be 2 from the first equation. Okay, now we'll put this right here. So ultimately it comes out 0 is equals to 2 minus Z plus. So Z plus comes out to be 2. Z plus comes out to be 2. That means I have two right hand side zeros if my k is 1. Okay. Now if I reduce my k, right? If I reduce my k, if I reduce my k, it will be somewhere here. The number of encirclements about the origin will not change. The number of encirclements about -1, 0 will not change. That means nothing will change. The right hand zeros also will not change. The right hand poles also will not change. Everything will be same. That means my system will be stable always if my k is lying between 0 to 1. That is, and how many right hand poles I will have? 2. I will have 2 right hand poles. Now please do this homework. Do this. That is for your own betterment only. Try to solve this using Rath-Horowitz. Like this is like method 2 is I've solved using Rath-Horowitz. Try to solve this. Okay, I've just given the space. You will get the same answer. You will get the same answer no matter what. Okay, now let's move on to the last question. Yeah, this is the last question basically. So here the Nyquist plot of a stable transfer function g of s is shown in the figure. We are interested in the stability of the closed loop system in feedback configuration shown. Okay, so Nyquist plot is shown, and the close like the stability is they are asking. Okay, which of the following is true? G of s is an all pass filter. G of s is impedance. G of s is this. So we are getting what we are getting. We are getting a circle. Okay, magnitude response is a circle. So what is a all pass filter? All pass filter is a filter that passes all frequencies and for which the gain is constant. Okay, gain is constant. So gain of g of s h of s is constant. Is it constant? You will feel yes sir, it is a circle, it is constant. No, what is the magnitude? Magnitude is the distance from the origin, right? Is the magnitude same everywhere? No, for different frequencies the magnitude is varying, so it is not a all pass filter. G of s is marginally stable. G of s is impedance of a passive network. If it was an impedance of a passive network, right, what can be the impedance? Either the impedance can be R, or impedance can be 1 by SC, or impedance can be SL, right? These are passive network. So are they like this? No. Here, right, it will simply be the phase will be always minus pi by 2. Here the phase will be always pi by 2. So no, they are not the impedance of a passive network. Stability I have to check. Stability I have to check. How will I check stability? So what you will do is again you will use the Nyquist stability criterion. So first this is for a OLTF. H of s is 1 here. H of s is 1 here. Okay. So first I will write the number of encirclements about the origin. So they have told me that it is a stable transfer function. If it is stable transfer, if it is a stable transfer function, that is stable g of s. It is a stable g of s. If it is stable g of s, I don't need to find n0, you only need to find n0, 0 when the g of s is not known. But they have told you it is a stable g of s, then only this one will work. N minus 1, 0 will be equals to p minus z. Okay, p plus minus z. So if it is a stable, then p plus will be 0 because none of the poles of the OLTF is on the right hand side of the g of s. Okay, then encirclements, how many encirclements I have? About minus 1, 0.0. So z plus is also 0, so I don't have any poles on the right hand side of my closed loop system. So system is g of s is not marginally stable, it will be stable. So only one of the option is left, so obviously option B will be correct. So what they're telling that g of s has a 0 on the right half plane. How can you confirm this? You can use the first equation, number of encirclement about the origin, that is equals to number of poles on the right hand side of the OLTF minus number of zeros of the OLTF on the right hand side. Number of encirclement about the origin is what? 1 in the clockwise direction. So Nyquist contour, if I assume, have they told us about the Nyquist contour? Although they have not told, first I will assume Nyquist contour to be in the clockwise direction. If I will not get a proper answer, then I will change my direction of Nyquist contour. So if Nyquist contour is assumed to be clockwise, so n should be in the anti-clockwise direction. But I am observing n is in the clockwise direction. That means I'm getting one encirclement about the origin, correct, but it will be -1, okay, because direction is opposite. So it will be -1 equals to P plus, it is a stable OLTF, so this will be 0 minus Z plus. So Z plus is what I need to find out, the zeros of the OLTF, correct. This will be equals to zeros of the OLTF will be equals to 1. That means I have a right hand 0, which is exactly what is written in the second option. So trust me, that's why you get confused in this topic, right? They ask you some basic questions and you will not be able to solve this. Okay, next question, the gain and phase margin. That is very simple, right? How do you find the gain margin? Gain margin is where the phase is -180. Okay, where is the phase -180? Here, right? Here is the phase -180. What is the gain of the transfer function at -180? That is 0.5. So what is gain margin? Gain margin is the inverse of the gain, so it will be 0.1 by 0.5, that is 2. So in dBs it will be 6 dBs. Okay, what about the phase margin? Phase margin is the phase 180 plus the phase at omega gc, where the gain is 1. Gain is 1 here, right? It is cutting here. What is the phase here? Phase is minus pi by 2. So phase margin will be, I will add pi with it, so it will be plus pi by 2. So phase margin is plus pi. Just hold on a second. Minus pi by 2. 180 if I add, it will be plus pi by 2. So yeah, it will be plus pi by 2, which is present in the option C. So option C will be your correct answer for this question. Okay,
let's start with gate PYQs of Nyquist plots. So this is the first question. Consider a negative unity feedback system with forward path transfer function to be this. A, B, C all are constants and positive. All of them are positive. So I see this is my forward path gain. So this is my OLTF, right? Out of which, of course, I see that I have one of the poles of the OLTF to be on the right hand side. So one of the poles of my OLTF is on the right hand side, correct? So P plus, right? I have a formula that is n plus of -1 comma 0 equals to P plus minus Z plus, where P plus represents the poles of 1 plus OL, that is 1 plus OLT, 1 plus G of S. This I have taught, of course, just before this. Or these are same as poles of G of S. No difference, right? But zeros is actually interesting. Zeros is basically are the roots of my characteristics equation. Okay. So zeros of 1 plus G of S is the roots of my characteristics equation. Right? Or poles of my transfer function. Poles of transfer function. Right? So P plus is 1 from this information, because A, B, C all are constant, positive constants. So P plus is 1. For a Nyquist path enclosing the entire imaginary axis and the right half of the spline. So basically my contour is this entire imaginary axis on the right hand side, and this is a valid Nyquist contour. Spline in the clockwise direction. So I'm encircling it in the clockwise direction. The Nyquist plot of 1 plus G of S, I'm plotting the Nyquist plot, encircles of 1 plus G of S, encircles the origin of 1 plus G of S plane once in the clockwise direction. So if it is encircling the origin of 1 plus G of S, now this is interesting, right? So this is correct, but they are not plotting the Nyquist plot of G of S. They are plotting the Nyquist plot of 1 plus G of S. So if I am plotting the Nyquist plot of 1 plus G of S, right, this here I will have imaginary part and here I will have real part. So basically we know the Nyquist plot around the Nyquist plot, the number of encirclements around the origin of this will be what? Number of encirclements around the origin will be number of poles on the right hand side of my function, that is 1 plus G of S, minus number of zeros of my function on the right hand side, that is 1 plus G of S. So this is P plus 1 plus G of S Z plus. Now, yeah, so I can say, so this information is given to me, right? This is already I can see, like P plus of 1 plus G of S would be same as P plus of my G of S. All these has been taught to you. That is one. Now what are they asking? Also they have told me that it encircles the origin once in the clockwise direction. So it is encircling the origin once in the clockwise direction. My Nyquist plot is also in the clockwise. So actually your n value, this should be in anti-clockwise, right? Because your Nyquist plot was in the clockwise, but they are telling me it is encircling origin once in the clockwise. So actually this value will be -1. So p plus is also 1 and minus z plus. So your z plus comes out to be 2. So my zeros of 1 plus g of s on the right hand side is 2. Or I can say the number of roots of my characteristics equation on the right hand side is 2. What are those? And never passes through the origin for a certain value of k. The number of poles of this, what is this? This is my CLTF, right? Closed loop transfer function, lying in the open right half plane of the S plane. So how many number of poles of this is lying on the open right half plane? That is nothing but the zeros z plus, and all this has been taught to you just before this in the R-PYQ video, right? So this is 2. So basically your answer will be 2. I have already calculated it because I knew what are they asking, but like I hope you get the idea. That's why understanding the basics of Nyquist plot is very important, because trust me, if you don't understand what is Nyquist plot, what is p plus z plus, you'll never be able to solve this. So you have to study. So for that your short notes is also given, and of course I have solved few examples and questions as well. I've given you the theory as well. So yeah, let's now move on to this one. This question: the open loop transfer function of a negative feedback system is g of s h of s, that is equals to this. The Nyquist plot for the above system is okay. So open loop, it is asking whether it will encircle -1, 0 point in the clockwise once, twice, whatever, right? So let me first of all say what is my how many number of open loop poles I have. P plus of 1 plus OL, that is equals to P plus of my OL, right? OLTF, basically G of S. So this would be 1, because I see I have one pole on the right hand side. Actually they should have actually there is a mistake here. They should have actually mentioned what is your direction of your Nyquist contour. What is the direction of your Nyquist contour? So by default you'll assume the Nyquist contour to be in the clockwise direction, right? They should actually mention here what is the direction of Nyquist contour. Nyquist contour you will assume by default to be in the clockwise direction. Okay, but actually for the question to be completely correct, they should mention. Okay, so we got this. Now how many number of uh, zeros I have on the right hand side? That is 1 plus g of s h of s. How many zeros? That is equals to 1 plus s into s minus 2. This is my transfer function, right? So I have to calculate the zeros here. I can easily calculate how many zeros I have on the right hand side, because it is simply a second order transfer function. So minus 2s plus 1 equal to 0. So this would be s minus 1 whole square equal to 0. So I actually have s equal to 1, s equal to 1, 2 zeros on the right hand side, and I have a 1 pole. So this will be 1 minus 2. Okay, 1 minus 2, because I have 2 zeros on the right hand side, n plus. So Nyquist, Nyquist, the so if I assume my Nyquist contour to be in the clockwise direction, so it is coming out to be, so it will encircle -1 times in the anti-clockwise direction. It will encircle -1 times in the anti-clockwise direction. So it basically means it will encircle the -1, 0 point once in the clockwise direction. I just have to reverse the clockwise direction. So I'm not explaining every single detail here, because already the theory has been taught to you, right? I'm doing this directly, not explaining the internal things, how are they working, because theory has been explained. So I'm skipping up the theory, how you will actually solve in the exam. That is what I'm showing you after understanding the theory. So please go through the theory here. I'm not explaining the theory over and again. So let's solve the next question. So the complete Nyquist loop, I think this already has been done, has been shown of a open loop feedback system if g of s h of s has 1 0 on the right hand side of S plane. So g of s h of s has 1 0 on the right hand side, basically z plus of g of s h of s, not 1 plus g of s h of s, right? Z plus of g of s h of s, I have 1 0 on the right hand side of g of s h of s. So how many times is it encircling the origin? Because I know this, right? P plus of g of s h of s minus this will equals to n plus, right? If Nyquist contour, again assume your Nyquist contour to be in the clockwise direction. So they have not given me the poles information, but I know 0 I have, right? 1 0 is on the right hand side, so Z plus is definitely 1, P plus I don't know. Now how many times is it encircling my Nyquist my origin? Once in the anti-clockwise direction. So once in the anti-clockwise direction, it is encircling the origin. So which is according to my direction, because my Nyquist contour is in the clockwise. So they should mention the Nyquist contour direction, but that's fine. So this is 1, this Z plus is 1, and P plus is this. So your P plus, right, poles of G of S, H of S is actually 0. So it is actually 2. P plus, P plus is actually 2. Now, how many times? Now, what are they asking? They're asking the number of poles that the closed loop system will have in the right half plane of S plane will be. So again, I can write another formula. That's why Nyquist, understanding the fundamentals of Nyquist is very important. P plus of 1 plus OL minus Z plus of 1 plus OL equals to N plus again of minus 1 comma 0. This was the around 0 comma 0 encirclement. This is the encirclement around minus 1 comma 0. So I see around minus 1 comma 0, I have one encirclement in the anti-clockwise direction. Again, I have another encirclement in the clockwise direction. So overall, how many encirclements I have? One in the anti-clockwise, one in the clockwise. So overall, it is 0 actually. So this would be 0. Now P plus of 1 plus OL would be same as P plus of OL, OLTF, that has been taught to you. So this will be simply 2, that is the information, minus Z plus of 1 plus OL, that is nothing but the number of right half zeros of 1 plus OL or number of right half poles of my closed loop system. So Z plus comes out to be 2. So I will have 2. Okay. Sorry. How many times is it encircling the minus 1 comma 0 point? Once it is encircling in the anti-clockwise, and once it is in the clockwise. Okay. Small mistake. So how many times is it encircling the origin? Once in the clockwise and again once in the clockwise. So don't miss this one, right? There can be silly mistakes. So this is like I'm encircling the origin twice. I'm encircling the origin twice actually. So this will be 2. My bad. This will be 2. So P plus would be 3. So if P plus is 3, this would be 3. So your Z plus would be 3. So your answer would be 3. So 3 would be your answer for the question. Okay, that's how you solve this question. Okay, just hold on, give me 1 second. P plus is 3. Okay, yeah, according to me, yeah, it should be 3. Okay, so let's solve the next question. Taking n as positive for the clockwise encirclement. Now n as positive, n is positive for the clockwise encirclement. So your Nyquist contour would be in the anti-clockwise direction. That is what your Nyquist contour is, right? NC. Otherwise negative. The number of encirclements n around minus 1 comma 0 point in the Nyquist plot of this. Okay. So this is pretty simple. You don't have to even have to plot it. You can plot it, you can confirm it, but let's do it, right? So number of encirclements around minus 1 comma 0, what is it? It is basically P plus of 1 plus OL minus Z plus of 1 plus OL. P plus of 1 plus OL is nothing but the poles of OL. P plus of OL. So number of right hand poles of G of S, that is 1, because I see P plus of OL is 1 because I see one right hand pole, that is simply S equal to 1. So P plus of OL is 1, so this value is 1. Great. What about Z plus of 1 plus OL? So Z plus of 1 plus OL, how many zeros I have on the right hand side of 1 plus OL? So I can do 1 plus G of S, right? 1 plus OL basically 1 plus G of S, that would be 3 plus S minus 1 by S minus 1. So it comes out to be S plus 2 actually. So I don't have any zeros on the right hand side. So this should be 0 actually, right? Okay. Taking n as positive for clockwise encirclement. So again, these questions are wrong actually. like the answer given here is -1, but they should mention that what is your Nyquist contour. Again, by default, if nothing is mentioned, you'll assume your Nyquist contour to be in the clockwise direction, but they should actually mention it, right? They should mention it. What is the direction of Nyquist contour? So this is coming out like this will be, if your Nyquist contour is in the clockwise direction, then your positive, yeah, then your like, no, this is wrong, right? You have to assume Nyquist contour to be in the clockwise direction if nothing is mentioned. Always assume it. Always assume it if nothing is mentioned, Nyquist contour to be in the clockwise. Okay, they should actually mention it. So yeah, here this will be n plus will be equals to 1. But what does it say? It says that it will encircle the -1, 0 point in the anti-clockwise direction once. But they have told me n is taken positive for clockwise encirclement. So my answer would be n equals to -1. Now the honest thing is I'm matching the answers because they have also given -1, but actually they should provide the direction of encirclement of Nyquist contour. This question is again incomplete. They should always provide the encirclement around the origin. Sorry, encirclement of Nyquist contour. So again, similar kind of question is given to us. Consider a closed loop control system with negative unity feedback and kg. So negative unity feedback is there. So this will be 1 plus k into g of s. That will be my CLTF characteristic equation in the forward path where the gain k is set to 2. K equals to 2. This value is for k equals to 2. This Nyquist plot drawn is for k equal to 2. The complete Nyquist plot of the transfer function g of s is plotted. Okay. G of s, this is not for k equal to 2. This is for k equal to 1 actually. The Nyquist plot for g of s, that means k equal to 1 is plotted. Here they have properly mentioned the Nyquist contour has been chosen to be in the clockwise sense. Assume g of s has no poles on the closed right half of the complex plane. So g of s does not have any closed loop poles on the right half plane. That is basically p plus of 1 plus ol, that is p plus of ol is 0. Great. The number of poles of the closed loop transfer function in the right half complex plane would be, basically they're asking me how many number of right half poles I have. So basically they're asking me this, right? 1 plus ol, this is my formula. Ol, that is n plus of -1, 0. They are basically asking me what is my z plus. So I know p plus, that is 0 because I don't have any poles on the right hand side. But what is my n plus? Encirclements around the -1, 0 point. Now interesting point here is this is plotted for k equals to 1. If I make k equal to 2, right, this magnitude, all everything will be just magnified by 2, correct? Everything will be simply magnified by 2. So what I'll do, I'll just do a trick here. So I'll plot the figure will be same, figure will not change basically, but all these values will be multiplied by 2, correct? All these values will be multiplied by 2 because the magnitude has increased by 2. So all these values will be multiplied by 2. So this will become, this will not be 0.8 anymore. This will be 1.6. 1.6. This will not be 0.4 anymore. This will be 0.8. Now here, right? So okay, what is this is 1.6, right? This is 0.8. So my -1 will be somewhere in between here actually. -1 will not be outside anymore. -1 will be here between 0.8 and 1.6. -1 is here. So yeah, so how many encirclements around -1, 0 point I have? One in the clockwise, one in the clockwise, so two in the clockwise direction, right? And my Nyquist contour is taken in the clockwise sense, so n will be equals to -2 because I'm getting clockwise, so n will be equals to -2. -2 is equals to 0 minus z, that is my poles on the right hand side, that is equals to z is equals to 2 simply. So I have two poles on the right hand side of my closed loop transfer function. So option C will be my correct answer for this question. So Nyquist questions can be solved in seconds if you know what that one like formula means. That is the only thing, right? It is like most students don't understand the significance of that formula. The open loop transfer function of a unity gain system is this. The Nyquist contour is encloses the entire right half plane and a small neighborhood around the origin. So basically it will not enclose the origin, because of course we cannot include origin, because our function transfer function is going to infinity, right? We will exclude our origin as shown. This is my Nyquist contour. Okay, so basically it is covering the around the origin on the left hand plane and a small neighborhood on the left hand and entire right half plane. It is okay, so it is covering the entire right half plane. Basically it is covering entire of this plane. Okay, so it is in the clockwise direction. As I can see, the number of encirclements minus 1 j comma 0 by the Nyquist plot of g of s corresponding to this Nyquist contour is denoted by n. So n will be equals to what? They should have also actually should have told what do they mean. So do they mean like clockwise or anti-clockwise? They should have actually told us, but it's fine. We'll assume they're talking about the default case, that is anti-clockwise, because Nyquist contour is in the clockwise direction. So that is n plus minus 1 comma 0 would be equals to there were few options. I don't know if there were options or not. So that would be equals to p plus 1 plus OL minus z plus of 1 plus OL. So p plus is simply equals to number of poles on the right hand side. Do I have any poles on the right hand side? Yes, I have a pole on the right hand side, correct? So this will be no, I don't have any poles on the right hand side. This will be 0. Okay. Okay, but one thing is there, I see basically this p plus, right, tells me how many of my poles are included in my Nyquist contour. So one thing is interesting. So I'm covering a bit of left hand side. So actually this, right, s equal to 0 is included in the Nyquist contour. S equal to 0 is included in the Nyquist contour. That is pretty interesting, right? So basically how many of my poles are included in the Nyquist contour, that is what this represents. P plus of 1 plus OL, P plus of 1 plus OL, because P plus of 1 plus OL is nothing but P plus of OL. So how many poles are included in my Nyquist contour? 1, because s equal to 0 is included in the Nyquist contour, right? It is included. S equal to minus 1 is not included, but s equal to 0 is definitely included in the Nyquist contour. So this will be 1 minus how many zeros of 1 plus OL. So what is the 0 of 1 plus OL? This will be 1 plus s square plus s upon s square plus s. So zeros, right? If I calculate zeros, this will be minus 1 plus minus b square minus 4ac. Okay, these are coming out to imaginary. Okay. So I don't have any zeros on the right hand side. No zeros on the right hand side. So because this is coming out to be complex conjugate negative, right? Like my zeros will be here, 1 0 will be here, 1 0 will be here. Is any of my zeros included in the Nyquist contour? No. How many poles are included in the Nyquist contour? 1. One pole is included in the Nyquist contour. So this will be 1 minus 0, that is 1. So I have one encirclement around minus 1 comma 0 point in the anti-clockwise direction. This question is very, very beautiful. And trust me, most of the students will not be able to solve it. Maybe I was also not able to solve it, because this was my year when I wrote my gate. So maybe I was also not able to solve it. I see the beauty of this question. This is beautiful. So like this will be your answer for the question. Let's solve the next question. The Nyquist plot of a stable open loop system. Whenever they say stable open loop system, they basically mean that the OLTF is stable. That means I don't have a right half pole for the OLTF. So P plus of OL is 0. That means P plus of 1 plus OL is also 0. This is the hidden information. So it is plotted basically here. It is found to intersect a unit circle. Basically this is my unit circle at the with center at the origin at point P equals to minus this value, right? P is this value, like at this pole location. Basically this is my omega, it's not omega, this is my pole location, whatever it is, like whenever the magnitude of my OLTF is 1 basically. Okay, this is my pole location. the points Q and R lie lie in the G of j omega plane. Assume Q to be this, R to be this value. The phase margin and the gain margin of the system would be. Okay, so they're actually not asking me. They're not asking me this Nyquist encirclement and all. They're just simply asking me what is the phase margin and gain margin. So what is phase margin? Phase margin is the phase of my OLTF. This is the plot of my OLTF when my gain is 1. So when is the gain 1? So at this particular point, the magnitude of my OLTF, it is 1. Correct, gain is 1 at this particular point. So what is the phase at this point? How do I calculate the phase at this point? That is interesting. So this will be interesting. So this location is given to me, right? P location is given actually. Sorry, this is not the pole, like this is not the frequency actually. Frequency is valid here, 0 to infinity. They have not given me the frequency. They have just given me the value of P. Basically the real part of my G of j omega and the imaginary part. So I see like this location is minus 0.77 minus 0.64. Okay, this is the x and y axis. So basically I need to calculate the angle, right? What is the angle basically? I need to calculate this angle. Sorry, both of them are negative. How can both of them be negative? Oh yeah, both of them, x and y both are negative. Yeah, that is correct. Okay. So what will be this angle basically? So what I can do is, this is a triangle, right? So the x coordinate is given, the magnitude of x, this length is given 0.77, and this length, the y length is given as 0.64. So I can just simply calculate this angle, and 180 minus this angle would be the phase. Remember, it is negative because it is in the clockwise direction. So my phase, right, of my OLTF at omega equals to omega GC would be minus 180 plus theta. Minus 180 degree plus theta is tan inverse y upon x. So y is 0.77, sorry, not 0.64 upon 0.77. One 80 plus 0.64 upon 0.77. Hold on a second. 0.64 upon 0.77. And already I'm calculating the phase margin. Phase margin is what? 180 plus this, right? So phase margin will be nothing but theta, because phase margin is 180 plus this, 180 plus this, right? So it will be theta simply. So basically I have to just calculate 0.64, 0.77 tan inverse 39 degrees. So phase margin comes out to be 39.73 degrees, which is present in option A and B. So either option A or B will be correct. Let us of course calculate the gain margin. Nothing is mentioned regarding the gain margin. So we are assuming gain margin is not in dBs, it is in decimal scale. So gain margin would be basically the inverse of magnitude of g of j omega at phase crossover frequency. So basically what is the phase crossover frequency? The frequency at which the phase of my OLTF becomes minus 180. Here I see, here it becomes minus 180 because it is crossing the negative real axis. So this is becoming minus 180 right here. So what is the value here? So actually, yeah, this r coordinate is given to me, right? What is r coordinate? R coordinate is minus j 0.21. So this distance is minus 0.21, right? That is basically nothing but the magnitude. Distance from the origin of my this curve is nothing but the magnitude. So the gain margin will be inverse of this, right? So I have to do inverse of this. So it will be 0.21. So this would be 0.21, that is 4.76. So 4.76 is your answer. So option A will be your correct answer, option B will be incorrect. So option A will be the correct answer for this particular question. Let's solve the next question. Yeah, let's solve this question now. So here we see that Nyquist plot of the open loop system corresponding to feedback loop, it is a negative unity feedback loop. Uh, the infinite semicircular arc of the Nyquist contour of S-plane is mapped into a point at what? Okay, that is pretty interesting. What are they asking? Corresponding to this feedback loop, the infinite semicircular arc of the Nyquist contour in the S-plane is mapped into a point at what? So infinite semicircular arc. So basically this, they're talking about this, right? They're talking about this whole infinite semicircular arc is plotted to where? Mapped of the Nyquist contour of S-plane. Like this is my S-plane, right? Sigma and j omega. So this whole infinite semicircular arc is mapped to what? So what happens? So omega varies from uh, plus infinity, because it is in the clockwise direction, to minus infinity, right? Am I correct? Plus infinity to minus infinity. Basically what is happening is that if I assume my s to be r e raised to power j theta, so what is happening? My r is infinity, right? R is infinity. R is infinity and theta is varying from plus pi by 2 to minus pi by 2. That is how you will plot here. So if I replace my s with r e raised to power j theta, so they are asking you basic things as well. This also I have taught, right? So if I replace my s with r e raised to power j theta, so this will be 3 r e raised to power j theta plus 5 j theta minus 1. So yeah, so what will happen? R is infinity, right? If R is infinity, I can simply neglect these values because this will be very high magnitude value. So I can neglect these 5 and plus 1. So this will be basically 3 raised to power, yeah, 3 only. G of s, h of s will be simply 3. Correct? Or you can say that if s, like basically you're mapping the infinite semicircular arc, you can say that s is tending to infinity, right? That is the magnitude of s is infinity, right? So if s is infinity, your g of h of s will be simply 3. So when s is tending to infinity, your g of s h of s will be simply 3. That's all. It will be 3. So option C will be correct. So they are asking you these basic things as well. So basically my theta will vary from plus pi by 2 to minus pi by 2 and r will be infinity. That is how you can map your entire right half plane of S plane to g of s h of s. That is how the mapping works, right? That is the theory of mapping. I hope you remember these things. So it will be 3. Option B, option C will be your correct answer for the question. Let's solve the next question. The number of times Nyquist plot g of s h of s encircles the origin. So again, they should have provided that your Nyquist contour will be in the clockwise direction. Again, bit of mistake on their behalf. So Nyquist contour is in the clockwise direction. So origin they are asking. So it will be simply n plus 0 comma 0 will be p plus of OL minus z plus of OL. So how many poles I have on the right hand side? 0. How many zeros I have on the right hand side? I have 2 zeros on the right hand side. Okay, 2 zeros on the right hand side. So okay, the number of times Nyquist plot encircles the origin. Actually, to be honest, the answer should be minus 2. Okay, but they should have provided, like, answer is given as 2. So I'm assuming they're asking like in the clockwise direction how many times it will encircle, because minus 2 is in the anti-clockwise direction, right? Because Nyquist contour was assumed to be in the clockwise direction. So yeah, plus 2 will be in 2 times in the clockwise direction, but they should have, again, I'm telling you again, these questions are bit of, they should have provided the direction of Nyquist contour, and whenever they're asking how many times will it encircle in the clockwise direction or in the anti-clockwise direction, that also should be mentioned. Okay, that is like, that is what I feel. or otherwise how will you understand these things, right? Yeah, that's all. The next question. So this is the next question. So here we have been given the Nyquist plot of the system is shown. PQRS all are basically points corresponding to my frequencies. All are positive frequencies corresponding to the positive frequencies at that particular points. Okay, these are all positive frequencies. Okay, so omega s is the gain crossover frequency, omega p is the phase crossover frequency. So before, like, they're talking about gain crossover frequency and phase crossover frequency, let me just see what is my gain crossover frequency. So gain, like, I'm varying my, this is my 0 plus and I'm varying it like this, right? So I'm varying it like this, so omega is increasing, so this is my direction. Again here, okay, it is here, again it is going, I think it is encircling to 1. So this is my omega equal to 0 to omega equal to infinity. So this is the path basically. This is the polar plot. It is simply this is the polar plot. So what do I see? This is the unit circle. So whenever it crosses the unit circle, that point represents the gain to be 1. And when gain is 1, that means this at this frequency is called as omega gc. So omega s is basically my gain crossover frequency. And whenever it crosses the negative real axis first time, that is called as the phase crossover frequency, because the phase is minus 180, that is q. So omega q would be my phase crossover frequency. So omega s is my gain crossover frequency, and omega q is my phase crossover frequency. Omega s gain crossover frequency, omega q phase crossover frequency. So option D is absolutely correct answer for this question. Pretty simple question, not that difficult. The Nyquist plot of a strictly stable g of s having the numerator polynomial as this encircles the critical point -1 once in the anti-clockwise direction. Which of the following statements on the closed loop system is correct? Okay, let me read it again. The Nyquist plot of a strictly stable, so g of s is strictly stable, that means your p plus of OL is 0 or p plus of f1 plus OL is also 0. Having numerator polynomial as s minus 3. Having numerator polynomial as s minus 3. It has a numerator polynomial of s minus 3. That basically means that z plus of OL is 1, because I have 0 on the right hand side, and encircles the critical point -1 once in the anti-clockwise direction. Again, assume your Nyquist contour to be in the clockwise direction, right? So n plus of -1 comma 0 is given to be 1. It encircles once in the anti-clockwise direction. This is once. Okay. Which of the following statements is correct? The system is stable. The system stability cannot be ascertained. Stable, margin is stable, unstable. Okay. So for that, I need to calculate what is z plus of 1 plus OL. That will give me the number of poles of my CLTF. So, okay, I don't know. I know this. Okay, I know p plus of 1 plus OL, that is 0. Z plus of 1 is 1, but will this information help me? The Nyquist plot is my anti-clockwise direction, because I don't know how many times it encircles around the origin. That information is also not of any use to me, but they have given me what is n of -1, right? So this will be equals to p plus of -1 comma 0, sorry, p plus, yeah, of 1 plus OL minus z plus of 1 plus OL, right? So p plus of 1 plus OL is same as p plus of OL, that is 0. So z plus is basically -1. Now this is not possible. -1 is not possible, right? Okay, maybe we have to assume that our Nyquist contour is in the clockwise direction, anti-clockwise direction. Otherwise, this will come out to be invalid. We have to assume that Nyquist contour is in the anti-clockwise. Like basically your z plus is coming out to be negative. If I assume my Nyquist contour to be in the clockwise direction, z plus is coming out to be negative. Again, they should actually mention the contour direction. Otherwise, the question is not proper. But this is coming out to be negative, which is not possible. So we have to assume it to be positive. So if I assume it to be positive, if I assume my Nyquist contour to be in the anti-clockwise direction, so if it encircles once in the anti-clockwise direction, that means it is n plus is -1, right? Because we have to write here the clockwise formula, because Nyquist contour is supposed to be the anti-clockwise. So this will be minus 1 equals to p plus, that is 0, minus z plus. So your z plus comes out to be 1. So basically you have one pole, closed loop pole on the right hand side. So definitely system will not be stable. Option D will be correct. Again, I'm saying, stressing this fact, they should actually mention the direction of Nyquist contour. Otherwise, there is huge confusion. They should mention it. Okay. But again, things are working out. You are seeing that, okay, Z plus is coming out to a negative. Negative is not possible. Negative Z plus is not possible. You never get negative Z plus. That means they had assumed their Nyquist contour to be in the anticlockwise direction. Because Z plus coming minus 1 was invalid. So we had to assume our Nyquist contour in the anti-clockwise direction. Okay, that is the reason. I hope you got this point. So yeah, I think this is the last question of Nyquist. Then we will move on to Bode plots. I think, yeah. So yeah, consider the control system block diagram. This, and this is the Nyquist contour, I guess. Nyquist contour is anti-clockwise. Okay, Nyquist contour in the anti-clockwise direction of infinite radius. Encircles two poles of G of HFS. It encircles, Nyquist contour encircles two poles. So if it encircles two poles of G of HFS, the locus of G of HFS should encircle the origin twice in the counterclockwise direction. Okay. Now the G of HFS does not have any pole on the geometric axis. Okay. Two poles on the G of HFS. What about the 0? Does not have any poles on the geometric axis. They have not mentioned regarding the locus of G of HFS should encircle the origin twice in the counterclockwise direction. Locus of G of HFS. So the thing is, n plus, because it is in the anti-clockwise direction, this will be in the clockwise direction of 0 comma 0 point would be p plus of OL minus z plus of OL. So how many times is it encircling the Nyquist contour? How many poles? Two poles. So I'm encircling the Nyquist contour twice. Minus z plus. Z plus means I'm encircling the Nyquist contour, like assuming like there are no zeros. Assuming there are no zeros here, right? So if I assume there to be no zeros, this will be 0, right? So basically I'm encircling the Nyquist contour in the clockwise direction around origin twice. So but it is telling me that the locus of G of SFS should encircle the origin twice in the counterclockwise direction. No, I will encircle twice in the clockwise direction. Also, they should have mentioned that there are no zeros here. Okay, they should have mentioned this. Again, question is incomplete. So no, this is incorrect. The locus of 1 plus G of S should encircle the origin twice in the clockwise direction. Okay, let me write. The locus of G of H of S should encircle the minus 1 comma 0 point twice in the counterclockwise direction. For that, I will need the information for closed loop stability. Okay, for if the system is stable, right, then n minus 1 of 0, this should be equals to p plus of 1 plus OL minus z plus of 1 plus OL. Now, if the system is stable, then this z plus will be 0. That is perfectly fine, right? Z plus will be 0. If the system is stable, z plus will be 0. Of 1 plus will be 0. And p plus is same as this one, right? And that is supposed to be 2. So basically, n plus of minus 1 comma 0, it is encircling it twice. In which direction? Again in the clockwise direction. Okay. So it will encircle minus 1 comma 0 twice in the clockwise direction. So here again it is telling me that it is encircling in the counterclockwise. Again incorrect, right? No. Locus of G of S H of S should encircle the minus 1 comma 0 point twice in the counterclockwise. Again it is incorrect. It should encircle it. Actually this statement, right? You cannot comment about this statement actually. Because again Z plus, although I have assumed it to be 0, but I don't know what is this value, right? There can be a right hand 0 that is included in the contour. They have not mentioned anything. So I can't comment about this option. Can't comment. They're asking which statement is correct. So can't comment about this. So this will not be my answer. This is also incorrect. Now locus of 1 plus G of S of S should encircle the origin, or locus of 1 plus G of S of S should encircle the minus 1 comma 0 point twice in the clockwise direction. Now what is the locus of 1 plus G of S of S? It is nothing but the shifted version, right? So if you remember, So if I have a this locus of g of s h of s, this is the imaginary part and this is the real part. Correct. So now now if I am plotting, so here, right, this minus 1 comma 0 point, if I am plotting this in the this plane, 1 plus g of s h of s, what will happen? So imaginary of 1 plus g of s h of s and real of 1 plus g of s h of s, if I plot this. So basically, right, imaginary part is 0. So if I add 1, so this will remain, this will basically, the imaginary part will not change, right, because I'm adding minus 1. So let's say this is the value, right, minus 1, and I'm adding 1 with this, so this is 0. So what is the imaginary part here? So a point that was minus 1 here, if I do 1 plus g of s, right, simply I'm adding 1. I'm adding 1 with my g of s h of s. So if I add, like, the value of the function is minus 1. So if I add 1, this will be 0. So what is the imaginary part? That is 0 only. What is the real part? That is 0 only. So basically this part, this point will be shifted to the origin. So encirclement around the origin of 1 plus g of h of s plane will be same as encirclement around minus 1 comma 0 point. And encirclement around minus 1 comma 0 point in the clockwise direction is 2. That is what I have calculated. So this statement is correct actually. The locus or the Nyquist plot of 1 plus g of s should encircle the origin twice, because encircling the origin twice of this particular locus is same as encircling minus 1 comma 0 of this particular locus plane. And that is what we have conclusively can conduct if my system is stable. If my system is stable, this will be 0. Correct? These two I cannot comment actually. These two I cannot comment. So this one I can comment definitely. Yes, it will encircle the minus 1 comma 0 point twice, but in the clockwise direction, not in the anti-clockwise. So this is incorrect. This again, it will encircle minus 1 comma 0 point twice. No, I cannot comment about this minus 1 because I don't know what is this point. This point is here, minus 2 comma 0. I cannot comment about this point. There is no information about this point. I cannot comment about this point. So I can only comment about option B and C. C is wrong, B is correct. I cannot comment about A and D. So here option B will be correct answer for your question. So now let's start with Bode plots. Let's start with the first basics of Bode plots, that is logarithms. So like educators, what they do, they directly start with Bode plots. But if you don't understand basics of logarithms, you will not be able to understand the graphs. Okay, and why we use log scale, that also I will explain. Okay, so let's start. Basic log, you know that if I have any number log ax like this equals to y, then how can I actually represent it? It is represented in power terms like this. It is a raised to power y equals to x. This one comes here. This is known as the base. This is the this is the base of the log that is coming here. This is the power exponent and this is the output, okay, result. So this is how I convert a log expression. So few basic properties you should know about log. Log a of a, where base is same, it is 1. How do you know? Basically you apply the same formula, right? What do? You do a raised to power, what I have to do to get to a, I have to do a raised to power 1, then I will, my result will be a. Same here as well. Log base a of 1 will be simply 0. So what I have to write in the power expression for a so that my result is 1? It is simply 0, correct? If I write 0, then I will get 1. So that's why this 0 comes here. Okay, so few basic properties of log. Another basic property of log is if I have log a mn, simply you can write it as log a m plus log a n. Then if I have this one log a m minus log a n, okay, then we have, like, this one is like if they are division, then subtraction sign will come. If something like this is there, right, x raised to power 2, so this power can come in front of the log, so this will be 2
log ax. So these are basic properties. I'm not explaining it how I got here. Like I hope like you have passed 12, so you will know all these basic properties. So now let's come to the linear scale and log scale thing. So in linear scale, right, all the distance are equidistant. Okay, so linear scale, that like everything goes equally. So if I move 1 unit, that means I have moved from 1 to 2. If I again move 1 unit, that means I have moved from 2 to 3. What is the difference? I will explain in the next slide. Okay, when in the log scale I will explain. So everything, the distance, right, if you see visually also, if you see the distance is same. So every time I travel 1 unit, my value gets increased by 1 of the previous value. Okay, what about decade scale? In decade scale, what happens? The distance is not equal. Every time I move 1 unit of distance in decade scale, my value becomes 10 times of the previous value. So this, right, this 1 2 3 4 is in the decade scale, but actually how my value is increasing, if I have moved one distance previously, if I was at omega, this will be 10 omega, this will be 100 omega, this will be 1000 omega, like that. It will keep on increasing 10 times. Previously it was 100 omega, now it has increased to 1000 omega. So this, right, although visually for showing you I am showing it equal, but they are actually not equal distance. Just understand, I am at 100 omega here, I am at 1000 omega. How can the distance be same as this? What is the difference here? The difference here is 90 omega. What is the difference here? The difference here is 900 omega. So of course the difference has increased, so the distance also will be more here. So that's why this scale is not linear scale. Same for octave scale. Octave scale means if I travel 1 unit distance in an octave scale, my value becomes twice of the previous value. So if this is omega, then this will be 2 omega, this will be 4 omega, this will be 8 omega. Again, if you see, this is omega, distance is omega here, distance is 2 omega here, distance is 4 omega here. So you can observe like the distance is increasing, right? So again, this scale is not linear. Okay, so now I will do few conversions. Basic conversion, I hope you know, from decimal to dB scale. If I have a number decimal, let's say 10, how do I write it in dB? It will be 20 log base 10 10, that is 20 dBs. So 10 in decimal is 20 in decimal in dB scale. Okay, decibel scale. Okay, so few basic things, like we are just solving the basic things right now. So let's do one more thing. So if I have a function f of omega which is defined between 0 to 1000 as 2 omega, and after 1000 or before 0 it is 0. Okay, so let's plot it for omega, let's plot it for omega cube, let's plot it for log 10 omega. So if I plot it for omega it will be pretty simple, right? It is a straight line, so it will be just like from 0 to 1000 I am going, so it will just be a straight line which will have a slope of 2, correct? Because I am plotting with respect to omega, that's why it will be straight line. Okay, it will be straight line. So now this is the straight line, linear scale. In linear scale, if I have a function that is proportional to omega, then I get a straight line. Okay, what is the slope? Slope is yb minus ya divided by b minus a, x value by y value. So y value by x value. So y value change, what is the change in y? Change in y, this right, this point is what? This point is 2000, right? This point, this point is 2000. Okay, this point is 2000, so this will be 4 minus not 4 minus, sorry, 2000 minus initial value 0, that is b minus a, that is 1000 minus 0, so this will be 2. Slope is 2. Okay, here the slope is 2. Okay, now let's move on to the next part. So the next part is this one. So here, if I have to do this, right, I have to plot with respect to omega cube. So I will just plot points. Okay, I will plot the points. So what is my f of omega? F of omega is this, right? 2 omega between omega 0 to 1000. So f of omega is 2 omega between omega 0 to 1000. So but I have to plot with respect to omega raised to power 1 by 3. So for omega equal to 0, what is f of omega? F of omega is 0. Okay, but when omega raised to power, like I am plotting for these 3 points, omega raised to power, like my x axis is now omega raised to power 1 by 3. So when my omega raised to power 1 by 3 is equals to 1, then what will be the value? That means omega is 1. That means omega is 1. That means f of omega, so we'll write here f of omega is 0. Here my f of omega is 1 only. Okay, not 1, sorry, 2, because f of omega is 2 omega. Okay, then if my omega raised to power 1 by 3 equals to 2, then omega raised to power omega equals to 2, then no, sorry, this will be omega equals to 8. Okay, omega equals to 8, f of omega equals to what it will be, 2 times omega, right, 16. Okay, so if you see, if I have moved 1 unit of distance here, right, like I will mark the same points. Just let me show you one thing, that here omega equals, like let me mark the points, omega equals to 1, omega equals to 2. Omega equals to 1, what is f of omega? It is 2. Omega equals to 2, what is f of omega? It is 4. So if I move 1 unit of distance, I am moving 2 units. Again, if omega equals to 3, f of omega will be 6. So again I am moving 2 units of distance. So this is equidistant. This is equidistant. But here, if I choose omega raised to power 3 equals to 3, right, because my x axis is omega raised to power 1 by 3, this will be equals to, omega will be equals to what? Omega will be equals to 27. So what is my f of omega? F of omega will be 27 into 2, that is 54. So I am observing that this is not equidistance. So the graph, right, will be something like this, parabolic, something like this. Okay, this will not be not a straight line. Okay, so this is a problem to us. Okay, so here I have written the same thing, that if omega raised to power 1 by 3, if omega raised to power 1 by 3 is increasing linearly, but omega is not increasing linearly, that's why f of omega is also not increasing linearly. Okay, so let's do for the log scale now. Okay, so like, but here, right, here, sorry, not for the log scale, before coming to the log scale, if I write this in the omega scale, will this be linear? Yes, this will be linear. Correct, this will be linear. There will not be any problem. This will still be a straight line. But what we do, I'm trying to explain one thing, is in your Bode plots, right, in the x-axis they will write here omega, but the scale will actually be something else. Okay, what did I say? In your examination, your x-axis will be written as omega, but it is not as same as this omega. Okay, they are just writing the omega because they are following some convention, but actually the scale is something else. The scale is not this one as well. I will tell you what is the scale, but scale is not omega. Scale is something else. So in this example, scale is omega raised to power 1 by 3. Although they have written here omega, but the scale is something else. Okay, now if the scale is something else, then your graph also won't be linear, because when the scale was omega, then the graph was linear. But if the scale is not omega, graph is not linear. So here graph will not be linear. Don't worry, I will tell you what is the scale. Okay, just try to understand this point. Just have to clear this misconception that scale is not omega. Although omega is written here, scale is not omega, scale is something else. Scale is log base 10. Sometimes they write it, sometimes they don't. That's why students get confused. Okay, so scale will be this one. Okay, why we use log scale, I will explain later on. I will explain that, don't worry about that. Now in log scale as well, will my function be linear? So in log scale, right, I can never reach 0, because log of 0 is undefined minus infinity. So I can go very low value, but I can never touch 0. Okay, so what does log scale mean? Log scale means it is a decade scale. Log scale is basically a decade scale. So for 1 decade movement, omega gets multiplied by 10. That is what a decade scale is. I have already explained at the starting of this lecture what is a decade scale. So for one decade movement, omega gets multiplied by 10. Okay, so basically actual value of omega, right? What is log, like what is this? Log base 10 omega equals to 0, because that is what this scale represents. This value is equals to log base 10, right? So this is equals to 0. When is this equals to 0? At the starting of this lecture I have already told you, when omega will be equals to 1, then this value is equal to 0. That means actually this represents omega equals to 1. When will this value equals to 1? Log base 10 omega equals to 1 when it is equals to 1 when omega is 10. Starting of this lecture I have explained this. Okay, so same for 2 it will be 100, for 3 it will be 1000, for minus 1 it will be 0.1, for minus 2 it will be 0.01. okay, something like that, like this. I hope you have understood the log scale now. So here, right, that's why what examiners do, they don't write anything here, they just write omega and they write these points, okay, in decade distance. So you have to understand that this is written in decade scale. Now let's write the values. Okay, for 0.1 f of omega will be 0.2, for 1 f of omega I write f of 1 is equals to 2, f of 10 will be equals to 20. Again I see if I am moving 1 unit distance, these are not equidistant. Okay, that means again my graph will not be linear, it will be something like this. Okay, parabolic like this. Okay, so we have to resolve this because we don't like to plot these kind of graphs. In Bode plots, if you have seen, we get linear lines. How do we get that? We will come to that. Okay, so I hope you have understood the difference between decade and octave scales. Okay, decade is in multiples of 10, octave is in multiples of 2. Okay, now if I want to write what is actually 1 decade equals to in decimal value. Okay, so 1 decade is equals to x2 minus x1, right? I am at this point, okay, let's say this is my x2 and this is my x1. So what is x2 equals to? X2 is equals to log base of omega 2, right? This is equals to log 10 base omega 2. This omega 2 is in the decimal scale, so I want to convert into decimal scale. Okay, and this x1 is equals to log 10 omega 1. Okay, so this will be equals to log omega 2 minus, like base 10, don't forget the base 10, everything will have base 10 omega 1. So this is actually equals to log of 10 omega 2 by omega 1. Now if you see, now if you put omega 2 equals to 10 omega 1, then this actually becomes 1. That means 1 decade becomes 1 decade. Like if in the decimal scale I move 10 times the previous value, then in the decade scale I move 1 unit. That is the basic meaning of this particular result. Okay, so I hope you understood the point. Okay, and same for octave as well, same for octave. So in octave again I will do the same thing, x2 minus x1. So again it will be log of, now in octave, right, the base is 2 because I am doubling, that's why the base is 2. I will prove it to you why the base is 2 as well, minus log of 2 omega 1. So this will be equals to log of 2 omega 2 by omega 1. Now here, right, it is doubling. So if it is doubling, that means what? If my omega 2 is twice of omega 1, then this becomes 1. So that's why here I have a base 2. Only for base 2 this will equate to 1. Okay, that's why I have a here base 2. So I hope you have understood the differences. Now if I want to convert octave into decade. Okay, so 1 decade of distance is this, correct? So now if I have moved a octave distance, so that will be equals to what? Then my omega 2 will be equals to to omega 1. So then yeah, so then I will replace here omega 2 by omega 1. I get 1 octave is 0.3 decades. Does it make sense? Yes, because 1 decade means I am moving at 10 times distance. 1 octave means I am moving 2 times distance. So 1 octave should be a fraction of a decade. So this result makes sense. And the most famous result that we remember is this one, actually not this one, is 20. This is 1 decade, 20, something is wrong here. 2, this should be 0.3. So if I multiply here 20 decade, it should be, no, not this one, 20 dB per decade. Okay, no, that is some other result. I'll discuss about that result. Okay, so these are the result. 1 decade is 3 octave, you can remember this, or 1 octave is 0.3 decade. Anyone is okay. You can remember this. Generally they will give you decade scale, but sometimes you get given octave scale as well, so be careful about that. Okay, so I will tell you another relationship that I will come to later on. For now, remember this relationship. Okay, it's better for examination. Just remember this one, that this is also intuitive to understand that 1 octave will be a fraction of a decade. So 1 octave is equals to 0.3 of a decade. Now let's come to the reasoning. Why log scale is required? Why log scale is required in x-axis? Okay, so to plot larger range of omega, log scale is required because we want to check the high frequency response and the low frequency response in the same graph. That is only possible for a log scale, because let's say I want to check 10 kilo radians. Okay, that means can I plot it in a linear graph? No. Can I plot it in a log graph? Yes. Log 10 of 10 kilo radians will be, this will be 10 raised to power, not raised to power, 10 into 10 raised to power 4, right? So 10 raised to power 4 will be there. So only 4 units I have to move in the log scale. But in linear scale, I have to go 1000 units, right? That is too far away. In the same scale, I will not be able to represent that. That's why we use log scale. And low frequency, yeah, sorry for the interruption. My throat was actually dry. So as I was explaining that we have to plot like lower frequency region can be expanded because 0.1, 0.01, they are also all 1 unit. Okay, 1 unit distance, so they can be expanded. So I will not explain more here because we have to cover other things as well. Okay, so why we will not be able to cover 0? Because log of 0 is minus infinity, so we will ignore. We can, in Bode plots, we can only talk about omega greater than 0. At omega equal to 0, we will not be able to actually plot it, but still we can show it in the graph, but in reality we don't talk it and we don't plot it, and actually we don't need 0 omega as well, because sine of 0 and cos of 0, they don't give us any information. That's why we can ignore the this 0 frequency response. Okay, so let's now come to few analysis. So let's do, like, Bode plot is a approximate frequency analysis, but before doing that, let's come to exact frequency analysis. So how do we do the exact frequency analysis? So up until now, in the x and y axis, in Nyquist and polar plot, there was real of OLTF and imaginary of OLTF, right? Now in the x axis there will be omega, that is log of omega to be precise, and in the y axis there will be magnitude of g of j omega. Okay, now it is a bit different. So we have to plot the magnitude with respect to omega. So what we do, we put s equal to j omega, and then we vary our omega from 0 plus to infinity. Okay, so I hope you know, like, if I am exactly plotting the magnitude, then it is known as exact magnitude plot, that is magnitude of g of j omega versus omega. If I am exactly plotting the phase, then it is known as like exact phase plot. Okay, so these things, you know, the magnitude of a standard transfer function, first order transfer function. Okay, and phase response. So what will be the like magnitude response? So if I observe that as I keep on increasing my omega, the magnitude just keeps on reducing. At omega equal to 0, the magnitude is k. Then as I keep on increasing my omega, it will keep on increasing. It will keep on decreasing in non-linear fashion. It is not linear, right? Linear means my magnitude, my f of x must be a linear function directly proportional to x. Is it the case here? No. F of x is some weird function of omega, right? It is not. So that's why the response will be something like this. Okay, the response will be something like this. Now remember, this is in the dB scale, and I hope you know how to convert into dB. This is the decimal number. Just do 20 log of k, you will get to dB. Why am I getting negative? You might say, sir, magnitude can never go negative. What is happening? This is not in the regular scale, right? This is not in the decimal scale. This is in the dB scale. What is happening? Let's say my magnitude is 0.1. It is positive, but if I take the log, it will become negative. Correct? Some negative number. That is exactly what is happening here. These are all what? These are all fractions, numbers less than 1. Okay, that's why I'm getting negative. Okay, I hope you understood this point. Now remember, this is with the linear scale, exact magnitude plot with the linear scale. What about the phase plot? Tan inverse omega has a frequency response, has a plot something like this. If you know this very well, if you don't know this, now you know. Okay, obviously we don't have time to prove. So tan inverse omega will have a phase response something like this. Okay, and at 1 by tau the angle will be minus 45 degrees. Okay, and this will be minus 90 degrees. This will be minus 90 degrees. Okay, so this is how actually it will not be exactly like this. It will be somewhat like this. Okay, somewhat like this. Okay, so this is how the phase response and the magnitude response will be there. Okay, so why do we plot in dB scale? Similar reason, as we have to plot larger range of magnitude. If I take the log, I can plot larger range of magnitude. Second reason is can break into factors into simple algebraic functions. What do I mean by this? Let's say if I have this, right, g omega this how do I say this? So I have to like, let's say my transfer function g of s is s plus 1 divided by s plus 2 into s plus 3. So I can convert this in as a linear functions. How? If I take the log, this will be log base 10 of s plus 1. Now first of all, let me write the magnitude. Magnitude of g omega will be magnitude of omega square plus 1 divided by omega square plus 4 into omega square plus 9. Okay, so now if I take the log, this will be log of omega square plus 1 whole under root plus, not plus, sorry, minus, because the other ones are in division, log of omega square plus 4 whole under root plus, because internally it is multiplication, right? Of course outside when it will come, it will be negative sign, but internally it is in multiplication, plus log of, I'm just doing the rough here, not writing the exact expression. Okay, just doing the rough, log of 10 omega square plus 9 whole under root. Okay, so like now you can see like I have converted in linear terms, like there will be 20 log to convert this into decimal scale. But now I hope you understood, I have converted as a algebraic sum, this expression, weird expression, as algebraic sum. So that is also another reason to use dB scale. This can get asked in interviews. Okay, so like I have done the same thing, the homework for you, write the magnitude expression in dB scale, like it will be just the sum of the logs, algebraic sum, right, as I have done in this example. Okay, so now let's plot few like Bode plots for these kind of things. Okay, I have shown you the exact frequency response. Okay, frequency response. Now we will draw the Bode plots. So how we draw the Bode plots? So we approximate few things. First, let's plot the Bode plot for this one. What will be the magnitude of this? Magnitude, like there is not a function of, it is not independent of frequency, so magnitude will simply be k, it will be constant. What is the phase? Phase will be 0 degrees simply. Let's say phase will be 0 degrees for positive values of k. If k is negative, then phase becomes minus 180. Just be careful about that. If k is negative, then phase becomes minus 180. Okay, so what will be the magnitude response? Magnitude will be 20 log 10 of k. It will be constant, right? It will be a constant value. It is not a function of frequency, so it will be constant. Just a constant value 20 log of k. Okay. Now this, right, remember this is in decade scale, although omega is written, but Bode plot is plotted with the decade scale. Okay, it is used in semi-log paper. Semi-log paper has x axis as a decade scale. Okay, so what about the phase? If my k is greater than 0, right, if my k is greater than 0, then the phase will be 0 degrees. Okay, if k is greater than 0, if my k is negative, obviously this value will be negative, right? If minus sign is there, then the phase is minus 180. Okay, I hope you understood this point. And remember, all these, right, are written in radian per second. Okay, don't forget about this. All these are written in radian per second. Okay, so what I see is, if I have a constant value, then the Bode magnitude plot will shift up or down by 20 log k. Okay, so the meaning of this statement we will realize later on. If k is positive, the phase for the Bode phase plot, if k is positive, phase doesn't change. If k is negative, phase is minus 180. So let me do the next question, then we'll understand the meaning of this previous statement. Okay, so for 1 by s, the magnitude will be 1 by omega. Okay, and in dBs, what it will be? It will be 20 log of 1 by omega. What is 20 log of 1 by omega? It is 20 log 10 of 1 minus 20 log 10 of omega. Okay, so this will be minus 20 log 10 of omega. Are you seeing something? My magnitude, that is f of omega, is 20 log of minus 20 log of 10 omega. Is it very interesting? Yes, it is very interesting. My scale is what? My scale is log 10 of omega. So actually this, right, inside this it should be f of log 10 of omega. Why? Because generally what you write, f of x equals to 2x, something like this, right? Then we call it as linear function, and this is my x axis, but I have changed my x axis. My x axis has been changed to log 10 of omega. I've told you already. So instead of this I can write this. So this is equals to minus 20 log 10 of omega. So now if I just convert this variable, if I write that log 10 of omega is some variable v, so this gets converted, f of v is equals to minus 20v. Now isn't this a linear function? Isn't this a linear function of v? Yes, it is. So this is also another reason to use log scale, because in Bode plot what we see is we can make our function magnitude linear. That's why we love Bode plots so much. We can make our function linear. Okay, what is the slope? Slope is 20, minus 20. But what is the unit of the slope? How much y distance I am moving? In what is the y-axis unit? dB. So y-axis is dB. What is the x-axis unit? Decade. I am moving a decade scale, so it is dB by decade. So that's how the unit came, dB by decade. Slope is minus 20 dB by decade. So if I plot it in the log scale, in the Bode plot with respect to y, it will just be a straight line of negative slope. Okay, it will just be a straight line of negative slope. That's it. Okay, and here also you can measure the slope using same formula. What is the formula of slope? That will not change. Slope formula is yb. Let me make this point a and b. So if I am moving from a to b, it will be yb minus ya divide by, remember, your x axis is not x, it is log 10 of x. So in the bottom I will write log 10 of omega b minus log 10 of omega a. Okay, so this formula, right, I will use everywhere, and this I have derived with basics. Okay, I hope now you understand this formula. This formula is written here as well. Okay, so I will not give too much time to this. We have to solve other things as well. What about the phase? What will happen to the slope, right, will just be a constant number, because here I forgot to write the slope expression. So your g of j omega will be what? G of j omega will be 1 by j omega. So the slope will be angle of j omega, it will simply be minus 90. Okay, because I have a j over here, so this will be minus 90 constant. Okay, so adding a pole at the origin gives a slope of minus 90 and a like not slope, sorry, gives a value of minus 90 in phase, and in the magnitude plot it gives a minus 20 dB per decade slope. Okay, so now I will combine these two information. So if I had this transfer function k by s, what it will do in Bode plot, remember the first point. First point was what? If I have a constant k that is getting applied in a transfer function, that means it will shift the Bode plot by 20 log k units. So what will happen? Basically, this was here, right? This plot is here. Everything will be shifted up by 20 log k units if it is k by s. What will happen to the phase? If my k is positive, then nothing will change. This phase will remain same. If my k is negative, then I will have to subtract another 180. So angle will become minus 270. That's how I have combined the k effect of k. So remember these points, right? At the end I will summarize. Don't worry about it. So let's do it for the 0 now. Okay, if I have a 0 at like s equal to 0, then again what will be the magnitude? Magnitude will be omega, and the angle will be plus 90 degrees. So in dB scale, what it will be? It will be 20 log of 10 omega. Again, this is what? This is the V, right? So again, it is in the relation as mx plus c, right? So my magnitude is directly proportional to log of 10 omega. So it will be a like linear scale in the positive direction. So what is the slope? This time the slope will be plus 20 dB per decade, as it is here plus 20. Okay, so the value will be something like this. It will be something like this. Okay, slope will be plus 20 dB per decade, plus 20 dB per decade. So if I have a 0, then what happens to the Bode plot? A slope of plus 20 dB gets added. So like same thing is written over here, plus 20 dB per decade. And for phase, what will happen? Phase will be plus 90 degrees. So phase here will be plus 90 degrees. So again, the conclusion, what is the conclusion? Conclusion is, if slope of slope of Bode magnitude plot changes by plus 20 dB per decade if j omega is added to the transfer function, and phase plot shifts up by plus 90 degrees. Okay, so now let's do these examples. Now what will happen to these examples? So now for this one, right, we have to do few approximation. Up until now we are doing the exact analysis. Now we will do few approximations. I will explain that. So what is the magnitude? Magnitude for this, right, will be 1 by 1 plus omega tau whole square whole under root. Okay, and angle will be minus tan inverse omega tau. I have drawn the exact plot for this transfer function. Now we will do approximation. So if my omega is very less than tau, right, so basically what will happen? This will be negligible. This omega tau will be very less than 1. Then if this is very lower than 1, then this like 1 plus 0.1 whole square, okay, will be almost equals to 1 only. So what I can do, in low frequency region the magnitude becomes 1. Okay, for low frequency region the magnitude becomes 1 j omega. What about the phase? This is 1 dB. Okay, so magnitude is 1 in decimal scale, but in dB scale what it will be? It will be 0 dBs. Okay, because log of 1 is 0. What about angle? Angle also becomes 0, right, because 1 is a positive number, so angle becomes 0. Okay, so for low frequency region, I'm getting 0 degrees of angle and 0 degree of magnitude. What about for high frequency region? High frequency region means omega has to be very greater than tau, that is your omega tau is very greater than 1. If omega tau is very greater than 1, that means this expression, right? I ignored this previously. Now what will happen is it will be under root 1 plus 100 square. That means it will almost be equivalent to 100 only. Okay, so I can ignore this one. So it will be equals to what? Your magnitude of g of j omega is equals to 1 by omega tau. Okay, 1 by omega tau. Now if I take the log, this will be minus 20 in dBs. This will be minus 20 log of omega tau. Okay, so that is what this will be, minus 20 log of omega tau. Now what about the angle, right? Approximately what it becomes minus 90, correct? Because this omega tau will be dominating instead of the other value, so it will become minus 90. Okay, so like few things are written over here. So basically this, right? The point of intersection of the low frequency asymptote and the high frequency asymptote is known as the corner frequency. Basically the point at which, like, at very high frequency the value is what? Value is minus 20 log of omega. At very low frequency the value is 1. Where these two points meet, that will be the point of that will be the corner frequency. Okay, because somewhere, like, what will be the, like, I will show you the plot. The plot is something like this. I'm expecting, sorry, this is in high frequency region. This should be high frequency region, actually. This should be high frequency region. Okay, in high frequency region, like, I am decreasing linearly. This is the approximate plot, right, that I have assumed. In high frequency region I am decreasing linearly, and in low frequency region, I am constant value, that is 1, and in dB scale that is 0. Okay, so the point at which they will meet, okay, what is the point? This 1 by tau, right? The point at which these asymptotes meet are known as the corner frequency. What do I mean by asymptotes? Basically, right, if you extend this, like, what is minus 20 log omega tau? Something like this, right? So I will extend this graph, and what is 0 dB? It is something like this, 0 dB. So wherever this intersection will happen, that is known as the corner frequency, and this happens at the value 1 by tau. Okay, at the pole location, basically. Okay, at the pole location the intersection happens. Okay, so what we were observing is, if you would have drawn, like, this is the approximate plot and this is what we will plot. Of course this is the exact analysis that I have shown to you at the start of the lecture. Now this is the approximate plot. Okay, so for high frequency region I was getting minus 20 log omega tau. For low frequency region I was getting 0 dB. Okay, so for magnitude the error is maximum at corner frequency. Maximum error, if you see, like, the here, right, error is lower. Here the error becomes highest, then again it becomes lower. So the if I plot the error function would be something like this. It will be symmetric about the corner frequency. Okay, it will be even symmetric about the corner frequency. Error will increase when it reaches to the corner frequency, then again it reduces. So this is the error in dBs. Okay, and, like, I have shown you a calculation. You can go through this. It's good if you remember this data, but I have shown you the calculation. I don't have time, so I will not explain this. Just the error is maximum at corner frequency, and the value of the error is actually minus 3 dB. How do I compare? Simply, you just find at corner frequency what is the Bode magnitude telling me. It is telling me 0 dBs. And what is the exact magnitude at corner frequency? It is 1 by root 2. So I have to convert this into dB. If I convert this into dB, it is minus 3.01 dBs. Okay, so 0 dBs and minus 3.0 dBs, so total error is 3.01 dBs. That's how I get this value. Okay, so these are few key points that I will summarize. The frequency at which the slope of the asymptote of the Bode magnitude plot will change is known as the corner frequency. Basically, don't have to worry about this. Corner frequency is the frequencies at which I have zeros or poles. That's it. Okay, that's it. This is a important point. The error will be maximum at corner frequency. Okay,
So corner, like what are corner frequency? Corner frequency are basically magnitude of pole location and magnitude of frequency location. That's it. This is the summary point that I wanted to emphasize on. Okay, you don't have to worry about the other thing. What about the phase? So the phase is a bit tricky. Okay, so the phase, if I draw this phase, right, what I was getting, so for low frequency region I was getting 0 degree phase, for high frequency region I was getting 90-degree phase. If I do something like this, right, there will be huge error. So what we do is 10 times before the corner frequency and 10 times after the corner frequency, we just draw a straight line. We just connect the two straight lines, okay, to minimize the error. To make the error at corner frequency 0, we do something like this. We draw a straight line which has a slope. Now currently I have a pole, so we draw a straight line which has a slope of minus 45 degree per decade. Decade, I hope you understand, the x-axis, y-axis is in degrees, that's why the unit is degrees per decade. Okay, so that's, just remember this, 10 times before a pole or 10 times after a pole there will be a straight line, and after this, right, I will be constant 90 degrees, because at high frequency region I know I was getting 90 degrees minus 90 degrees, and at low frequency region I was getting 0 degrees. Okay, so just to account for the error, for better approximation, I draw a straight line. So what happens is exactly at corner frequency, if I calculate the phase of this Bode approximate plot and the exact frequency plot, exact phase plot, you will observe there is 0 degrees of error. So there is no error. Error is minimized. So that's why we do these kind of approximation. So this was the first approximation. Then we move to this better approximation. Okay. So I hope you have understood this same point. So same process we will follow for zeros. For zeros at low frequency region, you will see the gain will be 0. For high frequency region, the gain will be plus 20. Now the slope will become plus. Instead of minus, it will become plus. Angle will be plus 90. Previously angle will be 0 degrees for low frequency region. Again here also exact plot is this one, and the approximate plot is this one. Error again will be same result you will get. Error will be 3 dBs at corner frequency, and in the phase also the error will be 0 at corner frequency. Okay, for 0 what we do, we draw a straight line, but this time the straight line has a slope of 45 degree per decade. Previously due to the pole we had a slope of minus 45 degree per decade. Okay, so this is the main thing that I wanted to discuss. Now we will discuss more about Bode plot. So in Bode plots, mainly you will be given two types of question. One is the Bode plot will be given, and you have to find the transfer function or some PM, GM, all those things. Else, the transfer function will be given. You have to identify the Bode plots. 90% of the times these type of question comes, and 10% of the times these type of question comes. Okay, so of course we'll solve everything. So this is the summary that I wanted to tell you. A pole gives a slope of minus 20 degree per decade at that corner frequency. After that corner frequency, a 0 gives a slope of plus 20 degree per decade after the corner frequency. Error will be maximum at corner frequency with respect to exact plot magnitude, for magnitude. Okay, and now the slope of magnitude plot of g of j omega would tend to minus 20 n minus n dB per decade as omega tends to infinity. What does it mean? Let's say I have something like this, s plus 1 divided by s plus 2 s plus 3 whole square. Okay, so at omega tends to infinity, what will be the slope? Again you can break this down. Ultimately your slope will be, here I have two poles, here I have single pole, here I have one pole. So here I have 1 0. So total I have 3 poles. So poles provide how much slope? Minus 20 dB per decade after their corner frequency. Here I am talking about omega tending to infinity. So I am talking about the region where I have passed all the corner frequencies. Okay, so due to the poles I am getting minus 20 dB slope. Due to the zeros I am getting what? Plus 20 dB slope. I have only a single 0. So it will be, ultimately it will come out to be 3 minus 2 into minus 20. So which is 3, not 3 minus 2, sorry, 3 minus 1 into minus 20, which is written here in formula. So don't have to remember the formula, just understand the concept. These two slides are the most important slides. Okay, these are the summary. So for phase, right, for phase it is a bit tricky. That's why the questions also comes very less in Bode phase plot, because it is a bit tricky. Try to understand this. A pole will always give a slope of minus 45 degree per decade, but for what region? 10 times before the corner frequency, that is 0.1 times omega p,
and 10 times after the corner frequency, that is 10 times omega p. So in this region, I will get a slope of minus 45 degree per decade. Before this region and after this region, I will not get any slope. It will provide 0 degree slope written here. It will provide 0 degree. It will provide an angle of constant 0 degree. Slope will be 0. After 10 omega, it will provide an angle of minus 90 constant, slope of 0. Okay. Understand this. Effect of a pole or 0 goes away 10 times after the pole and 10 times before the pole. Effect of that pole only stays within the 10 times before and 10 times after, within this region. It goes away after and before. Please understand this. This is a very, very important point. Okay. So same for 0 as well. I will not explain for 0. Okay. So key points for like Bode phase plot: error will be 0 at corner frequency. Okay, error will be minimum. The phase of g of j omega would tend to minus 90 n minus m as omega tends to infinity. This I have already talked to you with Nyquist plot and polar plot as well, but this is only valid for minimum phase system because the formulas will change, right? Calculation of phase angles will change if it is not a minimum phase system. We'll discuss what is a minimum phase system. Okay, so can you plot the Bode plot for this particular function? So we don't have time, so I will do this a bit quicker. Okay, I'll do this a bit quicker. So first is, like, sometimes, like, in my full course I teach everything, like how to break this down and all those things, but now I will do this a bit quick. So first of all, we have to convert this in our standard time constant format. What is our standard time constant format? Standard time constant format is this one. It should be k into s tau plus 1 s into omega z plus 1, then s into omega p1 plus 1, like this you can write as something like this: s tau z, this will be s tau p plus 1 into s tau p2 plus 1 into s tau p3 plus 1, and so on, right? This is my standard time constant format. So this can be converted like with s plus, right? This should be 1. Okay, here this is 1, but this is not, like I have to rewrite it. This will be 0.1 into s plus 1 divided by s divided by 0.1 plus 1 into s divided by 100 plus 1. So what are my corner frequencies here? My corner frequencies are this. Okay, corner frequencies are 1, this is my 0, this is my one of the corner frequency, omega p1 equals to 0.1 radian per second, omega p2 equals to 100 radian per second. Now let's break it down. So this 0.1 will provide a constant magnitude of what? 0.1 will provide a constant magnitude of 20 log 0.1. That is what? That is it's a minus 20 dB. So this 0.1 will provide my constant value of minus 20 dB. How much phase will it provide? Phase, as it is a positive number, it will provide 0 degrees. Now this pole will provide a slope of omega p1 will provide a slope of minus 20 dB per decade. Okay, how much phase angle? It will like this will be the for the magnitude. Okay, for the magnitude, and for the phase it will provide a slope of minus 45 degree per decade. Okay, what about the 0? So 0 will provide omega z 1, omega z will provide a slope of at what? This provides a slope after the corner frequency at omega p1 at 0.1. This provides a slope of plus 20 dB per decade after 1 radian per second, right? So this will be plus 20 dB per decade, and slope for the Bode phase plot will be minus, not minus, sorry, plus 45 degree per decade. Same for omega p2 as well, right? After 10 radian per second, or 10 or 100, it is 100, right? So after 100 radian per second, it will provide a slope of this. Okay, so same thing for after 118%. But remember, the slope of minus 45 degree per decade, what is the range? The range is for 10 times before the corner frequency and 10 times after the corner frequency. So 10 times before is my omega should lie in this range 0.01 and 10. Okay, after this the slope will be 0. So I will write here, for I'm talking about angle, magnitude is fixed, right? Magnitude is fixed. So this is slope of minus 20 after 0.1 radian. This is slope of plus 20 after 1 radian. This is slope of minus 20 after 100 radian per second. Okay, and this one here is slope of slope of minus 45. So after 10 and before 0.01, the slope will be 0 degree per decade. Same for this as well, like before, like this slope plus 45 degree is for 0.1 to 10. Okay, and before this and after this the slope is 0. Same for here. The region of interest is 10 times before omega and 10 times after omega. 10 times before this and 10 times after this, the slope is simply 0. Okay, so now let's do the same thing. Like this is a table of results. So at around 0.1, right, what is the overall slope? So at 0.1, which poles are active? At 0.1, which poles are zeros are active? So I observe at 0.1 only this pole is active, right? Just at 0.1. Before this there is no other pole, right? So the slope will be minus 20 dB per decade. I'm talking about the gain. At 1 radian per second, which poles and zeros are active? At 1 radian per second, this pole is obviously active because 1 radian per second is greater than 0.1, and this 0 is also active. Okay, just at 1 radian per second, 0 is also active. So overall 0 provides a pole, 0 provides a slope of plus 20 dB per decade, and pole provides a slope of minus 20 dB per decade. Overall my slope becomes 0, and after 100 radian per second, again I get an additional slope of minus 20 dB per decade. So overall my slope becomes minus 20. So here I have 0 dB per decade, that is due to pole plus 0. Here I have minus 20 dB per decade, that is due to pole plus 0 plus pole. Okay, so that is the thing. So like in my full course I teach a very like all this elaboratively, but here we don't have time. So basically just understand 10 times before this, right, only what will happen? Only the effect due to the constant term will be seen, that is minus 20 dBs that I have derived. Just after 0.1 I will get the effect of the first pole. This is due to the omega p1. Then after 1, right, the effect of omega p1 plus omega z both will be there, and after 100 the effect of the two poles and zeros also will be there. Okay, so this is the Bode plot, Bode gain plot. Bode phase plot, again like it will be a bit tricky for you to understand, but let us break it down. Let me break down few things. So 10 times before this, right, am I getting anything? 10 times before this none of the poles are active. So 10 times before this none of the poles are active. Just at 0.01 the first pole gets active, the effect of the pole is seen. Okay, so I get a 1 angle contribution here. I get a 1 angle contribution between this. Okay, so my slope will be minus 45 degree per decade due to the pole. Now the omega p1 is at 0.1, omega z is at 1, omega p2 is at 100. Okay, so 10 times before this the effect of 0 will come, that is at 0.1. So at 0.1 the effect of 0 also comes, right? So after this both the effect of 0 and the pole will be there. So for how long the effect of pole will be there? 10 times before and 10 times after. So 10 times after the corner frequency is 1, correct, if I multiply 10. So the effect of pole will be till 1 and effect of 0 is starting from 0.1. So from 0.1 to 1 which effects are there? So this will not come, right, because 10 times before this is 10, so it is long way, still long way to come. So only the effect of pole and 0 are there between 0.1 and 1. So overall what will be the slope? Pole will give me minus 45 degree per decade slope, 0 will give me plus 45 degree per decade slope. So overall I will have a 0 degree slope. So it will be pole plus 0. Okay, and what about the other one? So now just after 1 radian per second the effect of the pole is gone. So now still the effect of the 0 will be remaining up until 10 radian per second, and effect of the second pole will start from 10 radian per second. So from 1 to 10 only 0 is there. So I will have a slope of plus 45 degree per decade due to the 0. And after this, right, the 0 effect of 0 will go away, just the effect of pole will be there, which provides a slope of minus 45 degree per decade. I have explained this in a very smaller way, but I hope pause the video, try it out by yourself, think it out, you will be able to figure out, because I think you have studied Bode plots a bit, so you will be good in solving this problem. So the phase plot will be this. Okay, I will not explain this, just by looking at the table of slopes you can do. So while you solve that Bode phase plot, right, it is recommended you write the frequencies, then write the 10 times before and 10 times after, and then check the overall effect which will be lying in the range. Okay, and then you write the table of slopes, and then you draw the plot, Bode phase plot. Bode gain plot is very easy to plot. Bode phase plot is difficult to plot. Rarely they will ask Bode phase plot, but one day they will ask. No one will be able to solve it except you. Okay, so these are few key points you can read about Bode plot, all those things. Okay, so now I will discuss a brief about minimum phase system. Okay, what is a minimum phase system? Basically, minimum phase system is those type of systems in which all the poles and zeros are lying on the left hand side of the j omega axis. Basically, everything is lying here, nothing is lying here. Okay, so example from the following functions, identify the minimum phase system and all those things. So can you say, like, is this a minimum phase system? No, one of the pole is lying on the right hand side. Is this a minimum phase system? Yes, this is a minimum phase system. Okay, is this a minimum phase system? No, because one of the zero is lying on the right hand side. Okay, so that is what the same thing is written over here. If the CLTF of a system is given and it is a minimum phase system, then the system will be stable, but converse may not be true. Okay, so if a system is stable, if a system is stable, it may not be minimum phase system. Why? Because there can be a zero, right? There can be right hand zero. But if the CLTF is given and it is a minimum phase system, then for sure it will be a stable system. Why? Because all the zeros will lie on the left hand side. Okay, so that is one thing. Why is it called a minimum phase system? Just I wanted to show you just a brief why is it called a minimum phase system. Basically, right, if you try to like this transfer function and this transfer function, the magnitude of both the transfer function, right, are same. Okay, both the transfer function, the magnitude is same. What is different? The phase will be different. Okay, so to compare the two transfer functions, if I compare the phase will be this and phase will be this. Okay, so just I hope you know good coordinate geometry. I hope you understand how to calculate the phase of this. Okay, I will not explain over here. So if you just calculate the phase difference, you will see that the G1 transfer function will have a lower phase than the G2 transfer function. That hence it is called a minimum phase system. It has lower distance. It has a lower distance here. If you see, it has a lower distance, right? Sorry, this G1 transfer function, this G2 transfer function, the phase is here, and G1 transfer function, the phase is here. So as it is the lower distance between the 0 degree axis, that's why it is called minimum phase system. Just a interview related thing. Okay, interview related thing. It will not be asked in gate examination. Okay, so now the reason behind why we only draw Bode plot for minimum phase system, because in Bode plot what do you do? We plot the Bode gain plot and Bode phase plot. Generally we plot the Bode gain plot only. So if I write the gain of this, the gain of this will be 1 by under root 1 plus omega tau whole square, and the gain of this will be 1 by 1 plus omega tau whole square. Okay, so both of them have same gain. Both of them have same gain. So Bode plot will be identical. I will not be able to recover my transfer function just from the Bode gain plot. Although the Bode phase plot will be different. Okay, phase plot will be different. You can calculate the phase. Bode phase plot will be different, but Bode gain plot will be same. Okay, so to recover the transfer function just from the Bode gain plot, I will not be able to do that. So engineers told that this is too much of a hassle because drawing the Bode phase plot is a bit difficult. You saw, right? Bode gain plot was very simple to draw, but the Bode phase plot was a bit difficult to draw. So engineers told that we will only draw the Bode plot for minimum phase system. We can draw the Bode plot for a non-minimum phase system. There is no boundation. We can draw it, but it is well established that we will draw Bode plot for minimum phase system, so that I can recover my transfer function from the Bode plot, so that I can tell that this will be my transfer function. To have that convenience, engineers told that we will only be plotting for minimum phase system. We will not be plotting for non-minimum phase system. So this is the step of the Bode magnitude plot, how to plot the Bode magnitude plot. You can read through this. This is the general time constant format which I have explained previously. So let us do a few examples. Let's do this example. I have already done this type of example already. Okay, so first you write the table of slopes. So what are the corner, first you write the corner frequencies. What are the corner frequencies? Corner frequency here, again I have to first of all convert this into standard format. So I will take here common 2, so this will be s by 2 plus 1. If I will take here common 3, this will be s by 3 plus 1. I will take here common 1, that is s plus 1 only. So ultimately my transfer function or OLTF becomes 2 by 3 s by 2 plus 1 divided by s by 3 plus 1 into s plus 1. Okay, now what are your corner frequencies? I have a omega p1 at 3, I have omega p2 at 1, I have omega z at 2 radian per second. So I will go from lower to higher. So I encounter a what do you say? I encounter a pole at omega equals to 1 radian per second. Okay, I encounter a pole at omega equals to 1 radian per second. So this will be at 1 radian per second. I will encounter a pole. So just after 1 radian per second, the slope will be minus 20 dB per decade, because pole contributes a slope of minus 20 dB per decade. Then at omega equals to 2, I encounter a 0. So overall the slope will be 0. Why? Because both pole and 0 are there. Okay, that's why plus 20 minus 20 is 0. Then at omega equals to 3, I will get a slope of minus 20 per decade, because pole 0 are there, so they will together make 0 dB per decade. Then again another pole is there, so that will contribute another minus 20 dB per decade. So overall the slope will be minus 20 dB per decade. So just around 1, I will get a slope of minus 20 dB per decade. From 2 to 3, the slope will be 0 dB per decade. From 3 to infinity, it will go on till minus 20 dB per decade. And before this, right, the value will be constant, and at 0 frequency, what will be the gain? 20 log 1 by 3. Now remember, this 1 by 3 is less than 1, right? This 2 by 3, sorry, not 1 by 3, 2 by 3 is less than 1. So if 2 by 3 is less than 1, that means this, right, this will be my 0 dB axis. I will be lying below my 0 dB axis, because log of any number that is less than 1 will be negative. Okay, so the phase plot I will give you homework, because that will be lengthy task and I don't want to take up so much time to draw the phase plot. Now let's draw the Bode plot for repeated poles. So let me draw the Bode plot for k by a square. So what does k by a square means? So if I draw the k by a square, basically what will be the magnitude? Magnitude will be simply k by j omega whole square. It will be simply k by minus k by omega square. Okay, so now if I write the gain of this, the gain of this will be what? The gain of this will be simply k by omega square. In log terms, it will be minus 20 log to omega square, or I have told you a property of log. I can do this, right? This will be minus 40 log 10 omega. Okay, this will be the property. So if I have repeated poles, they contribute 40 dB of slope, minus 40 dB of slope. So I will get a slope of minus 40 dB. So instead of minus 20 dB here, right, the slope will be more steeper. I will get a slope of minus 40 dB. This slope will be of minus 40 dB per decade for repeated poles. Now this omega GC is actually pretty interesting. What is the omega GC basically? So omega gc is the frequency at which the gain of my OLTF becomes 1. So if I calculate the gain of my OLTF, g of j omega, this will be equals to what? 1. And what is magnitude of g of j omega? Magnitude of g of j omega is k by omega gc whole square, correct? So omega gc is equals to k raised to power 1 by 2. This is what my omega gc is equals to. Okay, now let me come back to this equation. So let's say at omega equals to 1 radian per second, what is the gain? At omega equals to 1 radian per second, the gain g of j1 is simply k, correct? It is simply k. Okay, and at omega equals to omega gc, the gain is simply k, simply 1. So in dBs it is what? 0 dB. In dBs it is what? 20 log k. Now can I apply the slope formula? What is the slope formula? I have told you, right? What is slope? Let me write this as point A and this as point B. So slope AB equals to YB minus YA divided by log of omega B by omega A. Okay, so what is YB? YB is the gain at omega GC. What is the gain at omega GC? 0 dB. So 0 minus YA. What is YA? YA is 20 log K. Okay, YA is the gain at 1 radian per second, that is 20 log K. So it will be 20 log K divided by log of, again, YB by YA. YB is omega GC, YA is 1. Okay, so this will be minus 20 log K divided by log of 10 omega GC. And what is the slope? What is the slope? Slope is minus 40 dB, right? 40 dB per decade. So this basically here comes out to be 2, and from here also, like, you derive the same result only, that omega GC is equals to k raised to power 1 by 2. Okay, this is just a result. Okay, I directly derived here. Okay, and then I did this much amount of hard work and we got this. So ultimately what I am saying is whatever we have done is correct, like if you are getting the correct answer. So now if my like transfer function has n repeated roots, the slope will be minus 20 times n. That will happen. So how do I prove? Just take the 20 log of this. If I take 20 log of this, it will be 20 log 10k minus 20 log 10 into s raised to power n, right? Not s raised to power n, omega raised to power n, because I am only discussing about the magnitude. Magnitude, what does the magnitude become? Magnitude becomes j omega equals to k divided by omega raised to power n. Okay, so this will be 20 log k, this is just a constant, minus 20 n log of 10 omega. So this log of 10 omega is v, if you remember the mapped function, and 20 n is the slope. So for n repeated poles, I will get minus 20 n slope. For m repeated zeros, I will get plus 20 m zeros. Okay, and what about the angle? Angle, for the angle, right? Basically for the angle, the slope will be minus 45 into n, and after the 10 times the corner frequency 10 times omega greater than 10 corner frequency, the angle contributed will be minus 90 into n. Okay, this have been taught in polar plot as well. Okay, so this is for the region for 10 times before corner frequency and 10 times after corner frequency, in this region only. Okay, omega c is the corner frequency. In this region only this equation is valid. This is the slope and this is the angle contribution. Angle contribution. Okay, So like what will be the Bode gain plot? Simple, right? It will be decreasing obviously, but the slope will be minus 20 n dB per decade. That's it. That will be the slope. Okay, initial value will be what? Initial value will be 20 log of k, and this value will be what? Again, this will cut omega gc some point, right? It will cut the omega gc at some point. What will be the value of omega gc? Omega gc will be k raised to power 1 by n. You can directly put it in the like formula gain plot, you can do. Okay, so for 0 as well, I'm not deriving it. It is same. It will be just plus 20 dB per decade slope. Just the difference will be here. The gain will be what? What is my transfer function? Transfer function g of j omega is minus k omega whole square, or if I want to write the magnitude, it will be k omega whole square. So if I equate this with equals to 1, so my at omega gc becomes what? K raised to power minus 1 by 2. For s raised to power n, my omega gc will be k raised to power minus 1 by n. And what will be the slope? Slope, did I write the slope previously? No, the slope, right, previously this slope will be plus 20 dB, plus 40 dB per decade, because I have two poles now. I have two poles now. Here as well, the slope will be plus 20 times n dB per decade. Okay, so like these are the same thing. The summary is written over here only. You can pause the video and see the summary. Okay, so now let's recover the transfer function from Bode magnitude plot. Okay, so like first let's do a few basic questions like this. Okay, so if you have to find the DC gain of this transfer function, what is the DC gain of this transfer function? DC gain of this transfer function is the gain at which omega equals to 0. If I put here omega 0, this will go, this will be 1, this will be 1, this will be 1, the DC gain will be 100. Okay, what is the DC gain of this transfer function? The DC gain of this transfer function, if you put omega equals to 0, this will be 1, this will be 1, this will be 1, and you will say DC gain is equals to 1, and I will say you are wrong. Okay, because you are ignoring this. There is a very huge misconception that you just remove the zeros, remove the poles at 0, s equal to 0, and just calculate the DC gain. No, for this, right, DC gain does not exist. Okay, DC gain is infinity. DC gain is infinity. Okay, DC gain does not exist. Okay, so I hope you understood this misconception. Let's now solve a gate question which came in GATE EE 2001. Okay, so let's solve this one. The asymptotic approximation log magnitude plot is shown for a minimum phase system with real poles and 1 0. So it has 1 0. This much I know. Number of zeros equals to 1 is shown here. Okay, then what are they asking? They are asking what will be the transfer function. So basic thing what I understand, here the slope was minus 40, here the slope is minus 60. So obviously after this a pole must have been added. So here a pole is added. So I can say at omega equals to 2, I have a pole. Here I observe, here just before this frequency the slope was what? Minus 60 dB per decade. Here the slope is minus 40 dB per decade. The slope increase plus 20 dB per decade. That means I have a 0 here. I have a 0 at omega equals to 2. I have a, sorry, not 2, sorry, at omega equals to 5 I have a 0. Now after this, right, here before this the slope is minus 40, after this the slope is minus 60. That means again a pole has been added because I am subtracting the slope. So here at omega equals to 25 a pole is getting added. That's it. So I can say I have a pole at omega equals to 2. Yes, I have a pole at omega equals to 25. Yes, I have a 0 at omega equals to 5. Yes, it is matching. Okay, it is matching, but all of them are matching. All of them are matching. But this is not correct, right? I don't have two poles at omega equals to 2. So this is definitely incorrect. This will be gone. And also, if I see initially, right, I forgot to mention, if I have poles at s equal to 0 or zeros at s equal to 0, that discusses about the initial slope. So if you have seen the previous part, initially the slope was minus 40 or plus 40. Okay, so here initially the slope is minus 40. Which one will provide me minus 40 dB per decade slope initially? Which provides me? Pole
at s equal to 0, 2 poles at s equal to 0. So this is a possible option, this is a possible answer. Now which one I will choose? So for this, right, they have given you a hint, this one is the hint. So basically what they're telling, this I have gain of 54 dB at omega equals to 0.1. Of course I cannot start from 0, but at 0.1 I have a gain of 54. So if I find out the gain at 0.1, right, if I find out the gain at 0.1, basically at 0.1, right, that is the low frequency region. So if I find out the gain for these two expressions will always be similar except this constant term, okay. So this one will be ignored basically, because what will happen, it will be 0.1 whole square plus 2 square, so that is almost equals to 2 square only. So automatically this one will be ignored, this one will be ignored, so the value will come out to be like, I have to choose, right, so it will be 5 whole square whole under root, because I'm ignoring the 0.1 whole square. I hope you understand. I have just replaced s with j omega, then I'm putting omega equals to 0.1, and as I'm doing the magnitude, it will be omega square plus 5 square, something like that. So 0.1 whole square is getting ignored here. So it is 5 square whole under root, then it is 2 square into 25 whole square whole under root. Okay, so and of course I have, but this one I cannot ignore, right, it doesn't have any constant term with it, so this will be 0.1 whole square. Okay, I hope, like, I'm just skipping few steps, I hope you can do this. Okay, I hope you can do this. So this will be like, here I will have a constant term because I don't know exactly what is the transfer function, so I will write here some constant term k. This is not the DC gain, okay, this is just a constant term to identify whether it will be 20 or 50. Okay, so this will be k into 5 divided by 500 into 2 into 25, so this will be 50, this will be 10. So k into 10 is equals to 54 dB, but this is not in dB scale, right, this is in decimal. So I will convert 54 dBs into decimal scale. So 54 dB will be equals to 20 log of x in decimal scale. So basically what I need to do is, I need to do 10 raised to power 2.7, that will be equals to x. Okay, I hope you know how to convert from dB to decimal scale. Okay, so let me do this. So it will be 10 raised to power 2.7, it will be 501. Okay, x will be approximately equals to 501. This is equals to 10 times k, so my k ultimately comes out to 50, almost equivalent to 50. So answer will be option D. Okay, I skipped a few steps, I hope you can do this because I have to solve more questions as well. So this is up to you, I'm leaving it up to you, the middle steps I'm leaving up to you guys. Okay, so how do you identify the transfer function? This is how, like, whatever I have done, that is how you identify the transfer function. You identify the corner frequencies, observe the initial slope. If I have initial slope, that means either I will have poles or zeros at origin. Okay, then determine the change in slope at the corner frequency. From that you will understand whether a pole is getting added or a zero is getting added at that particular corner frequency. Just hold on a second. Yeah, so then you have to find the value of k. So k, right, will always not be in k will always not be in DC gain. It is not a DC gain, it is just a value, it is just a value. Okay, because sometimes we have to equate this with the transfer function, then only we will be able to find this out. Okay, so then you write the transfer function in the time constant format, and then from there you will find out. Okay, let's solve a more recent question from gate. Okay, so one more information I think I missed here. Yeah, I think I did not write here. Okay, so this right here, very important relationship is, it is there, 1 decade is 10 by 3 octave. Okay, so what will be 20 dB per decade in octave scale? So 20 dB will be, this will be 20 dB by 1 decade. Okay, so what is 1 decade? 1 decade is 10 by 3 octave, 10 by 3 octave, so it will be 6 dB per octave. This is a very important relationship. Sometimes they give in octave scale, sometimes they give in decade scale, so try to remember this relationship. Okay, don't forget this relationship. So let's now move and solve few questions. So this is the first question. So we have to identify the transfer function. So I can observe that initially
have they given any slope? They have not given me any slope. Okay, but I can identify the slope. At omega equals to 1, the value is 32. At omega equals to 10, the value is minus 8. So I can find using the slope formula. So yb is minus 8, ya is 32 divided by log of omega b by omega a. Omega b is 10, omega a is 1. So the bottom becomes 1 and this becomes minus 40 dB per decade. Okay, this is the slope. So if initially my slope is minus 40 dB per decade, that means I have two poles at the origin. So either this one is a possibility or this one is a possibility. How do I choose which one is the correct one? Simply you check the gain at omega equals to 1. So the gain at omega equals to 1 is 32 dBs. Okay, so what is the value in decimal scale? It will be 10 raised to power 32 divided by 20. So it will be 10 raised to power 1.6. So 1.6 10 raised to power this is 39.81. Okay, so basically my transfer function, right, g of s will be something like this, k by s square. This much I know. Okay, and I know the gain at 1 radian per second is 39.81. So this will be equals to k by omega square, 1 square. Okay, so k is basically 39.81, which is present in the option B. So option B will be the correct answer for this question. There are other ways to solve this as well. Okay, you can solve it any way you like. Let's solve this question. So the Bode magnitude plot is shown and the transfer function is also shown. They have already provided you the relationship of octave and decade scale. They're asking A by BK. So first of all, I identify this is in the standard time constant format. That is the first thing. Now they're telling me that I have a 0 at s by omega z, right? It is 2, 0 at 2. Okay, I hope you remember the time constant format. I have a 0 at 2 because I have to take the inverse of this. Okay, then I have another 0 at 1 by a. So this is omega z1, omega z2 is equals to 1 by a. Can I identify from the plot where is the 0? So here, right, my slope suddenly increased. What is the omega 2? So this 0 is already increased. This 0 is already included here, and slope increased by 6 dB per octave, that is 20 dB per decade in decade scale. So that means this is correct. I have a 0 at omega z equal to 2. Here again at this point I observe the slope has increased again 6 dB per octave. That means again at this corner frequency a 0 has been added. That means this 1 by a is 4. At 4 radians a 0 has been added. So a actually becomes 1 by 4. Okay, first point. Next point is, what about B? I have a pole at omega p1, that is at 8 radian per second. Then I have another pole at 1 by b radian per second. Then I have another pole at 1 by 36 radian per second. Okay, so 1 by b is let us check. So here, right, after 8 I see my slope has reduced from 6 dB per octave to 0 dB per octave. That means in decade scale it has reduced to minus 20 dB per decade. That means a pole is getting added here, which is exactly what as I have written here, right? So what about here? Again at 24 another pole will be added because the slope has reduced to minus 6 dB per octave. That means this will be equals to 24 radian per second. So B is 1 by 24. What about this one? I see here at 36 radian per second another pole is getting added because the slope reduces to minus 6 dB per octave. So this is correct, everything is tallied. So B is 1 by 24, A is 1 by 4, but I don't know what is the value of K. I don't know what is the value of K. How do I find out what is the value of K? So I observe the K value, right? They have shown me that if I just extend this line extends to 8, connects at 8. Basically what they're telling me, if I would have just seen this as my transfer function, then it would have crossed the 0 dB line at omega equals to 8. Basically what they're telling me, there is obviously this is the shortcut I'm telling you. You can solve it using basics. Okay, so basically what they're telling me, if my transfer function, let's say, was something like this, k by s, right, because initially I'm getting a minus 6 dB per octave, that is in decade scale it is minus 20 dB per decade. So if initially my like transfer function is this, then the omega gc for this transfer function, right, would have been 8. From this I will be able to see find out the k. So what will be the value of k? Value of k will be k by omega gc is equals to 1. Gain at omega gc is simply 1. Okay, just directly writing the gain. And what is omega gc for these, for only for this portion, right? Only for this portion is 8. So it will be k will be equals to 8. So k is 8. You can do it using the slope, basic slope method. You can do it, there is no boundation. Okay, but I have, like, we can solve this in this small amount of time. Actually the question was bit lengthy. Okay, so now what they have asked me, a by b will be 1 by 4 divided by 1 by 24 into k is into 8, so this will be 3, so this will be 3 by 4, so this will be 0.75. So your answer will be 0.75. Okay, so this is how you can solve this question elegantly. Let's solve few more questions. Okay, this is another question. Consider the Bode magnitude plot. Which one of the following transfer function is best represented for the Bode magnitude plot? I can observe that initially my slope is what, plus 20 dB per decade. That means I have a 0 at the origin. So this is what shows me I have a 0 at the origin. This also shows me I have a 0 at the origin. Okay, now let's discuss about the point 0.5. So I see at 0.5 I am touching the 0 dB axis. That means what, again the same process, right? If my transfer function was just ks, then for this transfer function the omega gc would have been 0.5. Okay, so basically if I write the gain, k into omega gc should be equals to 1, because gain at gain crossover frequency is 1. So omega gc is 0.5, so k becomes 2 from here. So all these are in time constant format. So I see k is 2 here, k is 2 here. Okay, so this is gone, this is gone. These are the possible solutions. Okay, here if I see around here, right, I see my slope was 0 dB here. After this it became minus 40 dB per decade. How do I know it is 0 dB? Because the value is constant, that's why the slope is 0. There is no change in y. Okay, so this is going to minus 40. So from 0 dB I am going minus 40. That means 2 poles have been added. That means this is only possible case, right? Because on this option there are only single poles, there are non-repeated poles, right? So one pole already have been taken care here, there should be 2 more poles, but here this is telling me I have only 2 poles. Not possible. So option A will be the correct answer for this question. Like you can solve this using lengthy method as well, there is no boundation. Okay, so let's now move on to the next question. Next topic, that is error in the asymptotic Bode plot. Okay, so basically I have given you a brief about the error. So how do you find out error? Basically you find the approximate value at the Bode plot, whatever the Bode plot tells you, then you subtract with the actual value, actual transfer function value, then you will calculate the error. This I have described previously as well, I hope. Okay, and how do you find out the error at corner frequency? So what does the Bode plot gives me at this point of time at 1 by tau corner frequency? Bode plot, the value of Bode plot is 20 log k. Okay, this is the value of Bode plot, and the value of the actual transfer function, if I have n poles, it will be 20n into log 100 1 plus omega tau. Like just apply log. Okay, now the Bode plot value is 20 log k. If I have n poles, if I have 100 poles, if I have n plus 1 poles, how many poles I have, the Bode plot value at the corner frequency is 20 log k. You can understand. I hope you do the approximate analysis, because for approximate analysis we assume omega tau to be very lower than 1, hence this term gets eliminated in approximate analysis, but in exact analysis we cannot eliminate this term. Okay, so basically like this is the phase error and this is the like magnitude error. So magnitude error will be this term only, this term will be magnitude error, which is written later on. Okay, I have shown you here the magnitude error comes out to be this one. So actual value comes out to be this. Why? Because I have just replaced, like at corner frequency I have replaced omega, with 1 by tau. If I replace omega with 1 by tau, this will be 1 plus 1 raised to power n. Okay, I think that is the case here, not 1 raised to power n, because I will, sorry, not 1 raised to power n, so not 1 raised to power n, this will be square only, as I have just hold on here. Okay, yeah, so if I replace, right, this is 20n, that is fine. If I replace here omega tau equals to 1, this will become 2 under root. So this is 2 raised to power half, so half can come outside, that's why this becomes from 20n, this becomes 10n. Okay, and log of 2 is 0.3. Apply in calculator, log of 2 is 0.3. So 0.3 times 10 is 3n. So ultimately, right, actual value is 20 log k minus 3n. Okay, actual value, and the approximate value is 20 log k. that is shown in the graph here, 20 log k. So what will be the error? Error, if I subtract these two things, error will be minus 3n. So as the number of pole increases, the error also increases at the corner frequency. More the poles, number of poles, repeated poles, more the error. Okay, and for the angle as well, you can find out the error at corner frequency. The error will always be 0 for angle. Okay, so this is the conclusion. You can like either you can remember this, or you can, like I have derived it this, you can go through this. Okay, there is nothing to say over here. Now like already you know what are the relative stability parameters. So with Bode plots we will try to find the relative stability parameters. Let's do a quick revision of what is a gain crossover frequency. Gain crossover frequency is the frequency at which the magnitude of OLTF becomes 1. Remember, Bode plot can be plotted for any transfer function, closed loop transfer function, open loop transfer function, any function. Okay, it can be a function of frequency as well, or not a function of frequency. If it is a complex number, then it can be plotted. Okay, but right now as I am discussing about relative stability parameters, I am only discussing about OLTF. So Bode plot generally can be plotted for anything, but generally in control systems we plot Bode plot of OLTFs to identify the phase margin, the gain margin. Okay, so and also obviously for unity negative feedback systems, because relative stability parameters exist for unity negative feedback systems only. So what is gain crossover frequency? Gain crossover frequency is the frequency at which the magnitude of OLTF becomes 1. Phase crossover frequency is the frequency at which the phase of the OLTF becomes minus 180. This has been already taught to you. Gain margin definition also has been taught to you. In dBs also it has been taught, and phase margin definition has also have been taught to you guys. Okay. Now we will do few questions related to this. Okay. So here, what is the phase margin here? So like we can solve the phase margin. You calculate it using the asymptotic Bode plot. So they want you to calculate the phase margin using the asymptotic Bode plot. So like although the answer is written already over here, but I will just calculate this quickly. So if how do you calculate the phase margin? To calculate the phase margin, what you have to do? You have to first like plot the phase. First identify the gain crossover frequency. To identify the gain crossover frequency, you have to plot the gain Bode gain plot. Okay, so this will be omega, this will be the magnitude g of j omega. So if I draw the Bode gain plot, this is not in our standard time constant format, so we have to convert this into our standard time constant format. So this will, if I convert this into our standard time constant format, this will be 10 divided by 0.1 into s divided by 0.1 plus 1 into s plus 1 into 10. I will take common s by 10 plus 1. Okay, so ultimately what it gets back to is this becomes 10 only. This becomes 10 divided by s by 0.1 plus 1 into s plus 1 into s by 10 plus 1. Okay, so ultimately the value, what does the value become? So the value becomes this. Okay, so now I have a corner frequency at 0.1 radian per second. So at 0.1 radian per second, I will exhibit a slope of minus 20 dB per decade. Then again at 1 radian per second, I will exhibit a slope of minus 40 dB per decade. This will be 1, this will be 0.1, this will be 1, and at 10 radian per second, I will exhibit a slope of minus 60 dB per decade. So this is minus 20 dB per decade, this is minus 40 dB per decade, this is minus 60 dB per decade. So basically what it means is that if I move, like what does this mean? If I move a decade, then my slope will be, then my magnitude will be reduced to 20 dBs. So here, right, I have moved a decade, right, 10 times this. That means my magnitude should reduce, whatever the magnitude I have here, it should get reduced by 20. Okay, so how do I know what is the magnitude here? So I will not be able to know, I have to write the values actually. So here, right, what you can do is at omega equals to 1, because what I have to know, I have to identify the gain crossover frequency. So the gain crossover frequency will be the frequency at which this crosses 0 dB per 0 dB axis, right? That will be my gain crossover frequency. So somehow I have to identify this value. So how do I identify this value? So you can identify this value with the help of the gain here, right? So if you calculate the gain at 0.01, okay, what will be the gain at 0.01? The gain at 0.01 will be, or let's say what is the gain at 0.01, right? All this will be ignored. At 0.01 the magnitude, all this will be ignored. Basically this 10 will be left, so the gain will just be 20 dBs, around 0.01. You can calculate, you put here omega equals to 0.01, you will say approximately the gain comes out to be 10. In decimal scale, in dBs, it will be 20 dBs. Okay, what about 0.1? So we, as it is an approximate Bode plot, they should have mentioned this. We will take the approximation that at 0.1 the gain is also same 20 dBs. Okay, because after 0.1 only the slope changes, correct? After 0.1 only the slope changes. Before that I get a constant value. This I have taught previously as well, right? Before the slope there is no slope, that means I will get a constant value. At DC gain, like at DC gain is 10, hence I will start with 20 dBs. Okay, now as I was saying, the definition of this is, if I move a decade, then my y value will reduce by 20 dBs. So initial value is 20 here. So if I move a decade, the y value will reduce 20. So final value here, right, this will be 0 dBs. Okay, so actually the gain crossover frequency is 1 radian per second, because the 0 dB happens at 1 radian per second. So this is my gain crossover frequency. You can see, right, I am using all the concepts. Because GATE does ask question conceptually. They do ask question conceptually. Just see how good conceptual question they asked. Okay, so here I got the omega GC. Omega GC is 1. So I have to find out the phase at this omega GC. Okay, I have to find out the phase at this omega GC. This will be a bit difficult and tricky. Okay, so you have to bear with me here. So what are my locations? So I have first pole at 0.1. I have second pole at 1 radian per second, and I have third pole at 10 radian per second, correct? These are my pole locations. Here. Okay, now what I have to do is I have to write the ranges. So the effect of first pole will be present 10 times before, that is 0.01, and 10 times after, that is 1. Effect of second pole will be visible from 10 times before, that is 0.1, and 10 times after, that is 10. Effect of the third pole is visible 10 times after, that is 100, 10 times before, that is 1. Okay, so now, so 10 times, like before 0.01, right, none of the poles are effective, so the overall slope will be 0. In this region, what is active? This is active, omega p1 is active. Is omega p2 active before 0.1? No. So only I will get one pole, minus 45 degree per decade, due to omega p1. And in this region, how many poles are active? Yes, omega p1 is active in this region, omega p2 is also active in this region. So the slope will be minus 90. Two poles are active, omega p1 and omega p2. Just see how good this question is. And educators teach question like this, just रट्टा मार लो कर लो हो गया, ठीक है? तो ऐसा नहीं होता. तो then this what is the slope in this region? But I will just take care of until this region. After this I will not draw the Bode phase plot, because I have to find the phase at omega equals to 1. So I will only take care until this region. Okay, so in this 1 to 10, right, obviously the effect of omega p1 is gone, effect of omega p2 is there, and just omega p3 has just started. So still I have two poles, but these are different poles. This will be omega p1, omega p2, and omega p3. Okay, so now I can draw the Bode plot. So initially none of the poles are active, so all of them are providing 0 degrees angle. Okay, now what is happening at omega equals to 0.01, omega p1 gets activated. So here this is 0.01, omega p1 gets activated, so my slope will be minus 45 degree per decade. Okay, this slope is minus 45 degree per decade. Then again at omega equals to 0.1, my slope becomes minus 90 degree per decade. Slope will become minus 90 degree per decade. Okay, then the slope remains same only after 1 as well, the slope remains same. Okay, so here this is the point of omega equals to 1 where I have to find out the phase. So here I start with 0 degree, and as I have moved here a decade, that means my value will reduce by what? 45 degrees. So if I move by a decade, my value will reduce by 45 degrees. So this will be minus 45. Okay, again if I move another decade, my value will again reduce by 45 degrees. Correct? No. What is the slope here? The slope here is minus 90 degree per decade. So how much my value will reduce? If I move a decade, the value will reduce will be 90 degrees. So here this will become minus 135 degrees. Okay, at omega equals to 1. So omega equals to 1, my phase is minus 135 degrees. This is the point of interest. So what is the phase margin? Phase margin is the angle of g of j omega at omega equals to 1 plus 180 degrees. Okay, so this will be equals to plus 45 degrees. That is what is written at the start of the question. So phase margin answer will be plus 45 degrees. Just see the beauty of this question. Okay, how good this question is, and I can assure you many of the educators will skip this question. Okay, many of the educators will skip this question because I'm not blaming them. Just what happens is generally the Bode phase plot, right? Bode phase plot is not taught to you. Bode phase plot is not taught, okay, correctly. So that's why they skip this question, because it involves Bode phase plot. Okay, so again this topic is done, Bode gain phase plot. Now we will discuss about the steady state error. How can I find out the steady state error? So there are a few things like this coefficient, type 0 system, positional coefficient. I don't like this. I don't like this method. I have to teach this because everyone teaches. So I have to teach this. If I don't teach this, then obviously you will say, sir, you didn't teach this. Solve with basics. Solve with basics. This error coefficients are there. Okay, I don't recommend going by this. You can see through the question and solve this. Like all this summary is there, but what I will recommend, right, solve with basics. Okay, so let's see. Let's solve this question. So the Bode asymptotic magnitude plot of a minimum phase system is shown below, okay, in the figure. Okay, you can pause the previous slides and just see whatever I have said, right? You can pause the slides and check whatever I have said here. Okay, so but I will solve with basics. So the magnitude plot is shown. The system is connected to a unity feedback system. Obviously we are discussing for error. Generally error will be discussed for unity negative feedback system only. Okay, find out the steady state error of the closed loop system for a unit ramp input. So first of all, I will try to find out the CLTF. Okay, so the OLTF is shown. I will recover the transfer function and then I will discuss about the CLTF. I see what is the initial slope. If I move a decade, right, 0.1 to 1, I have moved a decade, the y value has reduced by 20 dBs. That means the slope here is, slope is how much? Slope is minus 20 dB per decade. Okay, slope is minus 20 dB per decade. Now so initially I have a pole at the origin. So the Bode plot has a transfer function OLTF has a pole at the origin. Initial slope is minus 20 dB per decade. Now I see at omega equals to 2, the slope goes from minus 20 dB per decade to 0 because the value is constant. So I observe I am getting a 0 at omega equals to 2. Then again at omega equals to 10, the slope reduces to what value? So if I move a octave, my slope reduces to 6 dB. So the slope is 6 dB per octave, minus 6 dB per octave. And what is minus 6 dB per octave in decade scale? Minus 20 dB per decade. Okay, so basically again the same thing, only I am seeing a contribution of a pole at omega equals to 10 radian per second. So this is my transfer function. Only one thing is left to find out the value of k. How do I find out the value of k? Through this hint. At omega equals to 0.1, they have given me the value is 26 dBs. Okay, so if I replace here 0.1, right, this will be almost equals to 1, this will be almost equals to 1. I am talking about the magnitude. I am talking about the magnitude. Try it out by yourself. Try it out by yourself. Magnitude of g of j omega. If you put omega equals to 0.1, you will approximately get the value as k by omega. Just use the magnitude formula. You will approximately get the value of k by omega. So the magnitude is 26 dBs. Of course, I don't like dBs. I like in decimal scale. So we'll convert this in the decimal scale. So if I convert this in the decimal scale, okay. So if I convert this in the decimal scale, this will be 26 divided by 20. So 1.3 and 10 raised to power, this almost equals to 20. This will be almost equivalent to 20. Okay, so it is almost equivalent to 20. So this is equals to 20 at what value? At omega equals to 0.1. so I will replace here omega equals to 0.1, so k value comes out to be 2. So my transfer function, right, my transfer function is 2 s by 2, not my transfer function, my OLTF is 2 s by 2 divided by s by 10 plus 1. Okay, this is my transfer function. Now how to discuss about the error. So like I hope you remember all the unity feedback, negative feedback system. What is error? E of s is simply r of s minus c of s. Okay, I hope you know all these things. This is my expectation. So this value comes out as E of s equals to c of s, not c of s, sorry, r of s, I will take common, into 1 minus c of s by r of s. Okay, system has to be stable because they have asked a NAD type question, so system will be definitely stable. Okay, for those people who understand this, they will understand. Okay, so now I need to write the transfer function. So it is a negative unity feedback transfer function. So this is my g of s. My transfer function t of s will be c of s by r of s, which is equals to g of s by 1 plus g of s. So this will be like, what is my steady state error? Steady state error will be limit as s tends to 0 s e of s. So this will be s into r of s. R of s is for a unit ramp input, right? Unit ramp input will be the Laplace of unit ramp will be 1 by s square. Okay, 1 by s square, 1 minus, this is g of s upon 1 plus g of s. So ultimately this will be 1 plus g of s minus g of s divided by 1 plus g of s. Okay, I am doing it with basics. I am not telling you to remember any formula, no formula. Okay, so this will be 1 by s into numerator will be 1. Of course, don't forget limit as s tending to 0. Okay, limit as s tending to 0. This divided by 1 plus g of s. So what is 1 plus g of s? So if I write 1 plus g of s, right, it will simply be s by 10 plus 1 into s, of course, will be there. Okay, plus 2 into s divided by 2 plus 1 into, like, I hope, like, I'm just doing some bit of step manipulation. I hope you can do this, right? I hope you can do this. So this will be simply s into s by 10 plus 1. So what will happen? Ultimately this s and s will get cancelled. Okay, s and s will get cancelled. So here, right, now I can put s equal to 0. If I put s equal to 0, this will become 0 by 10 plus 1 divided by 0 plus 2 into 0 by 2 plus 1. So this will ultimately come out to be 1 by 2. So your steady state error will be 0.5. Did I tell you to remember any formula? No, right? All these slides are there. I have to also explain these slides because other educators teach this. If I don't teach this, you guys will give me slang. Okay, गाली दोगे आप मुझे कि आपने क्यों नहीं पढ़ाया ये क्यों नहीं पढ़ाया acceleration error coefficient क्यों नहीं पढ़ाया? But did I use any formula? No formula I used. Just this final value theorem I used. Okay, I also solve with basics. I understand your pain. Of course, I understand if you remember the formula, right, you will be able to solve this very quickly, but you will forget the formula. That is the point, right? You will forget the formula. I know that. So how many formulas you will remember? You have so many things already to remember, right? If I tell you another thing to remember, this will be a burden to you. I don't want it to be a burden to you. Okay, so I hope you have understood the steady state error. Now, just last topic is left, the Bode plots for standard second order systems. Okay, so for a standard second order system, I will just go bit quickly here. So what will happen is, we are discussing for underdamped systems. Okay, for overdamped systems, it has already been discussed. I will explain what do I mean by it. Okay, but one thing is for sure, if I am seeing that this is a OLTF of a standard second order system, OLTF of a standard second order system. I have a pole at the origin, that means it is a type 1 system. That means I will get a slope of minus 20 dB per decade. Okay, and I have order 2, I have another pole at somewhere, so hence the ending slope will be minus 40 dB per decade. Okay, minus 40 dB per decade. This is the ending slope. Okay, so for OLTF is fine. OLTF is easily, we can draw the Bode plot. The problem comes when I try to plot the Bode plot of a CLTF of a standard second order function. What is the problem? Problem is, previously, right, all the pole locations were real, but now if my zeta is between 0 and 1, right, if my zeta is between 0 and 1, the pole locations are complex. Okay, then things become a bit tricky. Like the derivation is here, things become a bit tricky. You will not be able to find out the corner frequency. What we do a very neat thing. Okay, so first let me write the, like, this is the magnitude response. What will be the angle response? So here, if you observe, when my omega is less than omega n, okay, this whole value anyways will be always positive. Okay, fine. So okay, this will be n square. Okay, yeah, I'm talking about here. How do you write the angle? Because this is a complex number, right? Let's write this complex number as x plus jy. So when my omega is less than omega n, then x is positive. That means I am lying in this quadrant. Y is always positive. That means I am lying in first quadrant. But when my omega is less than omega n, when my omega is greater than omega n, then this becomes negative. That means x is negative, y is positive always. So I am lying in the second quadrant. So the angle calculation is different for different quadrants. So if my omega is greater than omega n, then this angle becomes minus tan inverse mod of y by mod of x. Okay, if I am lying in the second quadrant, that is omega greater than omega n, then the angle becomes minus 180 plus tan inverse mod of y by mod of x. This I hope you know how to calculate the angle in different quadrants. So same thing I will write here. So this will be minus tan inverse mod of y over x. What is y? Y is 2 zeta omega by omega n. Okay, divided by mod of 1 minus omega whole square by 1. Okay, so this is when omega by omega n is less than 1. Okay, and this will be equals to minus 180 degree plus the same thing only, but this will be plus, and this will be when my omega by omega n is greater than 1. Okay, so they have two different angle definitions. Okay, now again, if I do the approximations for omega much less than omega n, what will happen is the magnitude will be almost equals to 1. Why? If I put here omega much less than omega n, this will be almost equals to 0. This will also be almost equals to 0. So only 1 will be left. That's why it will be almost be equals to k. Okay, what about the what will be it in dBs? In dBs it will be 20 log of k basically in dBs. Okay, if k is 1, it will be 0 dBs. Okay, what about the angle? Angle will be like k angle of t of j omega, right? For low frequency region, if like in this region, right, if omega is 0, if omega is 0, angle will be 0 simply. Angle will be simply 0 degrees. Okay, for low frequency region. Okay, now what about the high frequency region? For high frequency region, if my omega is very greater than omega n, then the transfer function changes. Okay, so this is my transfer function, correct? I will copy. Can I copy my transfer function? No, I cannot copy my transfer function. So if omega is greater than omega n, right? So this one, right, I can ignore. This will dominate. This term will dominate. Again, this term will dominate. So ultimately, right, what will I get? This will be omega by omega n whole raised to power 4. So what do I mean by it? So my transfer function will become, this will be k divided by whole under root minus of omega by omega n whole square plus 2 zeta omega by omega n whole square. Okay, I hope like initial simplification you can do, right? I have not taught you how to do simplification, just initial simplification you can do. Now what I can say is this will again dominate this one. Why? Because here I have omega raised to power 4, this is omega square, so this will dominate than this one, so this I can ignore. So ultimately this will come out to be k by omega n whole square. Okay, this will come out. Why? Because this can be ignored, because this is omega raised to power 4. Okay, so my magnitude of the transfer function comes out to be this. Okay, omega n square by omega. So if I calculate the magnitude, this will be in dBs, this will be 20 log of k, and if I want to write like in terms of omega, right, this will be 20 log of plus 20 log of omega n square minus 20 log of omega square. Okay, so my value comes out to be 20 log k, that is the DC gain, plus 40, you can write 20 as well, it doesn't matter, 20 log omega n square minus 40 log omega. So what am I observing? That for very high frequencies the slope is like this, tells me the slope, right? Slope is minus 40 dB per decade, and for low frequencies the slope is almost 0. Okay, slope is 0. Like the magnitude was constant 20 log k. Okay, what about the phase? So the phase, if I write here, if my omega is very large, that means it is tending to infinity, so I will be lying in this region. So if I am lying in this region, if omega is very large, so in the top I have a power of omega, in the bottom I have a power of omega square. So omega square will dominate omega, so ultimately this will tend to 0. So ultimately my phase will be minus 180. So my phase will be minus 180. Okay, I hope you have understood this point. My phase will tend to minus 180 approximately. Okay, what is the problem? The problem, everything is fine. In low frequency region, this is the gain, this is the angle. In high frequency region, this is the gain, angle is minus 180. But in this whole expression, there is no zeta. So what is happening? The information about zeta is getting lost. So when we plot the Bode plot of CLTF, now we are plotting the CLTF of a second order standard transfer function. The zeta, information of zeta is actually lost. What we do, we assume that the asymptotes meet at omega n. So we assume the corner frequency of a standard second order transfer function, closed transfer function CLTF, is omega n. Is it actually? No. We have complex poles, right? We have complex poles. So the poles are somewhere here, right? S equals to like if you remember, the real part is zeta omega n and the imaginary part is plus minus omega d, or this can be written, omega d can be written like this as well, minus zeta omega n plus minus 1 minus zeta square into omega n, if you remember this, right? What we are telling, we just take the magnitude of this s. Okay, just take the magnitude will be what? Magnitude of any complex number will be real part whole square plus imaginary part whole square, 1 minus zeta square into omega n whole square. So this will be equals to, this will be like, ultimately if you simplify you will get omega n. So we are telling just take the magnitude and assume that to be your corner frequency, and assume that we are getting two poles at this corner frequency. That's why the slope goes from 0 dB to minus 40 dB per decade. So if my zeta is 0, right, then if you just plot the exact transform function for zeta equal to 0, you will see at omega r equals to omega n, that is at resonant frequency, the function will blow up. Basically the function will blow up. Why? Because if zeta is 0, then your transfer function is s square plus omega n square, something like this. Okay, you replace s with j omega, so this will be minus omega square plus omega n square. Now if you put here omega equals to omega n, this will be infinity. Okay, so that is what is happening. Same thing, okay, this is already written in this next only, though it will blow up basically it is not good for us. Okay, so what will be the Bode magnitude plot? High frequency region, what is happening? High frequency region, again, if my omega is very greater than omega n, then my magnitude will be k by omega square. Okay, if my omega is very greater than omega n, magnitude will be k by omega square. Okay, if my omega is very less than omega n, my magnitude will be, in the low frequency region it is constant, that is k by omega n square. Okay, so again I observe that, of course, if I take the 20 log of this, I will get the the magnitude to be 20 log k minus 40 log of omega. So like you can see, I am getting a slope of minus 40 dB per decade. So what is happening, that I have this value 20 log k, and to represent, like what we do to represent that this is a undamped system, we draw our Bode plot like this. At omega n, my magnitude is infinity, right? It blows up. So we show our Bode plot like this for a undamped system. Okay, what about for underdamped system? For underdamped system, like what happens, as the zeta increases, this gain comes from here to here. Okay, so like this is for an underdamped system. I hope you have seen the bandwidth and all those things. Okay, these have been taught in frequency response of second order systems. So for underdamped system, what we do is simply I tell that omega n, I have got two poles, it is my corner frequency, that's it. The problem is we lose information about zeta. There is no information about zeta on this graph. That is the only problem with this approximation, but we have to do approximation, right? So when our roots are complex conjugate, we assume the corner frequency to be at the magnitude of the complex conjugate root. Okay, very important point. Okay, very important point. So what is the error? Error, if you want to calculate, right, you calculate exactly, error will be maximum again at the corner frequency. Okay, you calculate the magnitude of the transfer function at corner frequency, exact magnitude and the Bode magnitude. Okay, you will get that your error will come out to be minus 20 log 2 zeta. Someday they will ask question from this, and that day you will not be able to solve this. Now will I tell you to remember the formula? Probably not, but if you can remember the formula. Derivation is here, you can see the derivation. Of course I will not be able to discuss the derivation here, I have to discuss other topics as well. Okay, so I hope you have understood this point. This is very important point. Error in dBs for the underdamped system, closed loop, for a closed loop transfer function of an underdamped system. Now whatever information I was missing for zeta, that is displayed. The error that I am getting, higher the zeta, higher the error, because I am missing the information about zeta. Okay, all the other information is stored in the plot, but the zeta information is not stored in the plot. Okay, so zeta equals to 1, again the same thing only, not that different. For zeta equals to 1, right, basically we are getting negative repeated real roots. Now nothing will be missed, right? We already know how to find out the Bode plot for negative repeated real roots. We know how to do that, right? I will get a slope of minus 40, and what will be the corner frequency? Now the corner frequency will be totally correct. The corner frequency will be at s equals to omega n. Okay, so corner frequency now is correct. Now the corner frequency is totally correct. Omega p equals to omega n. Now it is nothing incorrect. Okay, so for overdamped system, what type of roots we get? We get roots as unequal roots, like s plus 1 into s plus 2. Have we learned how to draw the Bode plot for this? Yes, that is what we have been learning from the starting. But I haven't taught you how to plot the Bode plot for complex conjugate poles. That is what we learned just now. Okay, but we have learned previously how to draw the Bode plot for repeated poles and for unequal poles. That we already know, unequal radial poles. Okay, that we have already studied. So this will be very, very simple. Okay, now GATE have asked a question from this same concept also. Okay, so what they are asking, the values of the constant gain term and the highest corner frequency of the Bode plot respectively are. So what will be the value of the constant gain term? So constant gain term, so what do they mean by constant gain term? Okay, so constant gain term means basically the k in the time constant format. Okay, k in the time constant format. Okay, time constant format. So first we have to find out the corner frequencies. So here I will write this in the time constant format. So this will be, so this, right, how do you convert a standard second order transfer function to a time constant format? This I forgot to tell you that initially, right, when I was doing some manipulation here, if you remember, just at the start of this topic, here I did something. What did I do? I normalized. What did I normalize? I divided everything by omega n. I divided everything by omega n. So to normalize this, right, you have to divide everything by omega n. So here also we have to divide everything by omega n. So remember to normalize. Remember to normalize. So this here, this you have to normalize. How will you normalize? Divide by omega n. What is the omega n? Divided by omega n square basically. What is the omega n square? That is 25. Okay, normalize. Divide by omega n square. Okay, so this will be 5 into 4 divided by s by 4 plus 1 divided by s into 0.25 into s by 0.125 plus 1 into s square divided by 5 square plus 4s divided by 25 plus 1 into 25. Of course, I have taken 25 common. Okay, so this will be what? This is 1 by 4, so this will be 16. This will cancel to be 5. So this will be 16 by 5. Okay, 16 by 5. 16 by 5 is what? 3.2. Okay, so 3.2 will be the constant gain term. So either this option is correct or this option is correct. Okay, now let's discuss about the highest corner frequency. So what is the corner frequencies? The corner frequencies here is 4. The corner frequency here is 0.25. The corner frequency here, what is the corner frequency here? It is 25, right? The omega n. Omega n is the corner frequency. So highest corner frequency, is it 25? Okay, so I also made the mistake. Corner frequency is not 25. Omega n square is 25. Okay, so the highest corner frequency will be omega n will be 5. Okay, so the highest corner frequency will be 5 in this case. Okay, highest corner frequency will be 5. So 5 will be the correct answer. So option A will be the correct answer for this question. Okay, I hope you understood the solution to this question. So now let's do few more questions on Bode plot. So let's do this question. So the asymptotic Bode phase plot is shown. Okay, this is a recent question. Both with k and p1, k is here, where is k, and p1 is here, both are positive. Then the value of p1 will be. So they do ask good questions from Bode phase plot as well. Okay, so again, if you observe from 0.01 to 0.1, my slope is minus 45 degree per decade. My slope is minus 45 degree per decade because I have moved minus 45 degrees in a decade. Okay, so that may be due to this one, right? Because this one will contribute its pole from, this one will contribute its like slope from 0.01 to 1. Okay, so 0.01 to 1. So this one will contribute this one. So minus 45 degree. So this is the case here. So this, right, is due to this omega p1. Now this pole will come into action from when? This pole will come into action from 1 to 100. Okay, from 1 to 100 this pole will come into action. Okay, now here right, I'm observing that I have moved a decade from 0.1 to 1 and my y value has reduced to 90. That means the slope here has been minus 90 degree per decade. Okay, that means what? That means this pole will be on action after 1, right? After 1, and this pole is still in action before 1. That means one extra pole must be lying somewhere here. One extra pole must be lying somewhere here whose effect is starting from 0.1. So the effect of a pole is starting from 0.1. When does the effect of a pole start? 10 times before its corner frequency. So 10 times P1 will be equals to 0.1. Okay, so P1 will be 1. Okay, you can cross verify, you can apply your methods. P1 will be 1, so the corner frequency P1 will be 1. Okay, that's how simply you can solve this question. Okay, so let's solve another question. So they do ask question from error as well sometimes. So the asymptotic Bode plot for the transfer function is given in the figure below. The error in the phase angle and the dB gain at omega equals to 0.5 are respectively. Okay, so how do you find out the error in the phase angle? So to find out the error in the phase angle, right, or and the what do you have to find? Error in phase angle and dB gain. Okay, so basically you have to find out the error in dB and in the phase as well. So first let us find out the error in dBs. So in dBs at 0.5 A. So I am here. So at 0.5 A, what will be the gain? According to the Bode gain plot, it will be 20 log K. But at 0.5 A, what will be the actual gain? So the gain at 0.5 A, this will be equals to K by 1 plus 0.5, like this will be 0.5 A divided by A. So ultimately this will become whole square only, whole under root, correct? So ultimately this will be K divided by 1 plus 0.5 whole square whole under root. So if I want to write this in log scale, in dB scale, this will be 20 log K minus 10 log of 1.25. So log of 1.25, log into 10, this will be 0.96. So this will be 20 log K minus 0.96, that is almost equal to 0.97. So my Bode gain plot is saying my gain should be 20 log K, but actually my gain should be this. So what is the error? Error will come out to be actual minus the approximated value, minus the approx. Okay, so the error comes out to be 20 log K minus 0.97 minus of the approximate value, that is 20 log K. So actually my error comes out to be minus 0.97 dBs. Remember the minus sign is important. Okay, else they will mention you the definition of error. You don't have to worry, they will mention you the definition of error. So this will be the answer, okay, for the Bode gain plot. But what about the Bode phase plot? The phase plot also they have shown me. Okay, that is the advantage. The phase plot also they have shown me. So I have to just find out the phase at 0.5 A. Okay, so how do I find the phase at 0.5 A? So I have to again use the concept of slope, right? So YB minus YA. YB is at omega equals to 0.5 A. So this is my YB. What is YA? YA is at the location 0.1 A. At location 0.1 A, the Y value is 0. Log of omega B by omega A. Omega B is 0.5 A. Omega A is 0.1 A. Okay. So this comes out to be, this is equals to what? The slope. What is the slope? Slope is minus 45 degree per decade. Okay. So this will come out to be, YB will be 5 log into 45. This will be equals to minus 0.45 degrees. Okay, minus 31.45 degrees. This is the angle that I get in the Bode plot. But what is the actual angle? What is the actual angle? So I have to write down the expression for actual angle. The expression for actual angle, this will be simply minus tan inverse omega by a. That's it. That's it. Okay. So this will be equals to simply minus tan inverse 0.5 a divided by a, that is 0.5 only. So what is tan inverse 0.5? It is 26.56 degrees. Okay. So I am just doing it in a hurry. So it is minus 26.56 degrees. So this will be the degrees value. Okay, actual value and the approximate value. So again the error will be what? Error will be actual minus approximate. Okay, so actually it is minus 26.56, but approximately it is minus 31.45. So this comes out to be, if I do this, 31.45, 4.89 degrees. Okay, so your error in the angle is 4.89 degrees. So let's solve this question as well. So this question is also again pretty good. This question I think came recently only. Okay, so here what are they telling? Given the figure shows below the Bode magnitude, gain and phase plot. Okay, so these are actually exact plots. These are not approximate plots. These are exact plots of a stable transformation like this. Then consider a negative unity feedback system with gain k in the feed forward path. The closed loop system is stable for k less than k0. The maximum value of k0 will be. Okay, so we have to find out the maximum value of k0. How do we find out the maximum value of k0? Okay, so what you can do is few things I can identify, right? What is the thing that I can identify? So the gain is 0 here. Okay, but they have not mentioned me, but here, right, the phase is minus 180 here. The phase is minus 180 here. So at minus 180, what is the gain? 20 dB. Does it ring any bells? So when does the phase become minus 180? At phase crossover frequency. And what is the gain at phase crossover frequency? They have given me the gain at phase crossover frequency as 20 dB. What is the gain margin at phase crossover frequency? Gain margin at phase crossover frequency is minus 20 dB. So obviously system is unstable because the gain margin is negative. Okay, so I have told you in polar plots as well, my phase crossover frequency should happen after gain crossover frequency for my system to be relatively stable. Told you, right? I hope you remember in the previous lectures. But here, right, omega gc is where? Omega gc is somewhere here. This is the point where my gain is 1, or in dB scale it is 0 dBs. So somehow this is k times this, right? Somehow what I have to do, this is k times this. So I have to bring this backwards. So how will I bring this backwards? That is what I have to think. Okay, so few information they have given you, like this n0 s cube by this thing. So will I be able to find out n0 by d0? Yes, because they have shown me that at 0, right, the gain is 36 dBs. At 0 frequency, that is at DC. Okay, so it is equals to 10 raised to power 1.8. I am doing directly. Basically it is 20 log of x. 20 log of x equals to 36. So your x is basically 10 raised to power 1.8. So it will be 1.8 raised to power 10, that is 6.3. So your DC gain is 6.3. Okay, so 36 divided by 1.8, 10 raised to power 1.8. Okay, something I'm doing wrong. 1.8, right? 1.8 if I do 10 raised to power, it will be 63. Yeah, it will be 63.1. Okay, so basically what is the DC gain at omega equal to 0, right? Omega equal to 0, basically I will be only left with n0 by d0. So my n0 by D naught is 63.1. Okay, N naught by D naught is 63.1, and my gain margin is minus 20 dB. Okay, gain margin is minus 20 dB. Now if I want to calculate the gain margin, so what will happen with the gain margin? Very interesting. Just listen to me. Current transfer function is what? This. What is the gain for this? The gain of this transfer function at omega equals to omega PC is what? 20 dBs. I can see from this graph, correct? Now I have done what? I have just simply multiplied k with the transfer function. What will happen to the gain? Now the gain, right? Log property. What will happen to the gain? Gain will become 20. If I have just simply multiplied, gain will be shifted by 20 log k, right? That is what will happen in the log scale, in the dB scale. It will be 20 log k plus the previous gain, whatever the previous gain was, g of omega previously. Okay. Now if I calculate this value at omega equals to omega PC, because if this k is changing, right? If this k is changing, phase crossover frequency will not change, gain crossover frequency will change, and that is what I want. So this will be equals to 20 log k, because this is not a function of omega, this is a function of omega. What is the value at omega equals to omega PC gain? The previous value, it was 20 dBs. It was 20 dBs plus 20 dB. Okay, plus 20. So this is the gain at omega equals to omega PC of the modified transfer function. What do I want? I want my gain margin, like for my system to be stable, my gain margin has to be greater than or equals to 0, correct? So this is not the gain actually. This is not the gain margin. This is the gain. To find out the gain margin, what we do? We just multiply a minus sign. Why? Because if I am writing something like this, right? 1 by gain of g omega. In log scale, how do I write? We simply write negative 20 log of g of j omega. Why? Because this, right, I can write as this has a power of g of magnitude of g of j omega raised to power minus 1. Of course, this is like basic class 12 thing, okay? Basic class 12 thing. I'm not going too much in depth here. So I hope you understand these things, why minus sign is coming, all those things, okay? I hope you get this point. So here I have to take a reciprocal, like already this is in dB scale. If I take the reciprocal in decimal scale, simply I have to multiply a minus 1, because this is the gain expression. This is not the gain margin. Gain margin is the inverse of the gain. So inverse in the decimal scale will be negative sign in the dB scale. I hope you understand simple reciprocal, simple log scale, okay? So I have to multiply a minus sign. So if I multiply minus sign, this will be minus 20 log of k minus 20. This is equals to my gain margin, okay? And my gain margin has to be, for the system to be stable, gain margin has to be greater than or equals to 0. So it will be 20 log k equals to minus 20. So k has to be equals to 0.1. Okay, this will be an answer. Now getting to the answer is not important. Understanding the concept. I got stuck here, right? Although I did this, okay, in the exam hall as well, I will think, okay, they have given some DC gain, so let me do the DC gain. I did this, right? Then I went into some other thought process, okay? Although in the exam as well, I will do this, but this was not useful. Then I quickly switch to some other thing, okay? So in the exam as well, you will do the same. You will do the same. You will think of something, then it may not work, then you will follow some other method, okay? So I hope you understood this point, and it is reasonable as well, right? It is reasonable as well. Why it is reasonable? Because I have to shift this more downwards, because I want my gain crossover frequency to come much more earlier. So that's why I will multiply, I will decimate this thing so that it shifts downward, so the gain crossover frequency comes much earlier, okay? Okay, so I hope you have understood this point. Now this question, these are the last two questions. We have to find out the transfer function from the given Bode plot and the error at the corner frequency. So if I see initially my slope is plus 20 dB per decade, that means I have a 0. That is for sure at origin, okay? Then at this 2 radian per second, my slope is going from plus 20 to minus 40. That means there is a decrease of minus 40 degree per decade. That means I will observe a pole at 2 radian per second, and it will be a repeated pole. of order 2. Okay, then what am I observing? I'm observing it is written zeta over here. If it is written zeta, then you stop. Then you stop. That means whatever you're doing, this is wrong. Okay, that means this is a underdamped system. For an underdamped system, yes, I observe a pole, like I observe two poles at 2 radian per second. The corner frequency is 2 radian per second. But as this is a underdamped system, so I have to write it like this. It will be S by omega n whole square plus 2 zeta omega by omega n plus 1. I hope you understand how to normalize. I have already told you at the starting. So zeta they have already given me. As zeta information is I cannot get from the graph, they have written the zeta. Zeta will be 0.6. Okay, zeta will be 0.6. So this will be S divided by omega n will be 2 because corner frequency is 2 square. 2 square plus 2 into zeta, that is 0.6 into omega divided by omega n, that is 2 only plus 1. Okay, so ultimately your transfer function, right, this I can delete, and initially the gain is minus 20. At 0.1 the gain is minus 20, that is basically 0.1 basically means k into 0.1 is 10 dBs, 10 in decimal scale. Okay, I'm doing it in a hurry. Okay, I hope you you can solve this. So k into 0.1 is 10. That means something, k into 0.1 is 10, right? Sorry, not 10 dBs. This is minus 20, right? That's why we should not be in a hurry. If this is minus 20, that means this will be 1 by 10 in decimal scale. So k will be 1. Okay, so k is 1. So ultimately, right, your transfer function will be something like this: 1 into s divided by s square by omega n square, that is 4, plus 2 zeta omega n. 2 into zeta is 0.6, 1.2, like 2 gets cancelled, so only 0.6 will be left. Okay, so it will be 0.6 into omega, or you can write s plus 1. Okay, this will be your transfer function. What will be the error? So error, of course, you can derive, but if you can remember, like only one formula I will tell you to remember, you can remember. Like very rarely this will get asked, so this you can leave this at low priority. You can leave this at low priority, but if you want to, like if you want to get in the top hundreds or top 50 rank, right, you should know everything. So error is minus 20 log 2 zeta. Okay, so like I know minus 20 log 1.2, I can directly solve. Okay, of course you can derive. I have not derived. I've shown you the derivation. You can derive with the derivation as well. So it will be 1.2. If I do log into 20, it will be minus 1.58 dBs. So this will be the error. This will be the error. So just be careful. If zeta is provided, right, then you solve using zeta. Else you would have assumed it to be a overdamped system. You would have assumed here to be repeated roots. Okay, so just be careful regarding that.
Let's start with gate PYQs of Bode plots. So yeah, the Bode plot for the transfer function V of s of the for the circuit shown. This is simply a RLC circuit is shown, right? Bode plot is shown. The value of R would be. So I am observing that I am getting a peak, and if you remember from the simple magnitude response of a second order system, we used to get a peak as well, right? And this peak was called the resonant frequency, right, at which the maximum value of the magnitude we get. And what is the resonant frequency of a simple RLC circuit? It is 1 by under root LC. So resonant frequency is supposed to be 2000. So from this, okay, already they have given me LNC. So yeah, that is of no use to me. But you can confirm actually here whether you are actually getting 2000 or not. Okay, you can confirm it. That is one thing. Now, what is the value of R? How can I find out the value of R? So I know the magnitude here, right? What is, so this is 0 dB. Magnitude at this resonant frequency is 26 dBs, right? So what is the magnitude? Magnitude of the transfer function. Magnitude of the transfer function is 26 dBs. So what is the value, magnitude of the transfer function at this resonant frequency in decimal scale? In decimal scale, it will be 26 by 20 raised to the power of 10, sorry, 26 by 20 raised to the power of 10, that is 19.95, which is approximately 20 only. So what is this actually? This is my output, magnitude of output over input, right? What is the transfer function here? Do you see what is the transfer function? Transfer function VO is the voltage across the capacitor and input, right? So do you know at resonance what is the voltage across the capacitor? It is actually Q times the input voltage. So Q times Vi, actually the voltage of the capacitor is Q times Vi. So Q is actually, if I take the magnitude, is magnitude of VO upon Vi. So this value, right, is nothing, 20 is nothing but the quality factor. Actually indirectly they have given me the quality factor. And what is simply a quality factor of a series RLC circuit? It is omega naught L by R. So omega naught is 2000 radian per second. So 2000 into L. L is 1 millihenry upon R. R is that is what I have to find out. Okay, R is that is what I have to find out. So R would be this 1 by, so 1 by 10. Okay, what I have, so this will be 0.1. 0.1. So your answer would be 0.1 for this question. Like, pretty simple question, but actually you have to understand what does this curve mean. That is also has been taught to you in the first chapter, right? Then you have to understand what is the quality factor. Okay, decode these things. So this will take some time. It is not that easy, but not that difficult as well, but not that simple as well, right? Again, it's like this response is just the response of a second order circuit. The magnitude and the phase plot are shown. Okay, what is the basically what is the transfer function? With the transfer function, what is the transfer function? So I see I'm getting a resonant at 100, but that is not enough for me. So what can I decode from here? What things can, so first of all I see the phase is actually somewhat decreasing linearly, and it is going to minus 720. That is again very interesting. It is going to minus 720 because at infinity this will dominate, so this will provide negative phase minus 180, and this will also, okay, this will also keep on reducing. Okay. So basically at infinity this will keep on reducing. I cannot comment about that. So it, like, somewhat I'm getting a linear response here, and it will keep on reduce. It will keep on reduce, like the phase will keep on reducing, and I see the magnitude also reducing negative. It is going to something negative, right? It is not always 0 dB. So definitely either this will be the answer or this will be the answer. There has to be some exponential, because if only this is the answer, right? If only this is the answer, then this at max can provide minus 180 degree of phase shift. That is, like, I'm getting a phase shift of minus 720. That is not possible here and here. So definitely these options are automatically eliminated. At DC, I'm observing the gain is 0 dB. That means in decimal scale it is 1. So if I put s equal to 0 here, this is also 1 and this is also 1. Both cases it is 1. So that thing is shorted. So these things are same actually. Only this part is different. Okay. That makes it even difficult. So this, right, will not change anything in the magnitude. That is for certain. What about the phase? Okay. Okay. At 100 radian per second, the phase is minus 360. At 100 radian per second, the phase is minus 360. So can I do something regarding that? So let me put the value omega equals to 100. So if I put the value omega equals to 100 here, this will be 10 cube minus omega square plus 2j omega plus 10,000, right? And omega is basically 100. Omega is 100 into e raised to power minus j 0.5. This will be very low, right? This will be very low value. So whatever phase this will provide, that will be very low, because phase will be addition of this transfer function and this transfer function. Like phase will be addition of this one, this will be very low phase, actually very low, almost approximately 0 degrees, because this value is very small. Whatever you multiply 100, this value is very small. So this will provide approximately 0. This will be 100 square. 100 square, if I do, this will be cancelled. So overall this will provide a phase shift of minus 90. Okay, so I get a phase shift of minus 90 here, which is incorrect. I should get minus 360, right? So that we will receive in option B. So this provides, because if I put omega equals to 100, this will be cancelled. I will have 100 upon some j term. So the phase of this will be minus 90, because j will go at the numerator. That will become minus 90 minus j. So this will be minus 90. So this, anyways, here also it provides minus 90 only. What about this part? How much phase does this provide? Remember, this is in radians. This is in radians. Okay, don't forget that. So if I multiply 100 with this will be minus 5. 5. Okay, in radians. What about in degrees? So what is 5 radians in degrees? So I have to multiply 180 upon pi. That is 286. 286 plus 90, approximately it is very near. So minus, this is minus 286. If I subtract 90, approximately this will be minus 360, around 360 only. Okay, minus 376, which is exactly matching. So of course option B will be correct answer for this question. So like that's how you solve. Simply calculate the phase and magnitude. Let's solve the next question. So consider a type 2 unity feedback system. The intersection of the initial minus 40 dB per degree segment. Consider a type 2. Type 2 meaning, so we'll have two poles at the origin. Unity feedback system. The intersection of the initial initial minus 40. So if it is a type 2 system, right? So there will be some intersection with the 0 dB axis, correct? Because I will get a slope of minus 40, because I have two poles, so I get a slope of minus 40. So intersection with the 0 dB line occurs at a frequency of 2 radian per second. The acceleration error coefficient, although they should have actually mentioned what is acceleration error coefficient, it is nothing. They should actually provide this information. It is limit as s tends to 0 s square g of s. That is what your acceleration error coefficient is. Okay, they should provide this information actually. So what is this actually? So basically I will have some k upon a square into some other values, s upon a or s upon omega z1 plus 1 and whatever, it can go on, right? But if I'm only considering 1 by omega is 2, correct? So the magnitude will be decided by this value only. Okay, and this, right, it crosses the 0 dB axis at omega equals to 2. So 0 dB meaning the magnitude of my transfer function is 1 in decimal scale. So k upon s square, that is s equal to 2 square, equals to 1. So k will be equals to simply 4, and my g of s square into g of s. So I will be equals to this k s square will be cancelled. Limit as s tends to 0. So I will have s upon omega. So I will have k s upon omega z1 plus 1 and so on. I will have some poles as well. But if I put s equal to 0, this will be automatically gone. Only k will be there. So basically they are asking me the value of k, that is nothing but 4. So 4 will be your answer for this particular question. Like I'm solving this very fast, but I have already built the foundation, already built the base. I'm expecting that you already know few concepts, right? I'm not teaching you from absolute zero basics. Okay, yeah. The Bode magnitude plot of a first order stable system is constant. Okay, magnitude plot is constant and phase is going to minus 180. So it seems like it is just a all pass filter or something like that. Okay, so phase first, okay, it is a first order stable system. First order stable system. If it's a first order stable system, that means I will have s plus a and s minus a, something like this, correct? Yes, I will have s plus a. This is the like all pass filter, right? Magnitude is constant and maximum phase it can provide is minus 180. Exactly, correct. So I will have a pole on the right hand side. I will have a zero. Sorry, I will have a pole on the left hand side, and I will have a zero on the right hand side, and they will be exactly symmetrical. So one left hand side pole and one right hand side zero at the same frequency. Correct. This statement is correct. One pole, one left hand side pole and one left hand side zero at the same frequency. Now, both cannot be on the left hand side, otherwise your phase will not go to minus 180. Your phase has to go to minus 180. That is not possible. So yeah, this is wrong. Two poles on the left hand side, one right hand zero. Again, if I have two poles on the on the left hand side and one right hand side zero, phase will not be minus 180. Okay, here also two right hand side pole, one left hand side pole. No, one left hand side, one left hand plane zero. Again incorrect, right? So first option is correct. It is simply the frequency response of a all pass filter. Let's go through this next question. The asymptotic magnitude Bode plot is given to you. Okay. Now, for the minimum phase system, so if it is a minimum phase system, basically it means that all poles and zeros are lying outside. Okay, none of the poles and zeros are lying inside. Sorry, all poles and zeros are lying on the left hand plane. None of them are lying on the right half plane, basically. Correct. So okay, that is one thing. The transfer function of the system is shown like this. K, Z, P are all positive constant, then A plus Z plus C would be equals to what? So magnitude plot is shown to me. So I see I have a initial slope of minus 20 dB per decade. That basically means that my initial pole would be 1 by S. So my B would be equals to 1. B is 1. Right? Initial pole is 1. So sorry, B is 1. So yeah, B is 1. So B is 1. That is for certain. And then I see that I am getting a 0 because the slope is going from minus 20 dB per decade to 0 dB. So I am observing I have a 0 1, I have a 1 0 here. Then again my slope is going from 0 to minus 40. So I will encounter two poles here. So overall, so those two poles are nothing but this one, right? So at the same place I am encountering the pole. So C is equals to 2 and my A is equals to 1. They are asking me A plus B plus C, that is nothing but 4. So A plus B plus C will be simply 4. So 4 would be your answer for the question. I hope you have understood this part. Yeah, let's solve the next question. In context of Bode magnitude plot, 40 dB per decade is same as what? So this thing already we know. 20 dB per decade is same as 6 dB per octave. So 40 dB per decade would be same as 12 dB per octave. So 12 dB per octave is option A. Okay, so option A would be your correct answer for the question. Like this is like very basic and simple question. So they do ask simple questions as well. So consider the stable closed loop system shown in the figure. The asymptotic Bode magnitude plot has a constant slope of minus 20 dB per decade at least till 100 radian per second. So the Bode plot has a slope of minus 20 dB per decade at least till minus 20 dB, at least till 100 radian per second with a gain crossover frequency of 10 radian per second. So basically gain crossover frequency means whenever the magnitude of my Bode plot becomes 0 dBs, that is my gain crossover frequency. So till 100 radian per second, the slope is minus 20 dB per decade. That is the information that they have given me. the asymptotic Bode phase plot remains constant at minus 90 till omega equals to 10 radian per second. So till omega equals to 10 radian per second, the phase plot is minus 90. So basically what does it mean? Basically it is a type 1 system, right? That's why phase is always minus 90 before uh, before 10 radian per second. The steady state error for a unit ramp input would be, so how do I calculate the steady state error for a unit ramp input? So okay, consider a stable closed loop system. So let us consider a system like this, k upon s, because it is a type 1 system, into whatever s plus alpha beta. They should have also mentioned the order of the system, they have not mentioned, but it will not be required actually. So what will be the steady state error for a unit ramp input? So if my input is unit ramp, what is the, like it is a negative unity feedback, right? So what is my error function? Error function is c of s minus r of s equals to, so c of s is nothing but, sorry, r of s minus c of s, what am I doing? R of s minus c of s, right? And c of s is nothing but r of s into t of s. So yeah, 1 minus t of s, correct? And my transfer function is this, right? This is my transfer function basically. Closed loop system. Sorry, this is not my transfer function. This is my open loop. This is my g of s, right? They have plotted the g of s. This is my g of s. So what is my t of s? T of s would be simply 1 divided by, sorry, g of s upon 1 plus g of s, right? So this would be k upon s into s plus alpha plus, although you can assume it to be higher order as well, it will not matter. At the end, it will not matter. Okay, you can assume it to be higher order, but it will not matter. Trust me. Okay, trust me. It will not matter. So yeah, now you're like, I can solve this directly. Your steady state error will be k. I can solve this directly, but let's do it with a method because I don't want you to remember the formula. So here, if I put the transfer function, basically your steady state error would be limit as s tends to 0, s into e of s, correct? So s into the unit ramp is s square into 1 minus t of s. So this will be basically minus k, this will be s into s plus alpha, k will be cancelled, s into s plus alpha plus k. So what is happening, if I put s equal to 0, right, first of all 1s will be cancelled here, 1s will be cancelled here. Now if I put s equal to 0, this will be simply, okay, that is interesting. Okay, although they have plotted the Bode plot, actually this should not be alpha, actually this should be proper s upon alpha plus 1, like something like this, right? This will be the Bode plot, proper Bode plot, right? S upon alpha plus 1. Yeah, I hope you remember how to convert this into proper time constant format. That is also what I have taught. I have taught that s by alpha plus 1. Yeah, s by alpha plus 1. Now if I put s equal to 0, only I will have k basically, right? I will have only k. K will be there, right? Everything else will be, so basically this will be, s will be cancelled, 1s will be cancelled here, 1s will be cancelled here. If I put s equal to 0, this will be gone, this will be gone. I will have 1 by k. So basically your steady state error is nothing but 1 by k. So what is the k? So this also I have taught to you, right? For less than 10, right? So for very low values of omega, so this, right, will be very small compared to 1. So simply this can be neglected. All the values can be neglected except this, because this does not have any real part. So your magnitude will be converted into k upon omega, that is 1, right? That is my gain cost of frequency. The magnitude is k upon omega, omega is 10. So k would be simply 10. So like these are all things that I have taught to you. So 1 by k would be 0.1. So your steady state error would be 0.1. This will be your answer for the question. Okay, yeah. Let's solve the next question. In the Bode plot, for a second order low pass filter is shown below. Second order low pass filter is shown. What is the frequency at which the attenuation is minus 80 dB? So it is a second order low pass filter. So if it's a second order low pass filter, I see that initially I'm getting 0 dB per decade, and here I should get minus 40 dB per decade because it is a second order. So they have approximated it directly that the slope is becoming minus 40 directly at the same pole location. So when will it become, when at which the attenuation is 80 dB? Basically, when the magnitude reduces by 80 dB, that is what attenuation means. So the slope is minus 40 dB per decade. So at each decade, the magnitude is reducing by 40. So after 1 kilohertz, at 10 kilohertz, the magnitude will be minus 40 dB, right? And at 100 kilohertz, because 10 times after this frequency, the magnitude would be 80 dB, minus 80 dB basically. It is reducing, so it will be minus 80 dB. So yeah, so at 100 kilohertz, the magnitude would be minus 80 dB. So 100 kilohertz would be your answer for the question. Very simple and easy to solve. So yeah, I guess with that we have finished with Bode plots and everything. Basically, the whole frequency response. Like, this was pretty quick. This does not take this does not took us much time actually. So frequency response is very simple, right? You can solve it very easily if you just know few things, right? So I will also share the revision X notes, so you can revise through the revision X notes as well. And of course, you can revise through this R-PYQ video. Like, if you have enjoyed this video, please hit the like button. Please comment down below what things you want next. Of course, we'll try to bring those things. Okay. So with that, I will end this R-PYQ video, and I will see you in the next lecture. Until then, happy learning.